Welcome to Samsung 6G Forum. Hello everyone, my name is Eddie Kwon from Samsung, EVP at Samsung Research. So I'm going to moderate today's forum. I'm very happy to welcome all of you to the first Samsung 6G Forum under the theme of the next hyper-connected experience for all. So this forum is being broadcast live online via Samsung YouTube channel. We have two sessions today, the morning session and afternoon session. So each session consists of talks by experts from industry and academia, followed by a panel discussion. So let me give you an idea of a bit more details how today's forum is organized. So shortly, so we're going to have opening speech by Sebastian Seung, who is the president of Samsung Research. Then the morning session, 6G air interface, will start with a keynote speech by Professor Jeff Andrew from University of Texas at Austin. Then we are going to have invited talks by three speakers. First, Charlie Zhang, Senior VP, Samsung Research America. Then Takehiro Nakamura, Senior VP from entity DOCOMO. Then Smee, Senior VP of Qualcomm Technologies. Then we are going to have 10-minute break. After that, we have the panel discussion on 6G technology to be moderated by Juho Lee, who is a fellow at the Samsung Research. Then we are going to have the 1-hour lunch break, during which there will be a Samsung Research 6G technology demos presented by Seung Choi, who is EVP at the Samsung Research. So in the afternoon session, we are going to start from keynote speech from Professor Tarik Taleb from University of Oulu, Finland. Then we are going to invite talk by three speakers. Seongju Meng, the master of Samsung Electronics, and then Professor Byung-hyo Sim from Samsung University, the Seoul National University. Then Professor Shi-jin from Southeast University. Then we are going to have the 10-minute tea break. After that, we are going to have the panel discussion on network AI to be coordinated by Seung Choi, EVP of Samsung Research. Then Seung Choi will conclude today's forum. So if you have questions during the speech, please leave your questions on the QA bullet board on our official website, and I will deliver the question to the speaker. In addition, we have a Q&A event going on. Those who leave questions on the Q&A board will have a chance to win small prizes. So please be encouraged to win the surprise. All right, let's get started with an opening speech by Sebastian Seung, president of Samsung Research.
Hello, everyone. It's my great pleasure to welcome you to the first Samsung 6G Forum. Communication has always been central to human existence. Advances in wireless communications continue to change our daily lives and support amazing new experiences. The commercialization of 5G networks is far from over. But we all know that preparing for the next generation of communications technology takes a decade. That's why R&D for 6G networks has already begun. 6G will be a fundamental technology that drives convergence of services between industries. 6G will be ultra-wideband, ultra-low delay, ultra-intelligent, and hyperspatial. Revolutionary technologies such as AI, robotics, and automation will usher in unprecedented paradigm shifts in wireless communication. And wireless networks will expand from connecting humans to connecting things. These circumstances lead to three major megatrends advancing towards 6G. The explosive increase in connected machines will drive increasing use of network bandwidth. The management of complexity using AI and machine learning will improve performance and reduce expenses. And finally, software-based implementations of network entities are becoming much more common. And this trend makes open source software with open interfaces an attractive option for realizing network functions. Our 6G vision is to provide the next hyper-connected experience for all. And we highlight three key 6G services, namely truly immersive extended reality, high-fidelity mobile holograms, and digital replicas. These new 6G services, which will become possible thanks to advances in communications technology, as well as other technologies such as sensing, imaging, displays, and AI, will be introduced through hyperconnectivity between humans and things. To enable such services, 6G should support a tremendous amount of real-time data processing, hyper-fast data rate, and extremely low latency. And architecturally, it should also enable convergence of communications and computing, support of new network entities, and guarantee security and privacy in an open network environment. From 2G to 5G, the mobile industry has achieved success after success. We believe that now is the right time to start preparing for 6G. Shaping 6G will require many years, as we've seen with previous generations, and will need lots of discussion and collaboration. I'm delighted that world-renowned experts from both academia and industry are joining us for the first Samsung 6G Forum today. We'll focus on the topics of 6G interface and intelligent networks, and demos of Samsung 6G innovations will also be presented. Please join me and enjoy the Samsung 6G Forum 2022 as we imagine the hyper-connected world of the future. Thank you.
Thank you, Sebastian, for the wonderful opening speech. So as you mentioned, I'm sure that it's time to prepare ourselves for the next generation, 6G. Thanks again, Sebastian. So now, Professor Jeffrey Andrews from University of Texas will give a keynote speech on the topic of deep learning in the 6G air interface. Professor Andrews, the floor is yours.
Hi, it's an honor to be with you today at the first Samsung 6G Forum. I'm really feel like it's a privilege to give this talk on deep learning for the 6G air interface to you. I'm Jeff Andrews, the director of 6G at UT, a research center at the University of Texas at Austin. And so today, what I'd like to talk about is first, I'm going to talk a little bit about what we're doing at UT and what we think key research directions are for 6G, as well as some of the impact we've had on 5G, including collaborating with Samsung. Then I'll talk briefly about my overall philosophy on what the role of machine learning is in 5G Advanced and the 6G air interface. And then I've prepared two specific recent works from my group that I think might be of interest to Samsung that are well aligned with the current directions in 5G advanced for machine learning. And as time allows, I'll speak about both of them, but particularly the first one. And I'll make some parting remarks. So that's my plan for this talk. And so first, I just want to briefly introduce our research center at UT Austin. It's one of the only and first 6G research centers in academia in North America. We launched it a little less than a year ago, and one of our founding affiliates was Samsung, along with some of these other companies, and we've had a great reception from the industry, a lot of enthusiasm, and in the first year, right around the time we launched and through today, we've added all these companies you see here, like Ericsson and Nokia, as well as satellite companies, auto companies like Stellantis and Honda, and navigation companies. So we're really excited about this enthusiastic reaction from industry, and we're actually having our first ever board meeting and 6G forum ourselves in Austin the same week that Samsung is. Now, what we're really about at 6G UT is fundamental research, basic research, curiosity-driven research that can impact 6G. Of course, educating people, young people who will become the leading innovators in the 2030 6G, the 2030s, the 6G era. I just want to highlight briefly some of the things we did with Samsung, primarily with the group in Dallas that Charlie Zhang leads, that had an impact on 5G. We wrote a paper back in 2014, myself, my former student Wan Choi, who's a professor at Seoul National University now, and Charlie wound up becoming the most cited paper on 5G. And also we were, interacted with Samsung really early on, starting around 2010, 2009 on mmWave. I remember having great meetings with Charlie and Farouk and Jerry at their facility in Richardson, Texas. And it really, in my point of view, this group was really out in front and really imagining how mmWave could work for cellular when everyone else thought it was that. This would never happen. And of course, it did happen. Some of the things that we did with them, my colleague Ted and my current colleague John Tamir, who was a student of Ted's at that time, is now a faculty member, did the first ever outdoor mmWave cellular type measurements, and they were done right on our building at UT Austin, and used by Samsung and the industry to help prove that mmWave could actually work in 5G. And we continued to do research, myself, Robert Heath, and others that had both theoretical and practical impact on mmWave's operation in 5G. So we've really had a great teamwork with the team in Dallas, who's a very innovative group of researchers. We've also had other impacts on LTE Advanced and 5G. I'll just briefly highlight some of them here. Work on het nets and small cell coverage and capacity. I think we have the landmark results there that was honored with 4 major best paper awards by the IEEE Communications Society. My colleague in 6G at UT, Al Bovik, has won 2 Emmy Awards for his groundbreaking video quality assessment algorithms and the streaming algorithms, which are used on nearly all video traffic in the United States, which accounts for over half of all bits going over the 5G network today. Then we have made major contributions that led to LTE Direct, as well as really recently, my colleagues Sanjay Shakatai and Gustavo Devesiana developed a theoretical underpinnings for how joint scheduling should work for the ultra-reliable low latency traffic and the smartphone type traffic in 5G. And this was honored just last year with the Best Paper Award in Networking by the Communication Society. So I think you can see that we're doing a wide variety of research that really does lead, in 5 years time to impact in the cellular ecosystem. Now, moving on to 6G, a natural question is what will 6G be needed for? The 5G era is really just finally getting going. Deployments are really ramping up, and we're just beginning kind of at the infancy of seeing new applications and verticals emerging in 5G. And this is, how I see 5G. It was kind of the first major step by the industry to support traffic other than smartphones. Now there was some baby steps in LTE Advanced, but one of the key design philosophies of 5G was to make it flexible, to make it forward compatible, and to enable mission critical type services as well as a wide variety of Internet of Things type applications. So these are a lot of the same things we're still waiting to really reach maturity. And so the question is, what will 6G need to do differently? And I think when we think about the 6G era, which from my mind is the 2030s, we'll probably get a first standard labeled as 6G towards the end of this decade and commercial rollout by 2030s. And given that 5G was specifically designed with this concept of being very flexible and being future-proof, what will we really need to break or to enhance in order to create a new G? And in my mind, it's really about applications that require huge data rates, massive connectivity, and situational awareness. And this awareness, I think, is the key defining aspect of a lot of the 6G applications that we're excited about. Things like the various flavors of virtual and extended reality, and driverless cars, and ubiquitous robots, things that need to not only have great connections that are real time and high bandwidth, but also be aware of what's going on around them. Now, although driverless cars are built to be autonomous, they don't really work right unless they can sense things and know about things outside of their own field of vision. Otherwise, they'll just have to drive too slowly, too conservatively, for example, taking left turns or going around corners or overtaking. It needs to know more than it can sense itself. And this is where the network comes in, both collecting sensor data from the devices, as well as actually sensing itself. The base stations in 6G will be dense and tower mounted, and this is the perfect place to put lots of sensors such as radars and lidars and visual sensors and other forms of sensing in order to build an unprecedented network awareness. And so we think this is a key defining aspect of 6G along with machine learning. Okay, so as far as 6G at UT, we've brainstormed this a great deal, had many meetings and discussions, and we see the 4 key research directions, at least that we're undertaking, and I think are fundamental underpinning for 6G, things that will be new, are machine learning is going to penetrate very deeply into 6G networks. We're already seeing it, to some extent in 5G. You can certainly do a lot of things with machine learning without explicit standard support, but understanding how machine learning can help us and actually building it into the standard so that it's assumed to be there, it's natively there, we think is a key aspect. And I want to highlight that this is something where I think our center at UT is really unique globally in that even for the last 15 years, the machine learning folks and the wireless folks sit on the same floor. Our students sit together, talk together. We attend all the same seminars. And this has just been an organic development because so many of the tools for theoretical machine learning are so closely related to a lot of the tools, the signal processing and optimization tools that we use for wireless. Many of our machine learning experts at UT, who are some of the top theoretical machine learning people in the field, have a background in wireless or information theory or optimization. And we've been publishing papers and collaborating and co-advising students way before machine learning and wireless was even a thing. In fact, we have machine learning wireless papers from 2006, 2007 that you can look up. So I think this is a unique thing that we actually really have these deep collaborations on this topic. And it's one of the main reasons I've moved into this area about 5 years ago. We also think sensing will be of great importance in 6G, as I mentioned, and we have people doing, really groundbreaking work on localization, and robust and secure sensing and navigation and sensor fusion. We also have ongoing work on waveform design that can do both communication and sensing. So, for example, you could have the same radio with like an OFDM type waveform that is optimized both for communication and sensing simultaneously. And we think the network will offer sensing as a service in addition to, of course, communication. Another key direction we think is new spectrum and topologies. Just to highlight those, I mean, the new dense LEO constellations being put up are really like nothing the world's ever seen. And these will be a big part of really enabling global coverage, which I think when you look at 5G, really it's designed mostly as a dense urban type of high data rate standard. And I think where we've fallen short so far is in really enabling global connectivity, which is more important than ever in this new era of increasingly remote work where people want to live, not necessarily in near big companies in big urban areas, as well as providing equity to communities that don't have great broadband coverage currently. We think new spectrum, of course, will be brought in, both new spectrum sharing techniques and rules by the federal agencies. This is a major theme in the United States right now, is trying to develop new spectrum sharing modalities that don't rely on such exclusive licensing. Mid-band spectrum is very interesting, 7 to 15 gigahertz. I see this as having a lot of potential, even though terahertz gets a lot of hype for 6G. At UT, we feel this is more useful for very short range connections or sensing applications, and maybe should be de-emphasized as far as actually as a cellular mobility supporting technology. And instead, we think mmWave really is just in its infancy, and it's going to take probably into the 6G era before we really get it working so that typical connections can harness the power. And that's one of the key technical topics that I'll talk about today. And then the fourth direction is on the network side. Obviously, there's the O-RAN push, which is very new and exciting, and the idea that the networks will be much more open, transparent, secure. These things aren't contradictory, because if everything's engineered to be more usable by everyone, you can see what's going on and you can identify bad actors more easily. And network slicing will become very important for a lot of these applications that we're trying to enable in 6G, where we'll have totally different types of service requirements for driverless cars versus smartphones versus some of the other Internet of Things applications, where you'll want to allocate different slices of the network virtually over the same infrastructure. And one of the key themes here is controlling cost. We can't just deploy all these different networks, and certainly the base stations will need to be very dense. And so to make this cost effective, there'll have to be unprecedented amount of sharing and cooperation and reuse of infrastructure across multiple different operators and different applications. So this, I think, is a key direction as well that we're working on. Okay, so now let me get on to more the theme of the talk, and this is on deep learning in particular at the physical layer in Mac. And before getting going, I just want to offer a little bit of sobriety. Okay, there's a lot of excitement. Tons of people in wireless have moved into this machine learning area in the last several years, and I think this is great because it's certainly a new topic and there's a lot of potential there. But I think it's also important to be realistic about where we stand today. And the 5G physical layer has been developed over decades, and it's guided by theory. And in some cases, this theory tells us what the ultimate upper bound is. A good example, in a downlink cellular system, single cell, we know exactly what the capacity is theoretically. And we know the way we're doing things now with multi-user MIMO, with an OFDM waveform, with orthogonal multiple access, and really strong error correction codes such as LDPCs. It's very tough to beat that. I mean, you can actually prove that you can't beat that by very much, assuming all the models hold and we have linearity in the transmitter and receiver and sufficient resolution. So where machine learning can really help out the physical layer is where things either don't obey the models or there's some other advantage to be gained. And so, I'll talk a little bit about this, but also on the implementation side, there's been a great deal of work. I know this from having been an engineer at Qualcomm and having some ASIC background myself. That it's like unbelievable, and certainly people at Samsung know this. What they can fit into a single ASIC now in terms of the modem. You have many different physical layers, different standards, and you've squeezed every last little nanowatt that they can out of this. So the idea that we're just going to get rid of all this and go to a GPU-based architecture, particularly on the device side, to me doesn't seem very realistic because of just how far we are along on this both theoretical and implementation pathway for the physical layer. So what's deep learning's role? Well, I think it's great. The people are researching ways to rip out that whole physical layer and to see where advantages can be gotten. I just cite a couple of works here, one from Nokia folks, Jacobs now at NVIDIA, as well as my own group and one of Sanjay's students, which joint work we did with Cisco a couple of years ago, where we show that, at least in terms of performance, communication performance, you can get very close or even exceed in some cases, what we, conventional theory-guided implementations. But, is that really compelling? Is just beating it by a dB or two in certain cases compelling? I'm not sure, but it's very interesting. And it's certainly something people might not have thought 5 years ago, that you could just put in a neural net and train it and from a signal processing standpoint, be very competitive with these custom designs. Now, 3 areas where I do think the machine learning can have a big impact are, broadly speaking, on site-specific learning and design. And what I mean here is that, if you look, each base station has a unique propagation environment, a unique area that it's serving where users might behave differently, cluster in different areas. And so this kind of one-size-fits-all approach where, or on the other hand, sort of custom human-based tuning is not the way to go. And this is, I think, where machine learning can have a big impact by trying to optimize each base station individually to do a great job in itself. And so I list some examples of that here. Another that I alluded to earlier is where we have transceivers that defy good models. As we go to really large bandwidths, it may not be possible to have high resolution analog to digital converters. So this is an area where perhaps we can plug the gaps with machine learning. Other nonlinearities in the RF or analog components, and the other example I'll speak today is where we have really large MIMO channels with many transmit and receive antennas, where you can't possibly fully estimate the channel with conventional methods. It would take forever. We're also feeding back then information on this. And this is, again, we started working on this a few years ago because it seemed like a cool topic for a deep learning tool. But this is also now something that's been pegged as a 5G advanced topic to look at for machine learning. And then finally, my colleague Heji Kim, who actually worked at Samsung not too long ago, has done some really nice work on kind of open problems in information theory, trying to find good approximate solutions using deep learning pipelines. Okay, so let me talk briefly about this one research. This will be a little more technical, but it's good, I think, to get beneath the buzzwords and look at something we can specifically do with deep learning. And at least for me, I'll say that from the work my group's done, this is the one that I'm most proud of and excited by, and I think has real potential for later 5G or 6G as a paradigm for how to do beam alignment. And I think, let's just talk about beam alignment. So, one of the most exciting features of 5G is that we have all this millimeter wave spectrum that we've now enabled through new features in the standard. So it's kind of can be viewed like a form of advanced carrier aggregation, where we have specific support for narrow beamforming and how you of course the real trick in 5G is that we need to have these narrow directional beams from the base station to the UE, and also the UE having a beam pointing back ideally at the base station. And there's been lots of ways proposed to do this, but how it's basically done today is you do a kind of a two-stage search. You send broad beams, and then you send refining beams, and it's a pretty laborious, slow process. And there's good reasons that it's done with this exhaustive search way, which doesn't seem that smart, but it seems like it's just a ripe area that we can do better. And I wouldn't, and I'd say this is fundamental. This is like kind of the key bottleneck, not only for millimeter wave to make it work with mobility and to make it work reliably, and to serve lots of users, but also if we're going to have any hope of going to the higher frequencies we need to be able to quickly align beams and then track those beams. So what should a beam alignment method do? And I think these are sort of what I would call the dream properties. So first of all, exhaustive search we consider as a baseline. We want to be much faster than that while still finding all the UEs. And this is where a lot of current clever techniques fail, is that they're great for aligning with a single UE through various, cute methods, but they can't find all the UEs in the cell necessarily. We would really, to do this, we'll see what's key is to adapt to the cell propagation environment so we don't spend a lot of time sending beams off in directions that are fruitless, where there aren't UEs or where we're blocked. We also don't want we don't want a technique that requires knowledge of the UE locations. That would be a bonus, but this information currently is not available. We can't assume it'll be available. And we wanted to ideally adhere to the current alignment framework to not have to tear out the standard. And by this I mean that the base station sends beam feedback and then sends a narrow beam. It should be scalable to both highly mobile UEs and to these higher carrier frequencies with narrow beams. Okay, so this is what we'd like to do. Let's see if we can do it. Okay, so our technique here that my student Ethan developed, and this was joint work, by the way, with Samsung, is we develop. It's like the 5G method, but better. Okay, so we, instead of using just a generic set of broad beams, we develop a custom probing codebook, and this is a neural network that we learned through training of the specific propagation environment. So each base station in the network would, train, somehow. Okay, we'll get to that later. To develop this custom probing codebook that's like perfectly matched to its propagation environment. Okay, and the goal of this probing codebook is to allow UEs from measuring these probing beams to report signal strength that provides like a signature that allows then a different neural network, a beam selection function, to pick the optimal narrow beam. Okay, now there's two ways that we've looked at. The first kind of obvious way is we have a codebook of say 64 or 128 narrow beams, and we try to pick the best one or identify the best 2 or 3 in that codebook. Okay, so that was our first work. That's approach 1. The second way is, well, instead of doing that, let's just take the feedback from the probing beams and then directly find an arbitrary direction that doesn't have to be from a codebook. It can just be arbitrary weights. Okay, and so how it works, like is you send all these beams. Each UE measures all the beams, sends feedback on each beam, so it doesn't just identify the best one, but it sends back the strength on each one. And this forms what's called a feature vector in machine learning that can be used to train the beam selection function. Okay, and the key thing here is to train these two neural networks, the probing codebook and the beam selection function. It's the end-to-end training of both of them together, which allows the magic to happen. So this is just a quick picture of them stacked, in the interest of time, I'll just move on to the details. So we have this is based on ray tracing. It's based on ray tracing in 4 different quite different environments, both indoors, outdoors. Our data set plus the deep MIMO data set, which was developed by Professor Al-Khatib at ASU, who's a recent alumni of our center at UT. So I won't go over it in detail, the environments, but basically there's places that UEs tend to be. There's blocking, there's non-line of sight, there's line of sight. So it's a very diverse set of data sets at both 28 gigahertz and 60 gigahertz. Okay, in a nutshell, the technique works really well. Okay, it outperforms even exhaustive search, but with about an order of magnitude fewer searches. So this would translate to roughly a 10x speed up in beam alignment. And the thing you'll see here, though, is particularly if we're willing to find the best 2 or 3 beams, we can really quickly, with just 6 or 8 probing beams, identify the best 2 or 3 narrow beams. So if we want just the best one, it takes a bit longer, but likely this one of the top 2 or 3, if we just pick one of those, would have a good enough SNR to enable communication. Okay. Now I think something's really interesting is to look what these probing beams that are learned by the neural network through the training look like. And for line of sight, they create this sort of, rather than just, doing this direction, then this direction, then this direction, they actually do multiple directions simultaneously, spreading out the energy. And so this allows, again, when the UE reports on, say, all 8 of these, it allows the beam selection function to learn over time where the UE probably is and which narrow beam to use. Now, for 9 line of sight, it actually learns, it finds reflectors. So these like large beams are actually seeking out the reflectors in the environment and reflecting off them. And it doesn't send any energy here where there's a blocking object. So I put a building there just to kind of highlight that. So, this is what you'd want it to do. It avoids wasting energy and instead directs energy in the most useful directions. So kind of passes the smell check here. So I'll call this the midterm review. This is for the just the code book based approach. So we get about a 10x speed up. Doesn't need to know UE locations. It takes advantage of the propagation environment and adheres to the framework of 5G. Okay. Now, the main thing here is we don't want to have the secondary search of 2 or 3 UEs. So we've been working on this for like 6 months, and we had a breakthrough just about a month ago on how to do this. And without going into the details, the key thing is to go directly for the complex weights with an element-wise normalization. And so this is the architecture. And we didn't just come up with this. This is through a great deal of experimentation and other techniques that worked okay. But this one works really well. Okay. And we found with this, so now we're taking the feedback from the probing beams. So the probing beams are, again, trained end to end. So they're different ones. And with just four probing beams. So you just send out 4 beams over the whole cell, and the UEs feedback, and we can get almost the optimal SNR. Optimal meaning if you exactly knew the channel and did the optimal beamforming vector to it, we can get almost that with just 4 probing beams, which is amazing, I think. And as far as misdetection probability, it becomes very low with about 4 or 6 beams, and so it means we can find all the UEs. And so what the cool thing about this is if you have multiple UEs around the cell, we just send these probing beams, they each feed back, and then you can immediately beamform to them. So there's no second phase of search. There's no refinement search. So this is truly really fast. And the SNR, like I said, is competitive with the optimal techniques. It's even better than exhaustive search. I mean, the fact that you could search every single beam and still beat this and beat that with just 4 beams, I think really speaks to the power of this technique. Okay, so just to wrap up, we're now 30 times faster than the current exhaustive search procedure in 5G with this technique, and it's a single shot beam alignment. So, like I said, I think this is a really interesting approach that I think the industry should look at something like this for 5G Advanced to really unleash the millimeter wave spectrum and get this beam alignment to work much quicker. And you obviously could support mobility much more easily with this type of approach as well. So I know I'm almost out of time. The second thing I was going to talk about, which I'll just say a couple words about, is another area that I think is ripe for deep learning, is in estimation of very high dimensional channels. Now, we've used a cool tool called Deep Generative Networks, which my colleague Alex Tamakis is one of the pioneers on, to develop essentially a inverse problem, an ill-posed inverse problem solution to the channel estimation problem. The key idea is that you train a deep generative model, so something that essentially creates a very high dimensional object like a channel matrix from a very low dimensional vector. Okay, and by training this again in a site-specific way over the propagation environments of the cell, you can develop essentially a map of all the possible channels you could see that then can be indexed with a low dimensional vector that you can optimize to represent the current channel very, very accurately, even with just a small number of pilots. Okay, and this is essentially the pilots are used here. So again, I don't have time to explain this. We have some really recent papers that also show how to do this in a centralized fashion. But we were able to outperform all the state-of-the-art baselines by a pretty large margin, several dB, with fewer pilots, and with reasonable complexity. And a cool bonus of this technique is by doing the channel estimation with this low dimensional object, you can then use this low dimensional object, this vector, as a hyper compressed version of the channel that can then be used for feedback or communicating what channel you have to the other side. So it's like it kind of natively has very strong channel compression, which can be used for conveying this. Again, something that's of emphasis in the upcoming work item for 5G Advanced. Okay, so just my parting comments. Deep learning and the various flavors of deep learning, and there's a lot of them, more every year, are a powerful tool for 6G wireless that we should look at very carefully to understand. But we shouldn't expect it to really work magic. I mean, it's a tool. It's a powerful tool. It's an evolving tool. And but to actually apply it properly, you really have to understand wireless communications fundamentals. And I think this is why it's so important for us to continue to train students in the wireless fundamentals, which require very intensive multi-year study, along with learning the latest machine learning, and having students that are experts in both of these collaborating and talking, I think is essential to make progress on this topic and to do novel work. I think one last thing I'd like to highlight is to do this style of research, we need good data sets and publicly agreed upon simulators so we can verify results, get kind of friendly competitions going. We've tried to do this as much as possible in my own research, releasing our data, releasing our code. And actually, I love seeing it when somebody takes our approach and improves it and shows they can beat us. I mean, that's great. And I think that's the kind of spirit we need to really make machine learning reach its potential. And that's all I had. I look forward to taking any questions and chatting with you further.
All right. Okay, thanks a lot, Professor Andrews, for very inspirational insight about ML's role in wireless communications. In particular, 3-5 areas where the ML can have a big impact seems to be quite compelling. So let me take a question from the Q&A bulletin board. So in the interest of time, probably we can address only one question. So the question is, the data set is important for deep learning. So you also mentioned that this is a big challenge on which the industry and academia can cooperate. So can you give us a bit more details how we can tackle this challenge?
Yeah, so the data sets that we need are obviously different depending on what you're trying to engineer. Like in my beam alignment one, you would want channels all over the entire cell to many different UEs, and then if you had all these channels, like thousands or hundreds of thousands of them, you could then fairly compare different beam alignment methods like ours to other ones and see which one's really the best. I mean, so that's an example of a data set that is actually really hard to create. I mean, we created it synthetically using ray tracing, and it took quite a bit of time, and we also used the other one from Arizona State University. But having like industry, which has a lot more money and resources and equipment, for example, provide a great data set on this on, say 8 different cellular cases, a dense, just like we have channel models for 3GPP, if we actually had data sets that were much richer, that were agreed upon in, say, 3GPP that then academics could use and companies could use, I think this is important, and it depends on the problem at hand. But the last thing I'll say on that is that if you want to do transmitter optimization, in many cases, the data set isn't good enough, though, because much of what you're trying to do with the transmitter actually affects what's going on in the system. Like say if you're scheduling or what kind of transmission technique you use, you're trying to avoid interference. And so in that case, you need an agreed upon simulator rather than just a static data set.
All right. Yeah. Thank you. So I agree that there are a lot of things that we should work together between the academia and industry. All right. Thanks again. It's time to move to the invited talks. Okay. We'll see you again in the panel discussion. Okay.
Look forward.
Okay. So now invited talks from 3 speakers. First, Charlie Zhang, Senior VP, the Samsung Research America, will give us a presentation on radio technology evolution for beyond 5G and 6G. The Charlie is all yours.
Good morning. Welcome to the Samsung 6G Forum. I'm Charlie Zhang from Samsung Research America. It's a huge honor to be here today and share our vision on beyond 5G and 6G radio technology. Before talking about beyond 5G and 6G, let's take a look at where we are in terms of 5G. As everybody understands, 5G started about 3 years ago in April. Things have been picking up speed very well across the world. Right now, the deployment is going on in many countries and across many operators. And if you look at adoption rate, more than 500 million users already using 5G. And sometime this year in 2022, we're gonna hit the major milestone of 1 billion 5G users. This is a huge achievement because it's 3 years faster than 4G, because in 4G days, in comparison, it took about 6 years to reach that 1 billion user milestone. So things are going great and a really good success story for 5G. And Samsung as a company, we are very proud to be a part of this success story from day one. We're probably the only company that was able to support both sides of communication link, both from the PlayStation side and as well as from the smartphone terminal side. So if there's one thing that we learned from this process throughout this 5G initiatives, as well as commercialization R&D process, is that when it comes to wireless technology, you have to start early. You have to invest early, prepare the technology. And another thing, you have to work closely with your partners in the ecosystem. Wireless system is very complex. No company alone can do it by themselves. So even though now we are talking about 6G, the technology may be a little bit different, but I think these fundamental lessons learned will really serve us very well going forward. So let's take a quick look at the standardization side. So the 3GPP is a place where the 5G standard is taking place. So recently they just finished the first group of what we call initial 5G standards from release 15 to release 16 and release 17. So this initial group is really forming the foundation to enable a commercialization of 5G on a global scale. And release 15 is a starting point, and a lot of feature extension and optimization was taking place in release 16 and 17. Going forward, starting from release 18, we're going to shift gears and really take a big leap forward to address 2 key things. One is to add all these tools to really enable new vertical markets, both for the outdoor markets as well as for the indoor markets, such as warehouse, retail, healthcare, and so on. Another thing is to address some of the key issues identified during the 5G deployment, for example, the coverage issue, and so on. So that's where we are in terms of 5G standards and technology development. Now, if we take a step back, look a little bit forward, think about a few years into the future, we do see that there's many exciting new applications and use cases emerging, especially in the multimedia area, for example, truly immersive XR, high fidelity mobile hologram, digital replica. So these things, traditionally, we think of them as sci-fi movies, right? So, but now they're getting closer to reality. In many sense, that was thanks to the technology advancement in many related fields. For example, the multimedia camera capturing, delivery systems, as well as 3D displays, for example. But if you think about it, if you really want to bring these multimedia applications to life, right, anytime, anywhere, then you really need very high capability, high throughput, low latency wireless systems. That's where we see there's a gap between the capability of today's 5G and the requirement of some of these future multimedia applications. So because of that, that motivates us to think about in the future for 6G, what could be the requirements, right? So there will be a few different aspects. There will be traditional performance KPIs, for example, peak rate. We expect to hit 1 terabit per second. And also the average user data rate will be gigabit per second. Latency will be also much shorter compared to what we have today. So that's a KPI performance numbers. In the meantime, it's also very important to consider other requirement aspects, including the architectural requirements, as well as, for example, trustworthiness requirements. So especially in 6G, we expect this new network, new technology to be very open and transparent to start with, right? So with openness, it comes also higher level of security threat. So that's why it's very important to take into account this aspect and really think about security and privacy from the beginning of the 6G network and technology development. Then, once you have a rough understanding for these requirements, we are thinking about what could be the possible future technologies as candidates for 6G. So it's still very early days. I would say there will be some changes and movements, but by and large, we see a few interesting and important technologies on the horizon, including looking into new spectrum such as terahertz and upper mid-band spectrum, such as and technology such as AI native design, new antenna technology, new network topology that go beyond today's simple tree topology, and advanced duplex technology, MIMO, and so on. So these individual technology will play a big role in the future, but really most important thing is all of these new technology will kind of have to work together in an integrated way to support all these 6G use cases and very demanding requirement that we talked about a little bit earlier. Now, first thing maybe to look into whenever we think about new generation of wireless technology is spectrum, right? Spectrum, there's 3 most important things in wireless technology: spectrum, spectrum, spectrum. So for 5G, we looked into new band opportunities, including mid-band at 3.5 gigahertz to 6 gigahertz, and as well as mmWave spectrum from 24 gigahertz to 92 gigahertz. Including the early success for commercialization bands in 28 and 39. So similarly for 6G, we are looking at 2 new bands that looks very promising. The first one is the upper mid band from 7 to 24 gigahertz, and the second one is sub-terahertz band from 92 to 300 gigahertz. So upper mid band is a little bit above today's mid-band that's used for 5G, right? So as we know, one of the key things that enabled the mid-band in 5G is massive MIMO, large MIMO systems. So we expect the similar innovation to continue, maybe make it even bigger. For example, go from a 64 TRX system to a 256 transmit receive system in order to satisfy the requirement in those higher bands with a larger path loss. So I think this is a very excellent band eventually, with some of the innovation taking place, can provide excellent capacity with reasonable coverage. Now, on the other side, we also have this very large, really enormous amount of bandwidth sitting there in sub-terahertz band. So this is another very good opportunity for us to find enough capacity for all these exciting 6G services, right? So almost more than 200 gigahertz of available bandwidth there. So another thing that's very exciting about this sub-terahertz band is it naturally supports this joint communication and sensing. And really thanks to the large band that's there, and also ability to support dense array, because at those frequency, the wavelength is much smaller. So it's much easier to pack a dense and huge amount of antennas in a small form factor. So with that, you have much better spatial resolution if you want to do sensing, in addition to the traditional role of communication for these RF spectrum and systems. And next, we'll share a little bit about our sort of initial study for terahertz systems and what we learned from our initial research. So first thing we learned is there's a lot of challenges, of course, for these new bands, right? As we understand very well, when the frequency go up to these bands, you have much higher path loss. The PA output power goes much lower, efficiency goes much lower. and also a huge amount of complexity. So in order to do this ultra dense antenna array, and things that we never realized existed, like problems such as how do you do packaging? Packaging used to be really a very late stage research problem, but now we have to consider them in the very beginning, because now the chip size is getting very close, or maybe to the size of the antenna spacing, because the wavelength is so small, so making it very difficult for us to find room to put those chips on the RF module. On the other side, despite all these challenges, we also see opportunities in those new bands, right, for technology innovations. I mean, because of the band, because of the wavelength is small, you can see that now we can pack a lot of dense array and large array with much bigger beam gain at much smaller size, more suitable for the future smartphone form factors, for example. And also another thing is, when you consider antenna in package technology, now because of everything scales down, the size becomes smaller, your feed line becomes much smaller. So the loss of the RF signal strength between the front end module to the antenna becomes smaller, make it possible for us to design future systems to be a little bit more efficient. So, of course, the only way to really understand whether this technology works or not is to put them all together in a prototype system and try them out in the real field, right? This is exactly what we did. In Samsung, we carried out a series of experiments based on the last few years of work, and to see the feasibility of the 6G terahertz with adaptive beamforming. So last year we did two tests. One is indoor at 12 gigabit per second, 30 meter distance, and the other is outdoor, 2.3 gigahertz at 120 meter distance. And both of them were carried out in our Plano, Texas office. And both are pretty successful. You can see also we developed these modules that's really small in an area that's almost smaller than the size of a penny. We were able to pack this 8TX and 8RX, including 64 antennas. I also want to emphasize this is really a collaboration work between Professor Mark Rodwell of UCSB and Samsung. So it's without the RFIC chip that's provided by Professor Mark Rodwell, it wouldn't have been possible. So this is also another example is why this research collaboration is so important. You have to work together with your partners in the ecosystem, because there's too many challenges and too many complexity for a single company or research entity to handle by themselves. So this is what we did, our initial finding, pretty promising, but I think it's still a long way to go before this can become a commercial reality. Now, moving on to the next group of technology, what we call advanced duplex technology. So duplex technology has been pretty stable, I would say, all the way from 1G to 5G. We typically use either TDD or FDD to separate uplink traffic from downlink traffic. But from 5G advanced to 6G, looks like there's some exciting changes and developments. For example, in the 5G advanced, we are looking at something called XDD, or cross duplex division, with a goal to extend the coverage of those 5G advanced systems. And then eventually we see that there's a chance of us moving towards something called 4 duplex, meaning that in the same slot of time and frequency, you can support both downlink and uplink simultaneously. This is very exciting, because if we can achieve that, we can almost double the capacity of the future systems. So let me share a little bit of our recent work in this XDD area. So here again, as I mentioned earlier, the goal is to sort of extend the coverage for the traditional TDD systems, because if you look at the coverage map here, it's a little bit smaller compared to the low band FDD. And part of the reason is TDD doesn't allow the user to transmit at all times. So the idea is very simple, right? So instead of a very strict separation between downlink and uplink, now we allow some of the uplink traffic to happen during traditional downlink time slots. Now, of course, the challenge of doing that is once you put uplink and downlink together in the same time slot, then you create self-interference, right? So that's something that we have to address, and we did develop some technology. It's called self-interference cancellation technology in both antenna RF and digital domain to suppress and mitigate those interference. And You can see the initial result was pretty promising. We were able to achieve almost 10 dB improvement compared to the situation where you don't apply those algorithms. So that could be a very interesting thing to look forward to in the future. And then another thing that technology that we are looking into is MIMO advancement. MIMO is very important technology. For example, one of the key enabling technology for 5G is this FD-MIMO or massive MIMO, and it was able to provide 2 to 3 times capacity gain compared to LTE MIMO, 4x4 MIMO. Now going forward, we were thinking maybe by distributing these MIMO RF modules across space, you can further improve the system capacity by almost up to 2 times. We give a name of 4X Lego MIMO. So the idea is very simple, right? So, and also there's intuition behind that, because by distributing these modules, you can get closer to the end users. You can also more effectively support the case where user is more clustered together with little spatial separation. So we did some initial prototyping work, and you can see it's working out pretty well. So this is a case where we have 3 RF modules and supporting a group of 6 users about 20 meters away. In this case, users are very close to each other, right? So and then you look at results, you can see that if you only turn on 1 or 2 RF units, the performance is not that good. But then when you turn on the 3rd RF unit that's a little bit farther away from the first 2 units, then all of a sudden there's a huge jump in the system capacity. So it really shows you the benefit of really being able to separate out some of the RF modules. Okay, so that's the advanced MIMO technology. I think there's a lot of work to do during the beyond 5G and 6G research, but I think there's a lot of promise in this direction as well. Last group of technology I want to touch upon is AI for beyond 5G and 6G. So AI is already being used a lot, actually, in today's 4G, 5G systems, both from the mobile phone as well as from the network perspective, especially to help with automation and optimization when you have a lot of these previously very labor-intensive work, right? So here I'm just showing a few examples where we have some experience, for example, working on the mobile phone side to use AI to drive intelligent Wi-Fi and cellular connection choices. That was commercialized in 2019 on Galaxy S10. And also recently, we used AI to help support this, what we call adaptive Wi-Fi parameter setting. And was able to actually, it's very amazing, this using AI to learn the service type and then adjust the Wi-Fi parameter accordingly. We can save the Wi-Fi battery consumption by almost 30%. And similarly, on network side, there's a lot of interesting applications that we can think of, including the cell planning. In interest of time, probably skip this one and then move to talk about where we see the difference between the 5G and 6G, right? 5G, we do see still a lot of other exciting applications on the planning, on the prediction, management, and so on. But when it goes to 6G, that's when we see you can start from the clean slate of paper, really think about how to integrate this from the AI in a native way, into the protocol stacks, right? One way to look at this is a lot of these applications for AI today is local, but then in 5G Advanced, in release 18, we're already starting to look at this joint AI by putting some model to connect this, different AI units in UE side, base station side together, and then look further into 6G. And we think about more comprehensive AI to really achieve this end-to-end optimization of network performance and operation. So another question people could typically ask is, why AI? Why would AI, do better than traditional methods? So there's a few intuitions that we see are very important to answer that question, including that much better global awareness if you can do joint AI. And also AI is naturally suitable for joint optimization across functions and layers and handling things such as nonlinearity and long-term correlations. So these are some examples, I think, especially on the radio side that's emerging, but there are many other examples. So, but I think the key point is this is just beginning point. I think there's a lot of exciting research to be done really to bring this AI native design to the future 6G. with this, probably I'll move on to talk a little bit about the 6G timeline. So if you look at 3GPP side on the standard, next two releases will be release 18 and 19, still a little bit more on the 5G advanced side. Then starting from sometime in 2025, now that's where we're going to start getting to 6G with initial study item, then followed by work items. And similarly, ITU-R is also starting their standardization process. So everything has to work together eventually to support this standard, so so that we can commercialize and finish the specification around 2030. It may sound very far out, but once you break them down into all these necessary steps, all of a sudden you can see, right? You don't have much time left between now and when the 6G standards will actually start sometime in 2025. So yet again, a reminder for us that we have to start early. We have to get more broad-based support, right? Which is, if you look at what's happening globally, I'm very happy to see for 6G, there's much better global awareness of the necessity of early investment, early participation, and global consensus building and contribution from early stage, right? From United States, from Europe, from Asia, and so on. So I think when it comes to wireless technology, from our experience, it really takes a village to build these wireless networks of the future, right? It gets so complex, and it's not easy to do by a single company or country. So with this, I would like to share this African saying: if you want to go fast, go alone. If you want to go far, go together, right? So, really hope everybody can join us in this journey and enjoy the road to 6G together. Thank you very much for your time.
Thank you very much, Charlie, for the very nice presentation. I really like the proverb on your last slide. So I hope we can go all together. So I see quite a few questions on the Q&A board. So first question is there a specific challenge in the uplink for upper midband?
Yes, Eddie, that's a great question. Definitely there are many challenges for uplink, including how do you provide sufficient uplink capacity for all these hundreds of billions of users, IoT users especially, that we imagine, right? So specifically for the upper mid-band, 7 to 24 gigahertz band, there's also this additional challenge of coverage. As we know, for example, even for 5G at 3.5 gigahertz, we're already seeing the coverage of the these cells at 3.5 gigahertz is somewhat worse compared to the traditional lower bands, because the frequency is a bit higher, the path loss is a little bit stronger, right? So if we go to upper mid-band, situation will be a little bit even worse. And also very important to understand, typically when we think about coverage of a wireless system, it's always uplink limited. So that's very important to think about new technology that can address this from very beginning. I think, for example, the advanced duplex technology that I talked about, this XDD could be very helpful, both for today's 3.5 gigahertz as well as for the future upper mid-band going forward.
All right. Yeah. Thank you, Charlie. Yeah, it's not bad. We have a lot of the challenges there. We have a lot of things to work together, right? So I think it's time to move on. So we will see you again in the panel discussion.
Sounds great. Thank
you.
Okay.
Thank you, Charlie. So yeah, all right. The next speaker is Takehiro Nakamura, the Senior VP from NTT DOCOMO. So he's going to provide the presentation on 5G evolution and 6G. So Nakamura-san, it's all yours.
Hello, my name is Takehiro Nakamura of NTT DOCOMO. Thank you very much for inviting me to the great event, Samsung 6G Forum. It is a great honor for me to talk in this event. NTT DOCOMO is now very aggressive for 5G evolution and the 6G, and NTT Group is promoting ION, innovative optical and wireless network. In this presentation, I will explain our vision and the latest activities for 5G evolution and 6G. Cyber Physical System CPS or Cyber Physical Fusion CPF is essential and fundamental to provide and create new services for now. They will be more important and will be advanced in the future. Huge amount of data need to be transferred from physical space to cyberspace. The data is analyzed and processed by AI in the cyberspace, and then the processed data should be actuated in the physical space real-time manner. Network of 5G evolution and 6G need to support future CPS CPF by its 6 extremely high performance characteristics in terms of data rate capacity, low latency, coverage, reliability, energy and cost, and massive connectivity and sensing. I'd like to explain potential technologies for 5G evolution and 6G in the next slide. This slide shows technical development and research areas for 5G evolution and 6G. We can consider many technical components, and we listed 8 major research areas here. Some of them are further enhancement from the 5G, such as URLLC and massive MIMO. Some new technologies need to be studied. New network topologies such as RIS, dielectric waveguide, should be studied to extend and improve coverage efficiently, and with low cost, especially for higher frequency bands. Non-terrestrial network with HAPS and satellite is essential to realize 100% geographical coverage and to extend the coverage to sea and sky. Frequency extension to exploit higher frequency up to terahertz level. Very wide frequency bandwidth is very interesting and important topic to meet requirements on very high data rate and high capacity. After this, I'd like to explain some of very interesting technologies we are studying. As technologies for coverage extension, I will explain NTN HAPS. We believe that coverage should be extended drastically toward the 6G era, not only area where people live, but also 100% of geographical area, sea and sky, should be the communication coverage in 2030s. Conventional terrestrial network cannot be the solution for drastic coverage extension. Non-terrestrial network, so-called NTN, is the solution for it. We can have 3 kinds of technologies for NTN, ZEO, LEO, and HAPS. ZEO satellite communication services have been provided all over the world, including Japan. Very wide coverage services can be provided by ZEO. On the other hand, performance in terms of data rate and latency is not so good due to very long distance. LEO is very interesting solution now. Several major companies have launched so many satellites already, and it is expected that the LEO communication services will start in near future. HAPS, high altitude platform station, is also very interesting solution. We can expect very high performance with HAPS as next to very short distance, around 20 kilometers. We believe that HAPS can support more business use cases thanks to very high performance in terms of data rate and latency. This slide shows some kind of the actual use cases. Yes, so not only the disaster case, public safety case, but also the coverage for sea and coverage for the instruction area, IoT devices, services. Yeah, many use cases we can consider. We developed HAPS simulator to evaluate the data rate performance of HAPS communication system. We are updating this simulator, and the latest version of the simulator has functions for both of downlink and uplink, direct link for CPE and smartphone, as well as cell backhaul. Also, interference reduction and frequency sharing with terrestrial network according to various environments such as construction area, ships on the sea, and airplane in the sky. Major parameters are shown in the left bottom table. Let's watch the screen capture video of the HAPS simulator. You can see two HAPS on the screen. Each HAPS is supporting multiple connections for so many terminals at a variety of environments. Left-hand side graph shows a distribution of calculated user throughput and the SINR. The results show that several tens megabps of data rate can be provided to many of terminals via HAPS. Due to limited time, I will skip the details explanation. We are optimizing the simulator and we will provide more details in the evaluated result on HAPS communications at another opportunity. From here, I'd like to explain our activities for terahertz frequency. NO support frequency band up to around 50 gigahertz, and we think that it will be extended to approximately 90 gigahertz in future releases. 6G should exploit higher frequency bands, terahertz wave, with remarkably wider bandwidth to achieve extreme high data rate exceeding 100 gigabps. Considering serious challenges in terms of high propagation loss and RF device availability, we think that the 300 gigahertz is good target at the highest frequency for study on 6G. We should develop experimental system and conduct trials to evaluate the performance of 6G technologies at terahertz. However, it is premature to do it, and it is difficult to evaluate the 6G system performance with many user equipment and at wide area by trials at real fields. Therefore, we developed the 6G simulator. In the next slide, I will show a screen capture video of the 6G simulator. Let's go. This simulator supports use of terahertz frequency at factory environment. In this video, we set the center frequency of 100 gigahertz and the frequency bandwidth of 8 gigahertz. Uplink and downlink throughput performance can be evaluated simultaneously. And uplink downlink ratio can be changed flexibly. BS antennas are set on the roof on the factory to have line of sight environment as much as possible. Left bottom graph shows the ratio of UEs classified by downlink uplink throughput. With this condition, many of UE can experience 10 to 50 gigahertz short by green, as you can see. From here, I will explain our views and activities for innovative application in 6G era. This slide shows our high-level observation and views on mobile communication services. We think that mobile services up to 5G have improved functions and increased efficiencies for smart physical world. In our 6G vision, on the other hand, human sensations, emotions, and so on will be communicated, contributing to our customers' well-being. Thanks to very high performance of 6G network in terms of extremely high data rate and low latency, 6G network can perform as human nerves, so that 6G network can augment and extend human capabilities. If we can share body movement, 5 senses, and emotions through 6G network, as shown in this figure, we can realize very interesting and exciting new services, which were described as science fiction, such as telepathy, telekinesis. We can go beyond the constraint of space and time and realize ubiquitous body, superhuman, and so on. To show potential application of the human augmentation, we developed the human augmentation platform for demonstration. This platform treats sensing data of human activities such as electric activity in brain, myoelectricity. The sensing data is registered, reproduced, and stored in the platform and can be actuated with robot and human body in physical and cyberspaces. I will show some demos of this platform. This is demo on the transfer of human arm motion to a robot arm through the platform. As you can see, arm motion of the person can be transferred to the robot's arm correctly. Small white devices on the person's arms are sensors for motion and myoelectricity. The sensing data of the device is transmitted to the platform and reproduced to adjust motion of the robot. This is another approach to transfer human arm motion transfer to another human's arm. As you can see, the arm motion of the person on the right is transferred to the arm of the person on the left. The person on the right wears the same sensor which are used in the previous video. The person on the left wears the myoelectric devices on his arm to actuate motion of the arm of the person on the right. In this demo, the platform reproduced the sensing data for the person on the left so that the arm motion can be transferred between two humans properly. Two videos I explained are one-to-one connection demos. The platform can make one-to-multi connections. It means one sensing data can be transferred and actuated to multiple objects. Let's see it. In this demo, hand motion of the left top person is transferred to three objects: another person's hand in the left bottom, the robot arm in the right bottom, and hand in cyberspace in the left top. These are our first step of human augmentation trials. We will improve performance and connect additional sensing devices and actuations, showing potential use cases in 6G era. Finally, I'd like to explain our concept on 5G evolution at 6G, powered by ION. ION Innovative Optical and Wireless Network is an entity group's concept on the platform for communications and information processing toward the 2030s. Direction of ION is same as concept of 5G evolution at 6G. Technologies of 5G evolution and 6G can be combined with those of ION to further enhance the next generation ICT infrastructure and respond to the pressing needs of society. We have published the first version of our white paper on 5G evolution and 6G in January 2020 and updated. The fourth version of capturing our latest study results was published in the last November. You can find this on our website. We are happy if you review this and give us your feedback. That's my presentation. Thank you for your attention. I hope to have opportunities to discuss 5G evolution and 6G powered by ION with you in your future. Hopefully face-to-face after the situation getting better soon. Thank you very much.
Okay, thanks a lot, Nakamura-san. In particular, it's very interesting to see your simulators and the demonstrations. Yes. So before we take a few questions from the board, I have one immediate question regarding the human augmentation demonstration. So in that demo, are both sensing and the communications are used, and then which frequency ranges is used in that demonstration?
Oh, thank you very much for your question. And yeah, actually, now still the preliminary trial phase, and actually we do not have any 6G trial systems. So in our demo, we are using the wired connection, actually.
Oh, okay, I
Yes,
see.
not the 60 radio.
Okay.
But for the future, of course, we want to use the 60 experimental system for demonstration.
Okay. Okay, cool. And let's take some questions from the Q&A, the bulletin board. So first question is, do you anticipate some role changes among industry players? For example, the operators, network equipment vendors, cloud providers, and so on, in 6G era, considering environment changes such as further the cloudification and so on.
Yeah, I think such kind of the movement is an ongoing topic. And the cloudification or cloud-based solution will be used even for the 5G era, this 2020s. And based on that, maybe 6G network will be developed, I think. And operator's role and the vendor's role, I'm not so sure that will be changed drastically. Okay. But actually, open up all-round discussion is very interesting, and many stakeholders have a strong interest in that. And we have already deployed open RAN-based interface solutions, and the Samsung are also very aggressive on that. And on that, the development of the network based on the all-round specification, that should be done not only by the vendors, but also the operators. Maybe all stakeholders need to be collaborate to develop the all-RAN-based network very efficiently and very quickly. So more tight collaboration will be needed, and that will be baseline for the 6G, I think.
Okay, yeah, it's interesting to see. Okay, then next question is, I think it's regarding the coverage issues. So the question is, 5G deployment suffers from coverage issues compared with LTE because of its higher the operating band, right? For example, this sub-6 gigahertz and the mmWave. And how about 6G? Because its frequency range is expected to be even higher than the 5G.
Yeah. That's kind of the issue and challenges, ongoing challenges, and especially mmWave that has not deployed so much all over the world. And but on the other hand, we have a variety of the potential technologies to deploy the mmWave more. For example, RIS is one of the very interesting topic, and we are also interested in the dielectric waveguide to be used, and also, of course, not the technologies, but the operations, how to operate our network, how to set the antennas to have a more line of sight condition environment between the users and the antennas. That need to be studied, and that will be deployed according to the study results, I think. And then maybe before the 6G, we can use the mmWave more widely and more often manner. And that kind of the experience and skills can be used for the 6G, especially for the sub-terahertz deployment. So that is currently my thinking.
Okay. All right. So another question is, actually, I observed that multiple companies are addressing or looking at so-called upper mid-band, FR3, according to the 3GPP terminology. So can I ask NTT DOCOMO's view, or in terms of opportunities or the challenges of that particular band for 6G?
Particular band?
7 to 24 gigahertz, right?
Yeah, at this moment, we study on we do not preclude any spectrum band. And technology point of view, we need to study the technologies and the solutions for assuming that any of the spectrum band can be used, including the sub-terahertz level. And not only for the sub-terahertz in 6G era, of course, we operator point of view, we want to improve the performance for the existing spectrum band, including the low band, mid band, and mmWave also. All bands need to be enhanced to be used. So that is very important. But of course, that it is a little bit tricky to have a very nice technologies which can improve the system performance for the existing band. But some kind of the technologies, such kind of the distributed MIMO, AI-based technologies, that can be improved the performance for the existing spectrum band. And also, of course, sub-terahertz level, we have many challenges in the sub-terahertz that have to be solved, and hopefully sub-terahertz can be deployed from the beginning of 6G.
Okay, thank you, Nakamura-san. So I think we can address one more question. So yeah, let me read one of the questions from the bulletin board. I think it's about the terahertz. So the question is, correct me if I'm wrong, but since 5G is stopped by things like trees, since the wavelength is short, then how will 6G avoid things like trees?
Yeah, that's true. That's true. Yeah. As I mentioned, that the one of the solution is the position of the antennas, of course. And if antenna for the mmWave set a little bit higher position, as you mentioned, that we have some problem by the tree, blockage by the tree. But if we can set the antennas lower position, maybe that easily we can solve the issues.
Okay.
So including such kind of the network operation solutions, maybe we can use the mmWave more. And also, of course, the RIS or many kinds of the solutions or technologies can solve the issues on that, and to have so that we can have a line of sight conditions more and more, so that we can deploy the mmWave more and with a higher performance, we believe.
All right, yeah, thank you very much, Nakamura-san, in particular for addressing the many questions. So, see you soon in the panel discussion.
Yep, see you
okay.
soon.
Thank you.
Thank you.
All right, now the last speaker of the morning session is Smee, Senior VP, Qualcomm Technologies. The title of the presentation is Driving Air Interface Innovation Toward 6G. So, hi, John. Please go ahead.
Hi, I'm Dr. John Smee, Senior Vice President of Engineering and Global Head of Wireless Research Technologies at Qualcomm. It's truly my honor and pleasure to participate in the Samsung 6G Forum here in 2022. I'm going to be talking about driving air interface innovations towards 6G. When we look at wireless communication, it's really important to understand the transformation of the industry, how we've gone from analog to digital, and also how the mobile form factor has changed into the amazing smartphones we have today in terms of the computing power in your pocket. And at the same time, with 5G, we are transforming industries to connect virtually everything around us. As we look at the world state right now in 5G, it truly is accelerating globally, with over 205 operators commercially investing in 5G, and additional 280 more investing further in 5G beyond those initial deployments. And 750 million smartphones or more are expected to ship in 2022, with over 1 billion 5G connections by 2023. And this transition is indeed 2 years faster than in 4G. Looking all the way between 20 and 2025, we expect over 5 billion smartphones. And currently, there's over 1,275 5G designs launched. So what's so exciting about 5G is this driving into new applications and new use cases. And so today in the Samsung 6G forum, we'll be talking about how technology is continuing to change to enable even further types of devices in the future. And what's always interesting to understand with technology, we can understand the devices we're holding in our hands. At the same time, the role of the cloud is incredibly important as we look at the transformation of the wireless industry. And in particular, if we look at scaling, the center of gravity of artificial intelligence is moving processing closer to the edge. At Qualcomm, we define this as the connected intelligent edge, where we're able to have on-device processing between artificial intelligence and communication. This can enable better privacy, enhanced reliability, and also low latency communications and applications. It truly is this connectivity convergence into this more intelligent edge, and that participation between the edge and the cloud is becoming increasingly important. As we look at the world ahead, what's important to understand is that as part of 5G, we've now recently completed release 17. In some sense, this was the first half of 5G, as we started from 5G release 15, taking us into 16 and 17. And now, in 2022, we're beginning with 5G advanced standardization. This release 18 5G advanced is setting the stage for releases 19 and 20 for the full decade of 5G evolution from 2020 to 2030. And at the same time, it's a great time to be talking now about 6G technology research, the vision for the world in terms of future applications in 2030 and beyond. So there's a huge amount of time ahead for 5G evolution into 5G advanced. At the same time, that foundational research is going to be enabling both 5G advanced and new approaches with 6G. If we look at 5G itself, it began in release 15, and it was designed to ensure it could scale to meet future applications. And because of this, it was designed on a flexible slot-based framework. And it was so important that it could serve both mmWave applications, 5G sub-6 applications, and taking in new technologies like massive MIMO, and then bringing that expansion from release 15 to set the stage in release 16. What's exciting about 5G is how it's transforming industries. Things like ultra-reliable, low-latency communication, that enables connected factories, and new ways of designing 5G sidelink for applications like connected vehicles with cellular V2X. So release 16 was the beginning of the expansion of 5G into new use cases. And that continued in release 17 as we further moved forward into technologies like non-terrestrial networks and taking 5G further forward into the IoT with reduced capabilities NR Lite. And so here we are just about to begin release 18, taking that further step forward with interesting new technologies like full duplex and machine learning in the air interface being topics of significant study in release 18. So it really is an exciting expansion of the 5G ecosystem as we're moving into this new era of 5G advanced. And in some sense, it's setting off a type of evolution, both strengthening the end-to-end 5G system foundation, as well as proliferating 5G into new devices and use cases. And so what's interesting is even technologies like MIMO that we've been working on for many years, there's still important advancements that can be made as part of release 18. Things like how we're looking at the uplink massive MIMO, or even how we're looking at changing topologies with mobile integrated access backhaul and repeaters, and further improving mobility and duplexing. So it really is exciting to see that continued strengthening of the 5G system foundation, leveraging techniques like artificial intelligence and machine learning and more efficient network energy savings. And at the same time, in addition to an improved 5G system, we're also updating the 5G use cases to ensure things like augmented and virtual reality have seamless user experience on 5G, or further evolving reduced capability into lower tier devices and more connected wearables, and continuing to take positioning and sidelink forward. So it really is an exciting time as we're continuing to drive 5G forward. But when we take a step back and imagine the world in 2030, it's really about understanding the changing physical world, the many different types of devices that we will have connected. And at the same time, the data from those devices is being digitized. So we can understand the digital twin of a smart factory. And at the same time, we can also understand the data sharing, whether it's a medical application, information being shared in a smart hospital, or the evolution of smart education. So all of this digital world data is also being exchanged over wireless. And at the same time, the form factor that is being used for new types of devices, it's enabling a further virtual world where augmented and virtual reality are changing the form factors we can use, leveraging new technologies like spatial computing. So this merging of the physical world, digital world, and virtual world really is opening up new opportunities. It can enable people to be more productive and better connected. And at the same time, it's about adding value to that connectivity as we're looking at the way that devices are exchanging information. If we then understand, well, what are some of these key research vectors enabling both 5G advanced, but also driving that path to 6G? Things like artificial and air interface machine learning. We're actually designing into the air interface itself new algorithms for machine learning. So not only will we have intelligent base stations and intelligent devices, but the air interface itself can also become AI native. The best approach is to be a more predictable model of the system. So we're able to use machine learning to transition into a data-driven design. At the same time, using spectrum more efficiently, sharing better in terms of different types of incumbents. And then also taking new radio designs forward into new frequency bands, whether it's sub-terahertz at 140 gigahertz, or looking broadly at the spectrum bands like sub-6 gigahertz and mmWave, and designing for a world in 2030 in terms of that technology capabilities. And it's also important to understand that network architecture continues to scale. So new types of disaggregated platforms, new ways of evolving the network architecture so it's more cost-effective to deploy and can better support new use cases. And it goes without saying that another very important vector is communications resiliency, ensuring that we're making multifaceted designs for trust and configurable approaches. So if we look truly at the decade ahead, we're driving these 6 key research vectors to make sure that the opportunity ahead is addressing a wide variety of future use cases. And in particular then, if we look at artificial intelligence and machine learning, it's about understanding the role of distributed cloud and disaggregated network, and how does that combine with edge devices? So we can look at then at the different sorts of implementations and the different sorts of standardization trade-offs. What's the best way to have intelligent spectrum utilization? Or even the difference interplay between the artificial intelligence on the device and the artificial intelligence at the edge of the network. So this AI ML powered end-to-end communication enables us to transition from more statistical models to more data-driven networks with a cloud to network device approach. Similarly, we continue to advance technologies related to MIMO, bands, for example, between 10 and 15 gigahertz. We can use technologies like GigaMIMO to have even more antenna elements, doing it in a way that we can get the coverage and capacity of lower spectrum bands, but bringing in new higher bandwidth capabilities. This can enable wide area cellular connectivity in bands, for example, between 10 and 15 gigahertz. And so there's important research areas like hybrid beamforming and even ways of doing better coverage enhancements and making sure this is enabling high capacity, wide area cellular networks. If we look forward to the evolution of duplexing, it's not only going to be about frequency division duplex and time division duplex, but also new hybrid approaches. The best way to, for example, support subband full duplex, where part of the spectrum is able to be transmitting and receiving in the same carrier at the same time. And this enables more dynamic TDD deployments and also new types of applications with lower latency. So this continued evolution of duplexing is an important area of advanced study. Similarly, the role of mmWave continues to expand. New enhancements focus on things like coverage and robustness, and at the same time continuing to ensure that device power and size constraints are becoming more and more effective. So there's a lot of innovation to enable these further applications and further device types. And that can be combined with intelligent beam management and new ways of deploying networks with more topology enhancements. So on the path from 5G to 6G, there's a huge amount of exciting research in mmWave to make sure that the new system innovations continue to provide that wide area performance and new types of designs. Similarly, when we look at 6G, there's always a question of waveform, coding, modulation. What's the best way to combine these ingredients? And so we can look at new types of channel models, new types of designs for coding, so that we can reach terabit per second communication. What's the best way to have that end-to-end link performance? We can also look at new designs for power amplifier efficiency and to have high spectrum utilization, and even designing new multiple access schemes. So whether it's for low power IoT or for high data rate connected factories, it's really important to understand then that these new foundational air interface designs always include a careful look at the best technologies across coding, modulation, and multiple access. And then when we look at waveform technologies and radio technologies, it's interesting to understand the ability to design systems to work across different frequency bands, whether it's terahertz communication, mmWave communication, or even including new types of reconfigurable intelligent surfaces, where we can have different types of MIMO, for example, even line of sight MIMO, and new advanced duplexing and spectrum and RAN sharing. So we combine this radio technologies on the radio side and the RF side with new types of network topologies, roles of mobility and mesh and D2D networking, or even cooperative device communications. So it's a very important area for 6G to be looking at these foundational core innovations in the RF domain. If we look at the 5G advanced evolution then, I mentioned several key research areas, whether we're pushing the system design performance with things like MIMO and mmWave, or even designing for more energy efficient green networks, and designing towards industrial networks and an AI-enabled air interface. So this 5G advanced evolution into 6G, on one hand, it's about taking a big picture view to make sure we're addressing the most important use cases. On the other hand, it's also about how we put the technologies together to drive particular values into new vertical industries. We want to give some examples of the evolution research. There's advanced MIMO research innovations that we recently demonstrated, as well as mobile mmWave and an AI-enabled air interface. And we combine that with research into green networks to have more energy efficient communications. What's interesting also, as we drive to the future, is the role of integrated communications, positioning, and sensing. And so we can have positioning evolution both in 5G advanced and at the same time design for new positioning algorithms into 6G. If we look at augmented and virtual reality, we absolutely expect that to be served well by 6G, and at the same time enabling these technologies in the 5G advanced evolution. Taking 5G into IoT is also a very important research area, enabling RedCap and the evolution of reduced capability technologies. So if we look broadly at the advancements into the overall network architecture to ensure a more capable 5G system, we combine that with new applications and use cases across a growing range of connected industries. As a good example of some of these advanced demonstrations, these videos here can be watched by different people offline to better understand some of the deep technical research that's enabling us to move forward on these particular research vectors. Then if we look at the path towards 6G, as I mentioned, it's important to understand that we've just finished release 17. And so that is now bringing us towards the 5G advanced evolution into releases 18, 19, and 20. At the same time, this is now leading us on the path to 6G for that next technology leap, new efficiencies taking us from 2030 into 2040. And this road to 6G truly is a global set of people working together. And for example, then at the Samsung 6G Forum, it's so exciting to see other industry participants and academic participants as we look longer term, new spectrum bands, new ways of doing deployment, and then also new capabilities, and taking all of the lessons learned from 5G technology and bringing that into new market opportunities. So as we look at the broader wireless ecosystem, whether it's the cloud or the edge cloud or on-device intelligence, they can all work together to open up a new world of 6G possibilities. And that's why sharing innovative long-term research technology is an important way for people to understand the different trade-offs. What technologies need further investment? Which ones are going to be ready for commercialization in 2030? And how can we best put technologies together to make sure that we're also connecting the unconnected, to bridge the digital divide with new types of capabilities, best leveraging the technologies to bring more use cases in a cost-effective way. And that's about working across spectrum bands, the low bands, the mid bands, and the higher bands. And then also working across use cases, from communications to new applications where communications and sensing start merging into new applications, leveraging, for example, positioning, whether in a smart hospital, a smart factory, or for augmented and virtual reality. And then this broad 6G vision and all this research, bring that into the standardization in 3GPP, enables a global ecosystem and the full scale of investment and new opportunities. So thank you very much for this opportunity to address the Samsung 6G Forum, and I very much look forward to participating in the follow-on discussions. Thank you.
Oh, yeah. Thank you very much, John. It's very good to see the Qualcomm's view on air interface innovation toward 6G.
Yes, thank you very much, Eddie.
Yeah, by the way, it looks like the same location, the same closest, no change.
Almost, very close.
Okay. All right, so let me take a few questions from the board. The first question is, what will be the role of upper mid-band or FR3, according to 3GPP terminology, in 6G? So what opportunities and challenges are you envisioning, in particular for GigaMIMO in your, on the slides?
Yeah, that's a very good question. And I think it's an interesting band because one of the challenges is to find clean new spectrum for the new generation that can also have broader, longer propagation. And so we're looking at, just like in 5G when we were designing for bands from 3 gigahertz to 6 or 7 gigahertz, designing this FR3 upper mid-band spectrum, it's about saying how can we leverage the same footprint of a macro cell and then move all the way into these bands around 10 gigahertz or higher. So some of the interesting system challenges then are on how do we design the device side antennas and filters and amplifiers, the kind of end-to-end RF design. And then also on the infrastructure side, ensuring we have sufficient beamforming, given that the propagation is going to be at that higher frequency. So in my view, a lot of the challenges are going to be more on the RF power consumption standpoint, and then how do we best do hybrid beamforming. We can't obviously do everything in digital because at GigaMIMO, the number of elements is going to get so large. I think one way I like to look at it is if you look at a band around 3 gigahertz versus a band around 12 gigahertz, then the spectrum is 4 times higher. And so that means basically that the number of antenna elements can be 16 times higher because you're literally working in a 4x4 increase.
Right.
And so if we look at that area growth in terms of having more elements in the same aperture, then there's a lot of interesting engineering challenges to make sure that we're able to best use this higher band. And I also do think on the device mobility standpoint, it will be an interesting set of algorithms that are looking at, you know, the designs from the lower bands and the designs from FR2 mmWave and bringing the best two together in terms of making sure to have robust performance.
Right, yeah, very good. Thank you, John. By the way, my camera is here, but the screen is on this side, so it's a bit confusing. It's okay. The next question I have for you is, can you elaborate a bit more on the merging worlds on slide 3? What kind of technologies are needed and or enhanced in 6G to support metaverse?
Yeah, so when we looked at merging of the worlds, what's interesting, as I described in my talk, that the number of devices is going to be larger in the physical world. And then the data is being both digitized and virtualized into new, basically user devices from a human compute standpoint. So I think what's interesting when we project and design 6G, then we want to ensure that the air interface that we come up with in the first release of 6G is something that can evolve all the way from 2030 to 2040. And so that's obviously a long time away from now. So if we want to make sure that the design of 6G can handle, you know, future connected hospitals or connected classrooms or connected, you know, virtual reality experiences, then we have to really take a careful look at that end-to-end latency that is at the, you know, if we look at control plane or we look at the user plane or we look at mobility. And so I think we'll be able to design 6G to have adequate bandwidth, but I think the interesting challenges will be getting that end-to-end latency so that we can really have that more immersive physical experience. And I think that's where even now in 5G Advanced, as we look at release 18 and beyond, there's going to be additional, you know, work on augmented reality in release 18 and beyond, looking at certain aspects. And so then as we design 6G, the important components that need to come together is that end-to-end view and the role, for example, of the edge cloud and the on-device computing and how that workload is going to move around based on distributed compute. So I think that's kind of a core theme entering the 6G era, is that the computing is not just going to be on one device, it's how we also look at some of these split processing or some of these scenarios where the distributed compute can move to different processing energies. And that's why at Qualcomm, when we talk of the connected intelligent edge, I think a lot of the interesting use cases involve that data moving around in terms of where it's generated, how is it shared. So if we look at uplink and downlink, then one could understand that the uplink needs for 6G are going to be very significant because there's going to be a lot of user-generated spatial knowledge. And it's not just going to be people watching broadcast video on the downlink. So I do think as we talk in most generations on what are some of the primary use cases and their traffic needs across the network and the device, that something like the metaverse will force us to challenge how we're looking at that uplink, downlink partitioning for TDD spectrum, how we're looking at the role of full duplex for low latency, how we're looking at mobility management.
Okay, yeah, thank you very much, John, again. So we'll see you again in the panel session. So,
Sounds good.
Yeah, thank you. So now let's take a 10-minute break. After the break, there will be a panel session to discuss 6G RAN technology, right? All right. It's time for panel discussion on 6G RAN technology with the 4 speakers from earlier. So let me introduce the moderator of this panel discussion. Here is Julie, a fellow of Samsung Research. So let me hand over to you. Thank you.
Hello, my name is Chu-Ho Lee, working for Samsung Research. I will moderate the morning panel session about 6G RAN technology. We heard very insightful talks from 4 distinguished speakers this morning. So let me introduce them once again. So I guess everyone has to be available now. So hi, Jeff, Charlie, Nakamura-san, and John. I hope you are there. So we have Professor Jeffrey Andrew from University of Texas, Austin. Jeff, can you say hello to everybody? Okay, I can see you. All right, then we have Charlie Zhang from Samsung Research America. And we have Nakamura-san from Untitled DOCOMO. And we have John Smee from Qualcomm. All of them are my old friends. We have been working together a very long time already. And they are very well-known experts for research on 6G technologies. Okay. So let's start our panel discussion. So before starting discussion with our distinguished panelists, let me provide some general overview to postulate discussion today. Since 2000, the 5G system has been deployed since 2020. And since the first deployment of 5G NR system, industry has been working on further enhancement of 5G advanced standards. For example, 3PP is now working on the second package of 5G NR, which is called 5G Advanced. And at the same time, outside standard bodies, there is already research activity to study new and fundamental technologies for next generation, meaning 6G. So going forward, it is natural expectation that the 5G advanced technologies and also outcome from the research outside standard, both of them will be used to define technologies for 6G. Regarding the timing when the 6G will be deployed, there's no officially agreed time plan yet. Nevertheless, from the experiences so far, we naturally expect that 6G will be deployed around 2030 timeframe. So what technologies do we expect for 6G interface? Of course, spectrum is the most important aspect. Without spectrum, it is very difficult to deploy a new generation system. And we have been working on MIMO, duplex, waveform coding and modulation, and topology. All those technologies are basic technologies to define radio interface, air interface. And we expect a big leap moving towards 6G on those technology aspects. So on top of those rather traditional technologies, we have been working a long time already. We expect a new player, new technical component will come in to define 6 technologies, which is AI/ML. I appreciate all these insightful talks from Jeff, especially this morning. He provided very good insight on how to utilize AI/ML, and also, of course, other speakers also talked about AI/ML a lot. So it is very obvious that AI/ML will play an important role in 6G. And another thing is joint communications and sensing. Naturally, the communications technology will evolve. Then there's also increasing demand to have better sensing, for example, environmental awareness, etc. So then there's a big effort to somehow combine communication and sensing. so that we can do some joint operation. Then there can be new technologies that are not known yet. Of course, I mean, so I have just 3 dots there. So I'll be very happy to see new technologies that I currently don't know yet in the coming future. For example, 1 year, 2 years later, or 5 years later. I mean, having new technologies which we don't know yet will be very important to have true innovation for 6G. So I have looked at the question board and taking into account all the questions raised before today, I made a list of 7 discussion topics, and I can go through one by one. So the first topic, 5G versus 6G. Yeah, this is very somehow kind of popular question. So many people are using 5G, and people are saying that they are already very happy with the 4G. So there are questions, what do they do with the 5G? But then we are talking about 6G. Then it is a natural question, what additional benefit would 6G create compared to 5G? So I took this as the first question. And since this is related to kind of customer adoption, I think Nakamura-san has the best position to think about this question. So Nakamura-san, can you please try to address this topic first as an operator?
Okay, yeah, thank you very much, Yuho. Yeah, I think that many of the characteristics of the 5G need to be improved for the 6G, such as the high data rate, high capacity, lower latency, higher reliability, and so on. So those are the not so new topic, but we need to improve continuously for those kind of topics. On the other hand, new topic, one of the new topics should be from our point of view, we really want to extend the coverage drastically. Yeah, and so far we deployed our service area. It's mainly for the areas where the people live or people are working or something. But for the future, the IoT device will be everywhere. If so, we need to provide a service area not only for the urban area or areas where the people live, but also the mountainside. It means that we need to achieve the 100% geographical coverage need to be achieved. And not only on the land, but also on the sea, and the sky is also very important. Now, the drone is now used for the variety of the services already. And also, maybe everybody traveling a lot. Recently, due to the COVID-19, we could not travel, but potentially we travel a lot. Actually, I travel. I'm in US now, actually. And airplane communication conditions, environment need to be improved. I really hope so. So sky coverage area is also very important. In that sense, we really need to extend the coverage, 100% geographical area on the land, sea, and sky. And the 2030s, maybe we need to consider the coverage extension to the space, I think. So we need to consider that. So that could be the new topics in the 6C, for the 6C. And also, yeah, and sustainability. That is one of the most important topics, even for now. And maybe as for the 6C, that is essential topic need to be considered. And yeah, actually, sustainability, especially for the lower power consumption, studied and discussed even for the 3G, 4G, and 5G. But main focus was not the power consumption, but the higher data rate and the lower latency and so on. But 6G, lower power consumption. That's a very, very important topic for the sustainability toward the 6G. That is my thinking. Thank you.
Thank you, Nakamura-san. So I understand you are emphasizing to address some aspects that are not fully addressed in mobile communication so far, something like coverage or energy consumption aspect. Of course, we have to continue to improve the typical performance aspects like data rate and latency, but I think you made a very good point so that we can kind of enlarge the kind of service coverage of the mobile communication system to provide 100% coverage and to contribute to sustainable world. Yeah, so then, okay, that's from our perspective. Then naturally, we have to sell our technologies to customers, end users. Then, Jeff, maybe, of course, you are a researcher, you are leading research, but at the same time, I think you are at the position of customer buying products from us. So maybe, Jeff, maybe you can add some remarks from customer perspective or subscriber perspective, whatever.
Yeah, I think, even though I'm an academic, I think when we think about 6G and we think about designing a system for it, we have to think about what the use cases are to design the right system. From my point of view, my main use case is currently, and for the foreseeable future, is as a smartphone user, and I use a lot of data like most people and more every year. But I think 5G can probably handle that use case for quite a while, especially as mmWave works better and is more densely deployed. But so I think when we think about the 6G applications that are ultra high data rate, we think about 6G applications like Nakamura-san mentioned, IoT. I think very exciting to imagine huge growth there, and I agree that will require wide array coverage, and that's a very different design problem with different fundamentals than the urban smartphone type problem, covering space, covering the ocean. These are very different problems, and then of course if you want to add energy conservation, sustainability to it, these are very different things actually. So I think we have to we'll have to set some priorities for 6G. And I do see one key aspect of 6G is, that it'll probably be a few systems within a system, with perhaps different modes of operation. And 5G has this already to some extent, but I see 6G is going much further and really having orthogonal modes of operation that, that you'll generally try to run in the lowest power mode possible. And then for wider coverage, you'll have to go to narrow band and so on. And for holographic video and XR, it'll be wide band, dense deployment. So I think Gerhard Fettweis has talked a bit about this gearbox idea, and I agree kind of with his premise that we need to think about the 6G car as having different gears, not just different speeds, like different accelerations like we do in 5G. Actually, whole different PHY designs, with the premise being that you use a very low energy PHY. So I think that's maybe something interesting to think about for 6G.
Thank you. All right, then, okay, during this conversation about additional benefit from 6G compared to 5G, now we can pick up an important keyword, which is application, kill application. So we can move on to next topic naturally. So next question is kill applications of 6G. Yes, we talked about additional benefit from 6G, but then what would be kill applications of 6G? That's also an important question. And during the talks in the morning, some examples were mentioned. For example, mobile hologram, extended reality, and digital twin replica. So once again, Nakamura-san, can you provide your views on this kill application for 6G?
Yeah. My honest opinion, I'm a little bit reluctant to discuss on the killer application discussion. Anytime, any new generation system discussion, we discussed on the killer, what is the killer application, but the discussion results was not so appropriate. Yeah, 3G case, the typical case is, 3G TV phone could be the killer application, but no one used it at the time. So, but on the other hand, for the 6G killer application, we really want to create very new potential services. So that one of that should be the as I explained in my presentation, human augmentation, like a topic, is a very interesting topic as a new killer application. And we really want to realize the science fiction like use cases thanks to the 6G high performance network. And if so, we can realize the telepathy, telekinesis, such kind of services can be realized, so that we can use that kind of the new services for the as a solution of the social issues. In Japan, we have a variety of the social issues, such as the aging population, lack of the human resources, and so on. So maybe we can create the new services to solve those kind of the social issues for the future. Yeah.
Thank you. Then let me take one more view, perhaps from John. I know Qualcomm has been promoting many new services using technology, so maybe John, you can take some aspects.
Yeah. The way I look at it is we have to look, at the world in 2030. So as we're looking at services in that point, I think it's important to think a little bit about enterprise, right? So there's the consumer applications, there's enterprise applications, and similar as Nakamura was mentioning about human augmentation, I think we have to really understand that the computing requirements, not only for people using augmented virtual reality applications, but also the fact that there's going to be additional computing, even because of on-device artificial intelligence. So I do see a world where there's going to be more distributed computing, and some of that's going to directly relate to a human device, that is, whether it's an augmented virtual reality headset or a smartphone, evolved into the 2030 era. But at the same time, I do think that the digital equipment is also in and of itself going to be providing a lot of traffic needs. So the connectivity needs for the 6G network are not really just about people and our kind of limited requirements for two-dimensional video watching, but it's also going to be huge volumes of data being exchanged. And so that digital twin part, the amount of information exchanged at the edge of the network, I think it's going to be much larger than we might predict at this point if we were trying to extrapolate that, with any sort of linear function. I think it really is going to be a much larger growth in terms of the amount of information to truly have a more accurate view of the sensing, the RF environment, the entire physical environment. So I think it's something where, whether you're talking metaverse or whether you're talking digital twin or whether you're talking enterprise, I think that's also going to put a lot of needs on the future of cellular connectivity into that 6G era, 2030 and beyond.
All right, thank you. Yeah, so discussion about killer applications is always kind of difficult. So whatever we say, it may turn out that very small portion of all those visions may be realized. But anyway, I think we will continue to try to define new killer applications. Okay, then next topic is a relationship between 5G advanced and 6G. Right, so 3GPP as a standardization body is continuing to enhance 5G standard, and they just have started to work on 5G advanced standards. And it is expected that the first version of 5G advanced standard will be released, I think, end of 2023. And at the same time, then we are going to start discussion about 6G around 2025 timeframe. So how do we define the relationship between 5G advanced and 6G? So let's take a view from Charlie.
Okay, thank you, Juho. So thinking about the 6G and also this 5G advance is also taking place today, right? So kind of reminds me this analogy between what's happening 10 years ago when we started to look at the 5G, while in the meantime we were working on LTE advanced, very similar situations. So looking back, probably we can learn a couple of lessons from that, right? So if I look at what's happened back then, right, there's definitely, this technology that's more of a jump, going into new spectrums such as mmWave to enable all these new exciting services and so on. But there's also technology that kind of started a little bit earlier, even during LTE advance. already have an impact for 4G LTE, but continue to be optimized. It becomes really important in 5G. For example, FD MIMO, for example, the support for this reduced capability IoT devices, D2D, all these things kind of started during LTE advance, then moved on to 5G. I mean, then thinking about where we are today, situation I think is going to be very similar. We're looking at a few directions and technologies, for example, sub-terahertz, totally new spectrum, new opportunities, and requires a totally different type of thinking, looking into all these technologies, including RF, including system side, to be developed maybe in 6G, because we're not looking at that in 5G yet. So that, but then there will also be continuation of technology that we already started looking into during 5G advanced. For example, the AI machine learning that we all talked about a little bit earlier. And there's also this duplexing technology, for example, that just started in release 18. There's also this smart repeater, activity that's happening in 5G advanced. I think naturally it will progress and evolve into more interesting discussion about topology evolution going forward in 6G. So it's really a combination of these new jump technology versus a continuation of some of the technology that's already started, but then will become better during 6G.
Thank you. Yeah, right. So as one of the companies who are leading the technology innovation in 3GPP standard, maybe John, you may also add on some additional aspects.
Yeah, I think Charlie had some very good points, and just maybe to add a little bit additional ones, I think it's about like how things get combined, right? So to make it foundationally different. So we talk of AI in 5G advanced, whereas I think how we apply things will have more time from the standardization standpoint to basically take a broader step in 6G, a bigger step. So we might incorporate 6G more foundationally in terms of the AI role on the air interface itself, in terms of the kind of overall approach to the neural network models, or even technologies where we're thinking they're kind of moving along now, like as we're looking at evolving security, we're looking at high reliability, low latency communication. I think in the 6G era, we'll have the chance to design a different approach on the cloud side, on the core network side, and then on the RAN side. And so then how we look at the RAN and core splits, I think we'll be able to design an overall new approach to some of these layering approaches and more of a service-based architecture. And that brings in alternate approaches of doing security based on the need, for example, if we look at a 6G network and the late 2030s into 2040, we'll want to be hardened against, for example, post-quantum era aspects. So I think it's a lot of projecting forward and then bringing that back. Whereas 5G advanced, obviously, we're evolving from that release 16, 17 basis point.
Okay, thank you. So we discussed about the relationship between 5G advanced and 6G. Then naturally, we need to think about what kind of performance requirements we have to define for 6G to distinguish 6G from 5G. So we can move on to the next topic, which is related to performance requirements for 6G radio technologies. So if I recall what happened in the past, we have increased the number of performance parameters across multiple generations. For example, the number of performance indices in 5G actually was much more than what we had in 4G. So then there can be naturally question, what parameters do you want to use to define performance requirements for 6G radio, and what kind of initial expectations we have for defining performance requirements. On this, maybe we can take a little bit of fresher view from academia side. So, Jeff, can you be the first person to address this?
Yeah, and I mean, this goes back to my question as to what use cases we wanted to really focus on, right? My own sense is that we should de-emphasize peak rate in 6G. relative to each G, we really focus on the peak rate. Marketing people love the peak rate number, but is that really what we need to do in 6G, or do we need to figure out how to extend coverage, make it really reliable, lower the latency, enable new applications, and lower the energy? I mean, I think that would be more my point of view. And just like going back to the last question, I have some opinions on that too. But I guess a question I have is, will 6G even need to break backwards compatibility with 5G? Certainly 10 years ago, everyone was expecting 5G would be a radical break from LTE. People were talking about totally new waveforms, all this stuff. And at the end of the day, industry decided that they really liked the LTE physical layer, and they carried most of it over to 5G with some enhancements and making it more flexible and so on. So I mean, I think it's an open question moving to 6G. How much will even really change the physical layer, which then raises the question how much you can really radically change the performance metrics without densifying, adding more bandwidth, or adding just a lot more antennas. I mean, you need to do things in the Shannon formula that are before the logarithmic function to really move the needle. And so that's the menu: densifying, more antennas, more bandwidth.
Okay, thank you. I think, your comment about the kind of backward compatibility to 5G, of course, certainly a topic that we have to carefully think about when you define 6G. And so performance requirements like peak rate, yes, how important it is, that's an important question. So do you want to emphasize it quite much, or do you want to emphasize some other aspects more than peak rate? Yeah, that's a very important question. So then maybe we can take a view from, Charlie. You are the second position from the top, so it's a random choice.
Yeah, no problem. I think Jeff raised very good points. So definitely we should take a broader view, look into different aspects, not only limited by peak rate, latency, and so on. We have to look at capacity, coverage, and all these necessary components to make the system really work. And one thing that I think is really important to understand is, and we are seeing these new use cases such as digital twin and hologram that Juho, you mentioned earlier, right? I think one very unique thing about these new use cases that we are seeing today is, compared to the past, right? When we talk about peak rate and we talk about latency requirements, we don't necessarily expect these two numbers to be achieved at the same time. That's going to change when we go to 6G. When we think about digital twin, we think about hologram, because you're thinking about interaction aspects. You have to get the data, vast amount of throughput over there, but also in a very short amount of time to make this really seamless experience. That's really, I think it's a very important thing. It really sets it apart from what we are seeing today, typically in 5G.
Yeah, so I think you are emphasizing the importance of thinking the relationship between different parameters. So perhaps we can focus on some aspects for certain part of applications, and we can focus on the other aspects for the other applications. Yeah, that's certainly the topic we need to think more. Okay, then let's move on to the next topic. So which is the spectrum. Spectrum is, of course, the most important asset for new generation communication system. So my question is, what spectrums do you aim to use for deploying 6G systems around 2030? I guess you don't want to use the spectrum that is being occupied by 5G to deploy 6G systems already in 2030, because anyway, 5G and 6G would coexist for a while. So, Nakamura-san, can you please provide your view from upward perspectives? What spectrum do you think is most important for 6G in 2030 timeframe?
Yeah, operator point of view, any spectrum band, welcome, actually. Yeah, but of course, it is better to use the lower spectrum band, of course, thanks to the lower propagation loss. But everybody knows that there is no space in the lower spectrum band. And in any case, we need to explore the higher spectrum band. like the higher mmWave or sub-terahertz level in any case. But as everybody discussed, mid-higher bands, like they are 15 gigahertz or 24 or such kind of bands are of course very interesting. Actually, we conducted the trials in the 5G study era, and I remember that the 15 gigahertz was so nice, actually. So it is very good if we can use the 15 gigahertz or such kind of the bands spectrum can be used for the future. Yes, but anyway, it is very important to conduct the trials and verify the performance with those kind of the potential new spectrum bands, so that we can negotiate with the regulators that this band is very useful and we can achieve the very high performance, so that the regulators can consider the potential allocations of the new spectrum band for the mobile communication system. So that kind of activities need to be done together all over the world, of course. So yeah, I really want to collaborate with all of you to have such kind of the movement to allocate the new spectrum band. Yeah.
Okay, thank you. So, John, can you please add additional aspect?
Yeah, I absolutely agree with Nakamura-san that we're going to want to do our best to make sure we identify new spectrum. And so whether it's upper mid-band or even how we look at additional mmWave frequencies and even higher frequency bands. And kind of going back to some of the important points that Jeff was making on densification, I think we also have to be aware that as we're looking at RF sensing and better understanding of physical environment, then the higher frequency bands will also, in addition to communication and Charlie's point on very, very high data rate communication and low latency at the same time, we're also going to want to leverage some of these higher bands to do particular sensing applications. And so that allows that visualization or that spatial knowledge of the field. And so I would argue that in addition to identifying these new frequency bands, that we will also look at some of that 5G, 6G coexistence in existing bands. So kind of taking a brand new approach to how we look at dynamic spectrum sharing, but taking advantage of how the 5G system itself is quite forward compatible. So to Jeff's point on the time frequency slicing and some of the 4G, 5G OFDM, channelization similarities, some of the other differences that are true with 5G is that it's a lighter, leaner design in terms of occupancy in the time frequency grid. And there's technologies like, if we look at being able to have a smaller, resource allocation in terms of some of that subband technology. So I'm confident also that we'll be able to kind of bring in some new 6G approaches even into 5G spectrum. And then we start talking about, okay, is it truly backwards compatible? Is it brand new? Is it not backwards compatible? I think that we'll be able to design a new system that would not be backwards compatible, but it would be spectrum compatible with some of that existing 5G deployments. And that even the 5G flexibility itself will be able to bring in some of that 6G performance and kind of have a smooth migration with different percentages of 5G as 6G continues to grow, so that as time moves on, there becomes more and more 6G utilization of the spectrum. So I think it's an interesting thing where over time, by necessity, we're going to need to refarm. And in 6G, I think we're going to be able to bring in soft refarming of how we move that spectrum assets forward into some of these new kind of deployment models that will come with 6G.
Thank you. Okay, Charlie, do you want to add some more?
I think John and Nakamura-san really addressed very well. To me, it's very simple. We're going to try to use everything between 0 to 300 gigahertz that's available to us. So that's a short answer, right? So of course, some of them will be existing band where we try to make better use of them through refarming, through better optimization. But definitely we need to look into some of the new opportunities such as upper mid-band as well as sub-terahertz band.
Right. So I think on this spectrum aspect, most industry players would have similar views that, okay, we want to have new spectrum, not only in very high frequency band, but also in the low frequency band. And actually low frequency band would be quite useful to provide bigger coverage in terms of, because of these propagation characteristics. So I'm sure all of us can work together to secure enough spectrum for 6G. Okay, then let's move on to the next topic, which is radio technologies for 6G. I remember quite a long time ago, maybe not so long, maybe within 10 years, there was a very famous paper saying the physical layer is dead. This may not be exact title, but basically the message was the physical layer was dead. That was a very famous kind of magazine paper. Of course, there has been quite enormous evolution of radio technologies in 3G, 4G, and 5G. So then what to expect as the major evolution of radio technologies for 6G? It will be quite important questions to researchers working in industry as well as in academia. So let's take views from our panelists. Maybe Jeff, you can start.
Yeah, first of all, I was involved with that brainstorming on that paper, so I want to defend my co-author. Well, I wasn't an author, but Robert and Angel and Ronaldo. Only a couple of those guys thought that the phi layer was dead. Most of them did not. The question was asked in the paper, though, which everyone remembers. And of course, it turned out that the phi layer was most definitely not dead. So, moving into 6G, yeah, I think, your intro slide, Juho, laid out a lot of the things that we're looking at. I think the prospect of going to full duplex is, I'm hearing a lot of that from various top companies. John, Charlie both mentioned those that technology. I have, a PhD student who's done awesome work on enabling full duplex for mmWave. So he's been working on it for 4 years, and it's really exciting to see that the industry's also really interested in this, because we think it has benefits well beyond the physical layer, but at the higher layers, particularly in multi-hop networks like IAB, it can really help bring the latency down pretty radically, especially the worst case latency, is what a recent paper of ours has shown. That's just one thing. I think the machine layer piece is machine learning piece is a really big X factor. You do have the potential to learn whole new paradigms for communicating that right now humans have not invented. If you throw enough data at it and train away. We've already seen some new codes come out of my colleagues, Heji Kim's work at UT, that generally codes are invented by extremely smart human beings who've studied it for 10 plus years. And we have the possibility to learn new code through a systematic approach using deep learning and for very hard situations. That's very interesting to me as a possible new paradigm for 6G. So yeah, I'll just leave it there. I think, on the spectrum thing, I think I'm curious to hear from John how Qualcomm's going to fit these 79 different radios, all these different bands from 0 to 300 gigahertz into the phone. But yeah, I think there's lots of room for innovation in the 6G interface, and for me, it's really exciting.
Very nice, thank you. Then let's take a view from Nakamura-san.
Yeah, technology is that actually. Unfortunately, we could not identify the very brand new, excellent technologies towards 6G. Yeah, even from the 5G. Yeah, OFDM-based, MIMO-based, similar technologies are deployed. But the further enhancement was used. Enhancement was done. And also many kinds of the small technologies are integrated and combined, and then we could achieve the very high performance in the 4G and the 5G. Maybe that kind of situation will be continued for the 6G. Yeah, but of course, it is very good if we can identify the very new high performance technologies towards 6G. I believe that Samsung, Zhang, Charlie, you can do that. Of course, yeah. And also, I want to say that, actually, wireless technologies are improved so much, 3G, 4G, and 5G, maybe 6G. And spectrum band resources are expanded. So radio performance rate was so improved. On the other hand, the wireline network side, actually improved, but some case in order to have a high performance, end-to-end high performance, network side, wireline side can be the bottleneck some case. So it is important to study not only the wireless technology, but also the network side. Network architecture needs to be considered. And then we need to achieve the end-to-end high performance services, network functionalities can be achieved. In that sense, we are aggressive for the so-called ION, innovative optical and wireless network. And optical technologies also need to be considered, and some kind of integration with the wireless and optical. And also some kind of the computing resources, computing platform need to be improved. Everything need to be improved. So I hope that everybody address such kind of end-to-end high-performance network architecture functionalities need to be studied, and so that we can achieve a very high end-to-end performance.
Okay, so it was very nice to hear from Jeff that physical layer is not that. That was very good. And I think it is also very valuable comment from Nakamura-san that we have to consider overall end-to-end performance. So not only wireless, but also the network aspects, so computing aspects also have to be considered. That's very good. So Charlie, I guess you don't need to respond to Nakamura-san immediately, but I think you got a homework from Nakamura-san to provide technical advancements. And of course, and I'm sure the Zhang will also, Qualcomm will also continue their effort to provide true innovation towards 6G. So I got informed that we only have 8 minutes left. I thought I have about 12 minutes, but yeah. So in the interest of time, I think we have to move on to the next topic. Yeah. So AI/ML for air interface. Yeah, this is really hot topic. And myself has been discussing a lot with my colleagues about how to use AI/ML, but then I realized that it is really difficult to get meaningful outcome from the study on AI/ML, especially taking into account both AI/ML and radio, and how to have the best kind of combination of those technologies. And yes, Jeff provided very good insight today, and I appreciate that. I'm sure all researchers who saw Jeff's talk presentation will have good insight from that. So then, come back to the fundamentals. So what is the expected benefit of applying AI/ML to radio? So naturally, we can ask, in theory, there's performance bound, and we are already approaching to those performance bounds. Then what additional benefit we can achieve from AI/ML? That can be a natural question. And in terms of the standard, so what has to be supported in the standard to use AI/ML for air interface? I picked up these two questions. So for the first question, maybe Jeff, you are the best position to answer.
Well, I'll try to give an answer. I mean, it is still an evolving topic. I mean, I think if we look at just a point-to-point link, AI/ML is going to provide limited gains. It can help with some of these nonlinearities I spoke about. We've seen that already, some research that shows gains there. But I think I see it really as powerful for cases that, you know, the theoretical or traditional solutions don't work well. You know, I talked about beam alignment. Beam alignment is a hard problem. I mean, you want to imagine an intelligent network. What's more intelligent than, you know, thousands of base stations in Seoul, you know, linking up with directional beams following users as they move around, you know, 1 million users, you know, probably simultaneously in Seoul, you know, tracking them, turning them on and off, you know, allocating which bands to use for these different users. So there's a great deal of intelligence in the network that can provide, I think, big gains both on capacity and on power savings from applying these ML techniques. So I think at a system level, we'll see, we can see perhaps very significant gains along some of the KPIs that you care about. I think on the link level, you know, we should have more modest expectations of what can be accomplished. I mentioned a few things earlier, like possibly new codes, I think the beam alignment one is a big one, channel estimation, channel feedback. But again, I don't think the gains are going to be, in most cases, huge. They could be substantial and worth doing. But I think at the system level, as the network becomes more and more complicated, we add all these new bands. This is where I think ML can really shine, because there's just gazillions of parameters to configure, you know, and complexity, and it can hopefully help manage that some of that for us in a smart way, and learn from its mistakes, learn from, you know, by continuous online learning can improve systematically.
Okay, thank you. By the way, I got a good news. Actually, we have about now 14 minutes left, so that's good. Okay, then let's take a view about this potential benefit, or another view about the potential benefit, maybe from Charlie.
Yeah, sure. So, I mean, as Jeff said, right, looking at a single link, still might be some opportunities, but could be limited to some extent. But then you probably have to think outside of this box and look at this overall problem and really think, what is the intuition? Where do we see that this introduction of new tool of AI ML can be helpful, right? So one area we do see some beneficial aspect is when you think about AI can bring more global sort of understanding of the network together. What I meant is, for example, today in the network, right? So base station side does a lot of scheduling and radio resource assignment and so on, but base station has pretty limited understanding of the radio environment each and individual user is in, because the information that's being fed back to the base station was somewhat limited, right? For a good reason, because the uplink channel is pretty expensive. The UE terminal power is very expensive to do that as well. So if, you know, going forward, if we have a tool such as AI, is much more efficient in, you know, compressing those information, and if you can have agents sitting on both sides of the communication link, you can imagine that these two agents can jointly optimize, jointly learn this overall radio situation, and together trying to improve the performance. I mean, that could be one good example of thinking about where to look for opportunities of using some of the AI machine learning tools. I mean, another good place is, you know, think about where you have to design across the boundaries of different functions and different layers. Which traditionally for example, communication engineers are very good at putting things in one box, you know, put them in different layers, and also for good reason, because then we can manage the complexity and optimize, right? Because we didn't have a tool such as AI in the past, but now we do, right? And it's naturally very good at doing joint optimization. For example, you can now thinking about how to design the overall transmitter strategy across both physical layer as well as RF layer, to deal with that nonlinearity, for example. So that's where we see the opportunities are. Thank you.
All right, so we got few keywords. So of course, AI/ML can provide benefit for point-to-point operation. Of course, its benefit may be limited, but we have some evidences already. But then we expect that from system perspectives, AI/ML can provide benefits. Then overall integration of different operations so that we can remove boundaries. Yeah. All those are good observations. Thank you very much. Then maybe I can move on to the second question, which is about what has to be supported in the standard. And Qualcomm has been working very hard in 3PP to drive the effort for support of AIML, or maybe I need to say potential support of AIML in standard, because we don't know yet what has to be specified in standard. So maybe John, you could add some views on that question.
Absolutely, and it is something that there's that question, right? Because there's no doubt that AIML is already being implemented in products and implemented on the network side. And to these comments on the link side relative to the network side, I also agree there's that perspective that as we're starting to modify the air interface itself, it's about, how would we replace certain algorithms? So if we look at things like channel state feedback, or we look at kind of this end-to-end aspect. I think one other thing we didn't cover yet was this perspective that for AIML, we also want to ensure not only the ability to be a little bit more predictive on the physical layer propagation elements, relating to these beam management and, make sure we're matching the true physical channel, but we also want to understand if there's any contextual information in terms of an application that's running. So longer term, I think AIML is also going to be something that's involved in that predictability of how a service is evolving and matching that to the link as well as the network in terms of the mobility. But to your question, Juho, on the standard itself, I think that's when, as we're looking in leading this charge in release 18, the study item, and then bringing that forward into release 19 and beyond, there is then this perspective of, even if we look at the neural network models, what are the assumptions that the device side and the network side are making about the other side? And what do we need to exchange in a cross-node machine learning context, such that the training is not just the device doing everything or the network doing everything. So a lot of times when we do optimization, the question is, can you separate it serially across two nodes? And I think machine learning is like that as well. The device is going to know more information about its physical environment. The network's going to know obviously more information about its macro environment. But then at the same time, the air interface that is trying to drive to some of these KPI improvements is going to want to leverage the fact that ML is occurring on both sides. And so at that point, how you partition that solution space is a very interesting one. And it's one of the reasons that kind of our work in this area is trying to make sure that this cross-node aspect is done well.
Right, I think that's a very important point. So, we have two nodes, base station and terminal, then we want to make sure that both nodes are working together to maximize overall performance. Then in that regard, we may need to have some supporting standard for better operation by AIML. Yeah, I think yes, that is very good observation, good point. So then, from our perspective, I'm sure DOCOMO is also already using AIML for certain purposes, right, for network management already. But then what do you expect from AIML in the future? So from your network operation perspectives, maybe you can have some views on that.
Yeah. Actually, we are using AI for the network operation already, and some kind of the Song is some kind of the AI initial phase of the AI. But we are deploying the AI technologies for the network operation so much, and then we will use more and more, I think. Actually, I have a question on the AI. I would like to ask a question to everybody that if AI can be used so much for our industries, not only for the performance, but also the IoT testing point of view, we can have a benefit. I mean, that if we can use AI more and more, we can shorten the development time, and we can decrease the load of the testing, IoT. How do you think about that? If it is, it can be realistic, that should be nice. Yeah, actually, our mobile communication systems are so complicated, so many options, so many parameters, and we need to test so many kind of tests. If we can relax those kind of effort. That's good by the AI. What do you think?
I think that's a very fundamental question, maybe philosophical question. And I mean, okay, in the interest of time, maybe we cannot spend, I cannot invite answers from Charlie or John, but if I add my own observation, I think in theory, yes, I think there's such a possibility because people are believing the AI can kind of relax, as you said, the workload from human. So perhaps we can meet in the near future this year, hopefully. Then we can discuss about the over dinner and some beer. Okay. All right, so thank you very much for participating in the panel session. I'm sure people have enjoyed your insights as experts from industry and academia, and I hope people can utilize what they learned from today's discussion for their further research towards 6G. So once again, thank you very much for joining the panel. So I really hope to meet you in person in the near future and talk about the AI versus human labor aspect over dinner. Okay, thank you. Thank you. Talk to you later again. So we can conclude a panel session with this. But then before going for lunch break, we have some announcements. So there will be a broadcast of the video clip of some research outcome on 6G. And Seung Choi, who is SVP and head of the Advanced Communications Research Center at Samsung Research, will introduce our research results for some of the selected topics. And the lunch break will continue until 10 past 1. So afternoon session will start 10 past 1 with the theme of the intelligent network. So I hope everybody can come back by then. So thank you very much for your time in the morning. So see you soon again in the afternoon session. Thank you, bye.
Hello, everyone. I'm Seung Choi, the head of Advanced Communications Research Center at Samsung Research. Since 2019, we have been developing 6G technology with the vision to provide the next hyper-connected experience for all. Today, I'm very excited to share some of our progresses in 6G R&D. Before talking about the technological innovation, let me briefly talk about spectrum for 6G. This slide shows frequency allocation chart of Korea, including 5G bands at 3.5G, 5 gigahertz, and 28 gigahertz, and so on. Apparently, different countries their own frequency allocation chart. However, in order to achieve cost-effective global coverage, we have been trying to harmonize the spectrum for mobile communication as much as possible through discussion and collaboration in the places like ITUR. Well, actually, to identify and secure spectrum for a generation of mobile communication, it takes a decade. So this is the very right time to start talking about and identifying 6G spectrum. While we are currently under the study to identify target services and applications and target KPIs, we all believe that the performance of 6G should be far beyond that of 5G. And apparently, in order to achieve that, we need very wide bandwidth of spectrum. To achieve that kind of performance, we are considering new 6G spectrum in upper midband from 7 to 24 gigahertz and sub-terahertz band from 92 to 300 gigahertz. On the other hand, shown at the left figure, different ranges of spectrum have their own pros and cons in terms of coverage and available contiguous bandwidth. Accordingly, in order to achieve various services and applications, we need to utilize all different ranges of spectrum, namely low, mid, and high bands. At the same time, we have to work on to develop selective usage of spectrum in a flexible manner to use limited frequency resources efficiently, while considering both technical and regulatory approaches. I'm very pleased to share that we recently released 6G spectrum white paper, including all thoughts related with 6G spectrum. Now let's talk about technological innovation. Apparently, to enable and achieve 6G, we need to consider all different possibilities. Today, we would like to demonstrate some of selected 6G candidate technologies which we have been working on during the last 3 years. That includes terahertz communication, RIS or reconfigurable intelligent surface, and advanced duplex technology that should include XDD and full duplex, and finally, native AI that includes AI-based nonlinearity compensator and AI-based RAN power saving or energy saving. Let's talk about terahertz communication. As I said, as a new spectrum for 6G, we are considering sub-terahertz above 92 gigahertz to support broader band communication. Apparently, sub-terahertz band includes enormous available bandwidth for potential 6G services. And thanks to the usage of wide bandwidth, we can achieve high precision positioning and sensing capability. On the other hand, to utilize terahertz or sub-terahertz band, there are a lot of inherent technical challenges. Basically, as frequency goes up, antenna and RF loss increases, and also path loss increases too. At the same time, power amplifiers' output power is likely to go down, and low noise amplifiers' noise figure is likely to go up. For the same number of antenna elements, antenna and package size is going to down. That could result in thermal density going up, thus result in RF performance going down eventually. I said that wide availability of wide bandwidth is a kind of big plus, but as bandwidth increases, we need to increase the sampling rate. That could result in ADC and DAC power consumption going up. So in order to utilize terahertz band for 6G, we need to tackle all these challenges. And we have been trying to verify the kind of availability and achievability of terahertz communication through series of POC efforts. And this slide shows the current status of our RFIC. At both TX and RX module, we use CMOS RF ICs. And also for the transmitter side, we used indium phosphide power amplifiers. For TX power amplifier, we could achieve 112 milliwatt. And for the receiving side, noise figure of LNA is kind of found to be around 8.5 dB. So for our POC setup, we used TX and RX module, which I just showed. So they are composed of CMOS, RFIC, power amplifier, and 64 antenna elements to support 8 TX and RX chains, and also baseband and host machines to test both indoor and outdoor environment. This video shows that the transmitter module is composed of RFICs and indium phosphide amplifier and 64 antenna elements. And this one shows our baseband processing module. So for indoor test, we did test while separating transmitter and receiver with the distance of 30 meters. And then we tested using 16 QAM modulation to achieve 12 gigabps data rate. What's very exciting in here is, as shown in this video, we achieved beamforming. So as shown in this video, basically the transmitter's direction or orientation is kind of rotated. Even if the rotation is occurring, the beamforming towards the receiver is maintained in an adaptive manner so that irrespective of the direction or orientation of the transmitter, the link between transmitter and receiver is maintained so that the data rate of 12 gigabps could be maintained. Then we also went out to the outdoor environment. So in the parking lot environment of our research center, we did test with transmitter and receiver separated by 120 meters. And then we achieved 2.3 gigabps data rate by utilizing QPSK modulation. The next is RIS, or Reconfigurable Intelligent Surface. RIS is actively controlled metamaterial-based surface, or metasurface, to enhance beamforming and signal propagation. There are mainly two types of RIS, namely lens type and reflector type. The lens type can be placed in front of conventional antenna, and it can be used to enhance gain and steering range when the EM wave passes through the lens. On the other hand, with reflector type, it can provide alternative path when there is no line of sight path exists between transmitter and receiver. So basically, when the signal EM wave is reflected by this RIS reflector, the reflecting direction can be configured so that the target receiver, which could not be reachable, can be reached by the reflected signal from this RIS reflector. Recently, we did some POC with RIS lens prototyping. Our prototype is composed of 256 unit cells, where each cell provides phase reconfiguration using active devices composed of pin diodes. So because we have 2D array of unit cells, by controlling the phase distribution, we can control the direction and beam width of the signal which is passing through this lens. So that's shown at the left figure, or kind of animation. So when we have RIS lens in front of phase array antenna, we can use smaller set of phase array, so that's with smaller number of antenna elements, while we achieve the same performance as that of a phase array antenna with a lot larger number of antenna elements. So thanks to this reduced number of antenna elements, and also accordingly fewer RF chains, we can achieve reduced power consumption. That could be one potential beauty of this kind of RIS lenses. So this video shows our live POC demo. So in here, RIS lens is placed in front of horn antenna. And at the bottom, we have arrows which shows or indicate the signal strength at the receiver. So when RIS lens is turned off, the arrow length is just indicated by green color. Now by activating RIS lens, about 6 dB gain is achieved. And also by changing the phase distribution, 40-degree steering is achieved. And now by changing the direction of horn antenna by 40 degrees, actually the beam gain towards antenna 2 is becomes even higher. And then finally, additionally, by changing the phase distribution of the lens, we can achieve 60-degree steering of this beam. So what I'm showing in here is by utilizing RIS lens along with antenna, traditional antenna, we can achieve higher beam gain and also potentially wider steering range, which is not typically possible with only traditional and conventional phased array antenna. Yeah, the next topic is advanced duplex technology. Let's try to use basically full duplex and XDD, which is cross-division duplexing, on top of TDD and FDD in an adaptive manner, depending on the situation and environment of the network. So we have been utilizing TDD and FDD for 5G and 4G and so on, in which uplink and downlink signals are transmitted in a mutually exclusive manner. On the other hand, full duplex drastically increased the capacity by allowing both uplink and downlink transmissions occur simultaneously utilizing the same frequency. On the other hand, XDD, which we recently proposed as part of 3GPP Release 18, utilizes separated frequencies for uplink and downlink, but in the same TDD band, and also with very little gap between uplink and downlink spectrum. This one can achieve coverage extension, especially for uplink transmission, and also lower latency for overall throughput perspective in the TDD band. So for both XDD and TDD, the key challenge is how to cancel self-interference. So as shown at the right-hand side, with full duplex, uplink and downlink occur simultaneously in the exactly overlapping manner in the frequency domain. So downlink transmission from the base station interfere uplink signal reception at the base station. In the case of XDD, downlink and uplink transmission do not overlap in the frequency domain, but still, since the signaling and spectrum is not perfect, downlink transmission is kind of leaked into uplink frequency domain so that uplink reception is interfered. So in this environment, how to cancel self-interference to achieve uplink and downlink transmission reception simultaneous is the key challenge. To achieve self-interference cancellation, we can try cancel the self-interference in multiple domains, namely antenna domain and analog or RF domain, and finally digital domain. In our POC, we skipped the analog domain self-interference cancellation and just tried to utilize antenna and digital signal cancellation. So let's take a look at XDD. So basically, after antenna SIC, before digital SIC, downlink spectrum is kind of reduced, but still a lot higher than uplink receiving signal spectrum so that uplink reception can be interfered. However, after digital SiC, downlink spectrum is kind of reduced down to close to noise floor so that uplink reception can be achieved successfully. So the next one is full duplex in the mmWave band. So base station and mobile terminal are separated by 100 meters in the outdoor environment. And after antenna SiC, 78 dB power is kind of canceled. And then in the digital domain, through digital SiC, 36 dB additional interference is kind of canceled. And eventually, as shown in the video, basically the residual self-interference is kind of right above noise floor, so it's almost canceled. So we achieved more than 114 dB self-interference cancellation. And this enabled 64 QAM transmission and reception simultaneously. And accordingly, what we see in here is, with conventional TDD, the sum of uplink and downlink throughput is about 390 megabps. But with full duplex, we achieved over 740 megabps total throughput. So which should represent about 2 times throughput gain achievement and so on. So the last topic is AI ML for communications. So we are trying to achieve comprehensive and native AI for 6G network intelligence. So we are currently using 4G and 5G, and in today's network, we have been trying to utilize AI ML for network management and optimization. However, with 6G, we will develop 6G with AI in mind. And so AI should be core part of 6G technology. So that means AI can be utilized even in the physical layer, which could not be possible with the conventional, traditional mobile communication so far. So while we are working on native AI for 6G, we have been making some progress with applying AI ML technology to 4G, 5G, and today's network. And I would like to share some of our progresses today. The first one is AI-based RAN energy saving, or AIES. So in cellular network, there are multiple cell sites, and each cell site is typically composed of 3 sectors. And each sector runs normally multiple component carriers. So in here, we call each component carrier a cell. So when a sector is composed of multiple cells, depending on the traffic load of that cell, we could potentially turn off some cells so that the energy consumption of the RAN or base station can be reduced. So the quick question is, what should be the rule or parameter to turn on and off each cell in each cell site or RAN? And we try to utilize AI ML technology to determine such cell on-off parameter optimization. Well, of course, the bottom line is we try to turn and off the cells by utilizing fixed and default parameters. And what we have observed and will show today is, by utilizing per site or site-specific, cell on-off parameters, which were determined using AI ML technology, can achieve higher energy saving while maintaining the cell performance, for example, throughput, remain the same. So what's shown in the left-hand side is, by utilizing AIES, we could achieve a lot higher energy saving. So that's over 10%, while default threshold usage resulted in only around up to 2% energy saving. And at the same time, if you take a look at the perceived throughput, the perceived throughput is not much, compromised. Another important thing is, in order to utilize AI ML for this purpose, we have to make the overall process, so that is, a kind of, automated. So that's, closed loop data collection and training pipeline should be achieved to reduce optimizing time and labor resources. So if you take a look at the figure, the real data should be collected from the network, real network, and then after pre-processing, analysis, and so on, the data could be utilized for model training. And for this model training purpose, we use real data-based replicated simulation for reinforcement learning. And then through this kind of model training, we determine these cell on-off parameters, and which could be deployed to the real network. And then this kind of cycle can repeat over time to optimize the network even as time goes. So this video shows the comparison between AIES and the usage of default threshold. So, for a single site, there are 3 sectors and there are multiple cells, and some of the cells are kind of turned off depending on the traffic load. And we see that power consumption comparison and, AIES achieves low power consumption, and the very important part is the usage of default threshold can sometimes break the threshold of IP throughput. So that's, as shown right in here, basically the throughput of under 1 megabps is kind of achieved with default threshold usage. On the other hand, AIES guarantees that the throughput performance is not violated. So this video shows that the comparison again in terms of power consumption, PRB usage, and IP throughput. So power consumption is kind of maintained low, and IP throughput remains above 1 megabps. On the other hand, the default threshold usage now in here, we see that the throughput is kind of violated. So that's, throughput goes below 1 megabps. So the second topic in AI is AI-based nonlinearity compensator, or AINC. This is a kind of receiver algorithm at the base station so that the uplink coverage can be extended and throughput can be extended as well. Our AINC receiver utilizes very lightweight AI receiver that enables very fast learning of the AI model, and then that can be utilized at the data reception by compensating the distortion introduced at the transmitter due to the power amp's nonlinearity. So if you take a look at the figure, the graph, that shows the power amp's characteristics. In ideal situation, as the input power increases, the output power should increase linearly. However, in practical PA, as input power increases, the output power is kind of saturated. So in order to avoid that kind of nonlinearity effect, normally in traditional environment, the transmit power is backed off so that the transmitted signal will kind of made within the linear region of the power amplifier. However, our AINC allows the transmitter to transmit even higher power. But in such a case, signal will be distorted, but receiver can correct or compensate that distorted signal at the receiver side. So how it works in a very high level is the receiver, by receiving transmitter's reference signal, the receiver train AINC's AI model, and then by utilizing that trained model, the data distortion can be compensated during the reception too. So by utilizing this AINC, the UE can boost up the transmit power, especially for high order modulation scheme like 256 QAM. With commercial UE, we found that 2.5 dB gain is expected, and in POC environment, we found that the coverage extension of 90% was measured. On the other hand, this technology can be utilized to increase the modulation order even further. So as of today in 5G, 256 QAM is the highest order modulation scheme. On the other hand, if we apply AIN's kind of reception algorithm, the transmitter or UE is allowed to transmit even higher out order modulation scheme, such as 1K QAM and 4K QAM. And apparently, if we use 4K QAM instead of 256 QAM, the throughput gain of 50% is expected, which is humongous. So this video shows what happens with conventional receiver. So with conventional receiver in this environment, we found that the distance of 13 meters is kind of achievable for 256 QAM transmission. On the other hand, AINC allows 4 dB higher transmit power so that the transmission distance can be increased to 25 meters. So as a result, overall, 1.9 distance is kind of achieved with AINC compared with conventional receiver. So that's it for today. 6G technology development will be long and sweaty journey. We'll continue to make our best effort to achieve our vision to provide the next hyper-connected experience for all. Thank you very much for your interest and support. Thank you.
Okay, let's resume. I hope everybody enjoyed lunch as well as demos presented by Seung-Yeon Choi, who is also going to coordinate the panel discussion in the afternoon. Again, my name is Eddie Kwon. The afternoon session is Intelligent Network for 6G. So the section will start from a keynote speech by Professor Tarik Taleb from University of Oulu, Finland. Then we are going to have invite talks by 3 speakers. Seung-Ju Meng, who is master of the Samsung Electronics, and Byung-Hyo Shim is professor from Seoul National University, and Professor Shijin from the Southeast University. Then after the 10-minute break, we are going to have the afternoon panel session on the network AI to be coordinated by Seung-Yeon Choi, who is EVP, Samsung Research. And then Seung-Yeon will conclude today's forum. Okay, that's the plan for the afternoon. And again, same as in the morning, if you have questions, please upload your questions to the board, online board, and you will have a chance to win a small surprise. So please give it a try. All right, then Tarik Taleb, a professor at Oulu University, is going to give a keynote speech under the title 6G Networking, the Journey Toward a Novel Vision of Service of Services. Professor Taleb, the floor is yours.
Today, I'm extremely delighted to give this talk on beyond 5G or 6G networking, where I would like to share the view on this journey, which I think is going to lead us to a novel vision of 6G as being a service of services, rather than what is known as 6G being a network of networks. I'm very delighted, honored, and also very grateful to Samsung for this opportunity. I'm Professor Tarik Taleb from the University of Oulu. Before we delve into the topic of today's talk, I would like to study with you the current stand of 5G. In my humble opinion, 5G is facing kind of challenging business models. Number one, OTT are not willing to pay. Over-the-top service providers are not willing to pay. Verticals, as you know, 5G has been designed for them, but when it comes to the payment or the business model, who is going to pay for the service is not clear yet. For example, in case of automotive, who is going to pay for the connectivity service? Is it the driver, the owner of the vehicle, or is it the manufacturer of the car? And in case of the driver of the car, who is going to be liable in case there is a problem with the connectivity that caused any kind of car accident? So there are lots of challenging business models with the deployment of verticals in the context of 5G. At the same time, the business style is still kind of old-fashioned. Vendors are still selling boxes rather than softwares that could be deployed at large scale by the mobile operators. Even the architecture itself is kind of tied to the 4G model, particularly when it comes to the reference point model of the 5G architecture. There are lots of challenges with the regulations. Of course, the licenses are expensive of any kind of generation system, and that applies to 5G. But when it comes to 5G, as I said, 5G is being designed for many verticals, but then we don't see them being deployed at a large scale. For example, automotive and UAVs, they are not there yet because there are strict regulations when it comes to the deployment, and that relate to safety and so on and so forth. And this really puts mobile operators in a dilemma because they have to invest into buying new infrastructure equipment, which is usually expensive, but at the same time, there is this low average revenue per user. So there is not immediate return on investment on the infrastructure. 5G has been designed really with very ambitious requirements, particularly when it comes to the latency. We know that 5G was aiming for having the 1 millisecond end-to-end latency, But the question is always for what kind of service, which is supposed to be deployed at a large scale, so that will be in need of that expensive technology that will guarantee the end-to-end 1 millisecond latency. And it seems we are doing, I would say, the same mistake even in defining the requirements of 6G by using this kind of simplistic mathematical operations where we say, okay, 6G is going to provide 1,000 times more capacity than 5G. It's going to provide 1/10 of the latency that is going to be provided by 5G and so on. I have seen white papers that speak about 0.1 millisecond end-to-end latency for 6G, but my question is always, which is the service that will be deployed at a large scale that is supposed to bring lots of revenues to the operators that will be in need of this very expensive technology that will support this 0.1 millisecond latency. And for me, this is always the question which personally I'm very much bothered with. Yes, 5G has been designed for these three main use cases, which are enhanced mobile broadband, massive Internet of Things services, and also ultra-reliable low latency communications. When it comes to the massive Internet of Things, I think with some traffic engineering, 4G can do the job. And I don't have to go into details of how. When it comes to enhanced mobile broadband, yes, if we boost the radio access network with mmWave antennas that could be deployed in urban areas where we have lots of buildings, yes, we can also support that, even using only the 4G core network, which is the way how 5G is being deployed nowadays, this non-standalone deployment style. But in my humble opinion, 5G is lacking big time when it comes to the support of ultra-reliable low latency communication services. And this brings us to two categories of use cases of 6G. All the use cases, they are all not because they are widely deployed, they are all just because we are inheriting them from 5G. And here comes automotive, UAVs, tactile internet, and so on and so forth. And the new category of use cases include immersive services. It's holographic teleportation, digital twinning, Internet of Intelligence, and so on and so forth. Now, hopefully that was in brief about the current stand of 5G. Let's look into the beyond 5G networking. I think previous generations were characterized by certain feature. For example, 3G and 4G is the technology that supported ubiquitous connectivity with the roaming. 5G is the technology that actually brought in the expertise of cloud computing as well as software engineering to the telco world. And because of that, we have heavy involvement of different business models of cloud computing in 5G, like this IaaS, PaaS, and SaaS. There is, to a certain extent, large adoption of several IT principles in 5G, microservice concept, integration fabric concept, NFV, network slicing and softwareization, service-based architecture. Even the current design of 5G core is following some principles of SBA, service-based architecture, particularly in the control plane. But when it comes to the data plane, it's still, following the old model, which is reference point. Now, because of this, yes, we could achieve these two features in the design of 5G. We have services, mainly the control plane services, being loosely coupled, and that means they can be flexibly deployed on virtualization platforms. We have achieved certain level of modularity by splitting the mobility management from the session management. But when it comes to whether the system is truly cloud native, whether there is this extensibility of services, whether the network is truly open, in my humble opinion, the 5G core design that we have nowadays is not meeting these requirements. Now, with this in mind, and with also this level of progress that we have achieved in the adoption of IT principles in 5G design, I think when we design the 6G system, we should really do it in the right way, and we should make sure that it is truly cloud native. And this is what I want to leverage in this talk. Now, in my opinion, the beyond 5G system should be truly cloud native, entirely SBA based, and it's a system where you leverage this concept of producer-consumer relationship in the perfect way, including also the network. It's going to be a system which is composed of a set of services that could register somewhere at a certain point, like you see here, service registration and discovery function. And through that function, they can discover each other and they can actually talk to each other, of course, in secure manner. Now, in this vision, network is just a service which could produce connectivity service as it is to many services, but it could be also a service which is just consuming another, another service, within this set of services. So with this, when we think about beyond 5G, of course, we build on all of these things that have been achieved in 5G design. And I would say that beyond 5G system is the technology that will build on the expertise of cloud computing, software engineering, exactly like 5G did, but it is the technology that will bring in also expertise from the artificial intelligence world and also from the sensing actuation world, to the telco. In the 6G flagship program that we have running in Oulu University, we've been actually thinking of how we should be designing, the 6G system architecture with this concept in mind of service of services. And we came with these 6 key enabling services that you see here on the slide. Let's say that we want to deploy a service which is in need of having its packets delivered over the network. So, of course, network is a service, is a key enabling service there. This network components could be running as softwareized on a cloud computing platform, which will be provided by this application computing service. And even the service itself could be having its functions running, as cloud service provided by this application computing key enabling service. Now, of course, we aim for customization of the services. And for that purpose, it's very important to understand, contextual information about the users, basically how they are consuming the services, their mobility patterns, and so on and so forth. And you want to understand also the location in which users are actually moving or residing, and the location in wherein the service is going to be consumed. This brings us to the 4th key enabling service, which is service that will provide you with information about the location. Of course, the data that you get from here, you could fed into a suitable AI model that will take certain decisions of how to lifecycle manage the service. And this brings us to the 5th key enabling service, which we refer to as ubiquitous intelligence. But you can think of it as a huge library of AI models that could be called upon as per the need of the service that you target to deploy. And of course, this is service to which many AI model developers could actually commit their models and then have them being used by a third party. Then when a decision is being taken, then that decision is going to be enforced by an activation or by an orchestration system, if you want to allocate more resources and so on and so forth. And this brings us to the 6th key enabling service. Of course, with this concept of service of services, you would be able to deploy this at, with lots of flexibility and also as per the need of the service that you're targeting, and also as per the service, the region, service area which this service is supposed to be consumed in. So you could deploy just for a small region, or you could enlarge it to a city level or to a country level, and so on and so forth. All of these services, they should be communicating among themselves, following the IT principles. And here, of course, we use this concept of integration fabric, where they could discover themselves, where they could register, discover themselves, invoke each other, and communicate in a secure manner. The same integration fabric will be used by this service to consume these services that are actually, that we refer to as key enabling services. And the same integration fabric can be used actually by other services to communicate among each other. And this is exactly how extensibility can be achieved. Now, that was, let's say, the functional model of the 6G architecture, but let's look into it from the logical perspective. Of course, we will be having always this infrastructure, which is complex, which is consisting of multiple technologies and under the authority of different administrators. And we don't need to reinvent the wheel here. The way how to abstract this is there are lots of standards and there are lots of research work that has been done. Even there are lots of open sources that could be used, for abstracting the resources and building what we refer to here as cross-domain resource management and orchestration. So nothing to reinvent, but we build on what has been already achieved, in 5G. Now, let's say that we want to provide the service to user equipments or end devices which are actually on the move or static, like static IoT devices. These devices, they need to connect via just the run that we have nowadays, dedicated run or a shared run as we have nowadays, or actually the intention is to have run also, with its components virtualized. And, you have the there has been lots of work being done with the Open RAN and so on, things even moving towards this direction. Now, the data will be, of course, delivered on the data plane, which is also sitting on the transport network. This data plane is going to be controlled by a control plane. And of course, all of these functions, they could be just software images, software components, which you could run on any kind of edge cloud, near or far edge cloud, or centralized cloud. And that's the thing. It's actually that all the components that you see here, they could be just softwareized, and they talk among each other, via also an integration fabric, which is dedicated for that communication. Now, on top of that, of course, we're thinking about another layer, which is in-network supporting function, which we think of, sometimes, you have data which is coming from these end devices. It doesn't have to go all the way to the server to be processed, but you could just locally break it out at certain points, suitable points in the data plane, and then you break it out to function which we treat it, and then you get the outcome of that processing. For example, let's say that you are actually streaming video of certain location, and you want to know the faces of people that are actually moving in that location for safety reason. It can be used by the police or certain authorities. Then video will be streamed from this HoloLens, for example, from these glasses. They get broken out a certain data plane, and then they go to this in-network supporting function, which is like an object detection software, which does for you the processing, and then it tells you, okay, it gives you, it lists you, the names of the people, for example. Okay, so that's and this in-network supporting function, it could be different functions which need to be, of course, placed close to the end users. Now, each of these segments could be having its own closed loop, for the zero management of that segment, zero touch management of that segment. For example, you have an agent which is collecting data, doing the analytics, and then doing decision, and then enforcing that decision, using this suitable activator for that segment. Of course, the decisions could be selfish. For example, a RAN could take a decision which is just optimal for itself, but then it may not be optimal, for the control plane or for the in-network supporting function, and so on and so forth. And that's why coordination among these closed loops could be very beneficial sometimes. I mean, you could take a decision which is suboptimal to run, but then it's optimal when you look at it. And these decisions could be done offline or could be done online. In case of online, of course, you have to take into account the latency sensitivity of the service that you are actually addressing. When it comes to the service itself, of course, it's logic as well as the database, which is storing information about the end users and so on. Could be, it's running on the cloud, and this is what we have nowadays. It has also its own closed loop. But then what we are actually also thinking of is actually leveraging this concept of DevOps, which has been very successful, in the deployment of large-scale applications in the IT world. Since now we are also advocating for the concept of having the network itself provided as a software or as a cloud service and integrated well with the service itself. The DevOps concept could be also extended to the network service itself. And I'll explain that soon. So basically what we are doing, we're trying to extend the concept of cloud computing beyond data centers. So instead of having, for example, my service, my Gmails running in Google data centers, and then the connectivity is coming from completely third party, I could have my Gmails, my emails, running, stored in Google data center, but the network which will allow me to access my emails is actually also provided as cloud service, and it's consisting of the right functions, in the right locations, with the right amount of cloud resources, and so on and so forth. And all of this is offered to me as one atomic end-to-end service. And of course, it comes also with the DevOps features, where I'll be having, for example, certain amount of resources for the production. Huge amount of resources for the production, but then certain amount for development and testing. Only when I'm sure that the upgrades I made to the service also suits well with the functions that I'm running, in my network service, which is for development and testing. Only when I'm sure that end-to-end everything is going well, then I push it for the production. And this, of course, makes lots of sense, for deploying, this kind of immersive services where they need kind of special treatment of their packets. I mean, maybe the example of Gmails I was bringing was not the best example, but when it comes to immersive services, holographic teleportation services, and so on, building a network service which is really consisting of the functions that are most suitable for the processing of the packets of that service would make lots of sense. So in this way, what we're doing, we can create end-to-end network slice and also the service on the cloud. Everything, I mean, all these services could be exposing themselves through well-defined APIs, and through these APIs, they can actually consume each other. And this is how we can achieve, that concept of extensibility. Now, with this concept, we achieve mobile connectivity, transport networking, in network computing or in network supporting functions, decentralized computing, smart storage, DevOps features, everything as one atomic end-to-end service, and it comes with all of these nice features of cloud computing. Now, the extensibility can be achieved also in this, with this design. I mean, if you follow these design principles from the beginning, where we have the services, they can also register themselves and then communicate among each other through the same integration fabric, which is used, for that key enabling services, as I mentioned earlier. I mean, what service extensibility means? Let's say that I'm actually providing service to a certain mall, but then with time, I realized that actually I need to know more information about the mall, for example, about the location, the shops, and so on and so forth. Instead of having engineers that will develop for me, new codes that will actually collect that information about the mall and so on and so forth, I can just extend, I can just search for what is these services that are actually registered with the integration fabric that are actually providing information about the mall and whatever, the shops and so on and so forth. And then I will just consume it. And this actually what helps me to achieve, it helps me to upgrade my service, optimize it, quickly, in a cost-efficient way, and also it speeds my time to market. So this service extensibility definitely has lots of advantages. And with this also we achieve true network openness. I mean, as I said, instead of having the boundaries of the administration of the service provider only to the to the service logic and the database, which is actually managing, information about the end users, but the network is completely from the third party, consisting of functions which are probably not very suitable for my, for my type of packets. I mean, we extend the boundaries of this service provider all the way to the last mile, to the radio access network, and we offer everything. Everything is under the administration and the authority of the service provider. And somehow the service provider itself becomes also an operator, let's say network operator of the packets, for the delivery of the packets of its own services. And if we do this, I think lots of innovation could be enabled. Now, to achieve this concept of services, definitely edge computing has lots of role. And here I would like just to shed some light on the potential of edge computing in this context. And as I said, it's very important, for services which are actually envisioned in beyond 5G. I mean, either the old ones or the new ones. As a matter of fact, actually, all of these services which are actually qualified as beyond 5G services, they are actually in need, they fall under this category of immersive services, many of them, and they are in need of, to operate with the good immersive experience from the end user's perspective. There is need to ensure this motion to photon latency that should be less than 20 milliseconds. And this includes also the latency which is needed by the display technology for the refresh rate and so on and so forth. So if we take this into account, I mean, we have only 7 milliseconds which is left for computing and rendering and also the networking latency. So we are speaking about services that are really in need of being processed as closer as possible to the end users. Now, when there has been this study that studied, different edge cloud or different cloud infrastructure, which are actually provided all over the world, and the conclusion that was made by this study is that actually there are only very few countries that can really meet this timing deadline for the motion to the photon latency, which is 20 milliseconds. I mean, most of the countries, they are in need of having, their cloud or their edge cloud being deployed, locally. Now, once we have this edge cloud, and once we have this network softwareization, as I mentioned earlier, really enabled, what we can achieve, we can, we can push the services or the network services that are actually going to treat or to process the packets of the services as close as possible to the end users. Now, how that will happen, for example, if I have a service which is, I don't care about its latency, of course, like I'll be having service cached somewhere, like in CDN here in core, which could be far away from the end user. And then data will be broken at, for example, this UPF if I'm using 5G core, and then it will be, service will be consumed from the CDN. Now, if I'm talking about latency of, I don't know, maybe 20 or 30 milliseconds, then maybe I will use this concept of multi-access edge computing, where I will cache or store that service, and then I break out here at this UPF, and then the flow of packets will be coming from the end user via this distributed unit to the centralized unit. It goes to the UPF, it gets broken out, and then you consume it from the MEC. Now, if I'm talking about a service which in need of even more stricter latency or shorter latency, then I'll do the same thing. But then now I place the service much closer to the end user. And if I'm talking about really much shorter latency, then I will do the same thing. Of course, assuming that I have some kind of compute and storage resources at this distributed unit, where I will break out, at this UPF and then consume the service from very nearby. So basically, I would say with Edge Cloud, as well as with this ability of softwarizing the network and deploying it, as a cloud service, we have the right ingredient to do, to support that short latency which is needed by many beyond 5G services. But no matter how we get this closer to the end user, there is always a network segment which is going to be used, for the delivery of packets. And of course, when we are talking about the single-digit latency requirement, that means services that are in need of less than 10 millisecond latency, whatever we do to save in the networking latency is good. And whatever we do also in the processing and the computation will be, of course, very appreciated and beneficial. And here we have been looking into how we can support this kind of deterministic networking. Also adding to it, the processing latency which is needed by, GPUs or CPUs, which are actually offered by the cloud. And the conclusion is, of course, there is still need for proper queue management to ensure the deterministic quality of service requirements. Sometimes it is even important, to create remotely, new queues that will be, let's say, new high priority queues that will be dealing with certain flows that just emerge. And we have been able to do that actually using SDN solutions. Instead of just defining which switches, traffic should go via, or we can even define which queues within each switch, these flows have to be traversing, or sometimes even we have to create them remotely, so we can ensure that the end-to-end latency of that particular flow is kind of below a certain threshold. And that's how we can ensure this deterministic networking. And this is actually a term which we have been coining, which we call software-defined queuing. So it's not the network part that you define, but also you can define the queues via which these flows have to go via, and of course in a remote fashion. Of course, even if you create queues which are actually high priority queues, then you still have to. These queues, they will be shared by flows that are having the same requirements, and that's why it's very important to look into how you schedule the flows, how you shape the traffic, so you can, optimize the latency or shorten the latency for all of the flows that are actually competing for the resources of that particular. And of course, artificial intelligence can help. Of course, not any kind of artificial intelligence. If you have data about the flows and the behavior, then you can have some kind of scheduling which is happening, based on accurate data, which is not always the case. As you know, dynamics of networks are not always predictable. And that's why we've been looking into how we can use reinforcement learning, which is not depending too much on prior knowledge of the behavior of flows or prior availability of data. And we have shown that actually with the reinforcement learning, yes, we can at least increase the number of flows that could be accepted while still meeting their deterministic requirements in terms of latency. And we are hoping to extend the study to include also the bandwidth, deterministic requirements of the bandwidth. Of course, whatever packet of service that you are providing on a mobile network, you are still doing that on the transport network. And that's why it's very important to look into the problem of the end-to-end latency or deterministic latency provisioning, across all the segments, including, the transport network. And that's why it's very important to have, I would say, tighter integration with the transport network. And we have done certain studies there where we, as I said before, we'll be having data centers which are actually together with the optical transport network equipment, and then we can decide where to place, the functions that are processing those flows. Of course, when we decide on how to place them, we have to take into account that latency, and this is one study which we have done where we advocate for service function chaining in a latency-aware manner on the transport network, and we could get some good results, which you can find actually in this publication. Of course, if we use edge cloud, which are actually closer to the end users, the cost of those edge cloud resources are always expensive. The closer you get to the end users, the more expensive, in my humble opinion, the resources will become. And if we add the cost into as a factor, then there are also some kind of optimization techniques that we could adopt where we can minimize the cost which is involved in the deployment of those functions, but at the same time we maximize the number of flows that will be accepted without compromising the deterministic requirements in terms of latency as well as bandwidth. So there are lots of interesting things that could be done to achieve that deterministic latency requirements of many of those beyond 5G services. Definitely the networking principles have to be revised. I mean, here briefly, very briefly, I just mentioned that how we can select, the service function chaining, how we can build the queues or remotely create them and then direct, flows ongoing via, specific queues, which are classified as high priority and so on. How we can even select links in the bundle, how we can even add the processing latency itself, in the end-to-end latency. And there is lots of work happening there. Under this umbrella of computation first networking, for example. We can do semantic routing, dynamic casting, and so on and so forth. In my humble opinion, all of these are actually short-term solutions to a big problem that we will be definitely facing. We have metaverse-like applications being deployed at a large scale. The network itself becomes the bottleneck, and the bottleneck not only in terms of bandwidth, but also in terms of latency. And probably I think it's the right time to look into how we can completely revise, the IP principles or the IP protocols that we are using for networking. And I think we should do it before it becomes too late, because the problem is going to hit us definitely once we have this, as I said, metaverse-like services or immersive services being deployed at a very, very large scale. Maybe we have to think about the new IP. So with this, I come to the end of my talk. I thank you for your attention. Just as a recap, as I said, definitely when we think about how we design the beyond 5G system, we have to make sure that it is truly cloud native. Instead of understanding it as just like a network of networks that should be integrated, we have to think about it as a service of services, and really we have to have that in mind when we do the design. So we can gain a lot in terms of flexibility of deployment and speed of time to market and so on and so forth. DevOps has been a very great feature or principle adopted in IT, and it should be brought now to networking. And we have already achieved a lot in terms of softwarizing the network and learning actually from the expertise of the IT world. And why not bringing DevOps also to extending it also to the concept of network softwarization. Definitely AI is a very important, let's say, component for achieving this zero-touch service and network management. Latency, extreme latency, low latency communication, that's where 5G, as I said, is lacking. And I think this problem is going to become more and more challenging, in the context of beyond 5G. There are lots of solutions that we can come up with, but they remain as a short-term solutions, in my humble opinion. And we need to think about what is this long-term solution. At the end, still, we have to think probably about a completely new IP that will support this beyond 5G services, which are characterized by, low latency, huge interaction among the end users, and so on and so forth. Thank you, and this ends my talk.
Thank you very much, Professor Taleb, for a lot of valuable insight, in particular, network of networks and service of services. So let's take maybe one or two questions from the board. So the first question is, from the networking to protocol point of view, what kind of enhancement or new protocol adoption would be necessary in the next generation network?
Okay, yeah, thank you. As I mentioned also in earlier in the presentation, I mean, there are lots of work that is being done in accommodating, you know, this deterministic latency requirements of services. I mentioned about semantic routing, dynamic casting, you know, even you know, this computation first networking, where you add to the network latency, you also consider the processing latency. But in my humble opinion, as I said, these are like really short-term solutions, and probably we have to think about a new design of, let's say, IP protocols that can deal with this type of metaverse, you know, services that are really in need of lots of interaction, bandwidth intensive, and so on and so forth. And something else which I didn't mention in the presentation, and I think there are some researchers that are actually working on it. And since we are talking about AI, and I think there is this AI synthesized networking, where you have AI agents at, let's say, at certain routers or switches, where they decide how which transmission protocol to use for that particular, you know, service, predicting, you know, the dynamics of the network in the short term. So there are lots of opportunities, and this is quite interesting, you know, for the people doing research on networking in this arena of, you know, beyond 5G.
Okay. Thank you very much, Professor Taleb. So I think we can have further discussion in the following the panel discussion. So we'll see you soon again. Thank you.
Thank you.
Okay, so let's switch gears to invited talk. First speaker is Seung Meng, who is Master of Samsung Electronics. He's going to give us a presentation on challenges in applying AI/ML technology to mobile network. So, Seung, please go ahead.
Hello, everyone. Nice to meet you. This is Seung Meng from Samsung Electronics. It's my honor to meet you in the first Samsung 60 Forum. Today, I'm going to talk about the challenges of applying AI and ML technologies. First, let's look at the anomaly detection. As you know, mobile communication networks consist of a large number of base stations, and there are a variety of problems in the communication process between base stations and terminals. Your voice call may be cut off while you are working, or YouTube video is suddenly stalled when you turn around the corner, or you fail to upload the picture on the Instagram. Previously, an anomaly was detected by checking whether individual performance indicators are higher or lower than a specific threshold. But the problem with this method is that the accuracy is low and the number of cells detected is too large. AI-based anomaly detection uses a correlation between key performance indicators, and this detects whether the correlation deviates from the normal state, and you can check the anomalies more accurately. Now, let's look at the root cause analysis. Once you detected the problematic cell, now you need to know why this problem has occurred. AI-based root cause analysis extracts patterns of performance indicators for each problem category. And for the newly detected anomaly situation, it checks which pattern is mapped to the current problem, the current performance indicators, and finds the problem category. By this, operators can reduce effort to find the root cause of problem. Next is the alarm correlation. It is very important for mobile networks to provide stable services. So, operators check the normality of the system with numerous alarms. More than 1 million alarms are generated per day, and this is because alarms for one defect often set off more related subsequent alarms. Alarm correlation is a function that analyzes the correlation between alarms and identifies the core alarm, that is the real problem among various alarms. Through this, we can take the appropriate action quickly to solve the problem. There are also other AI technologies to improve network performance. Here are the 3 use cases: load balancing, and parameter recommendation, and energy saving. In general, mobile networks utilize multiple frequency bands, and the resource utilization rates of each frequency bands are quite different. In load balancing, AI technology determines how many users need to be moved from one frequency band to another in order to balance the load in each frequency band. A parameter recommender is a function that automatically tunes the parameter settings to improve network performance. In energy saving, AI technology can determine which frequency band should be turned off to maximize power saving gains, while at the same time minimizing the impact on the performance. And nowadays, many AI and ML use cases are being standardized in various standard organizations. ORAN and 3GPP are representative organizations. In ORAN, specifications are already made for these use cases. And several vendors already performs and showcase trials with these use cases in the latest MWC held in late February. In 3GPP, also trying to standardize AI ML use cases, including these, at release 18, which will start standardization from the second quarter of this year. And it will be completed in March 2024. Now, let's take a look at the difficulties of applying AI/ML technology one by one. They can be classified into 3 main categories here. The combining AI and ML technology with domain knowledge and securing data quality, and also the system architecture aspect. First, let's look at the domain knowledge aspect. AI/ML technology has developed based on computer science, but mobile network technology is based on communication theory. So the background is very different. There is also a big difference in the way we look at the problems. For example, from the standpoint of creating an AI and ML algorithm, if the correlation between two variables is very large, one of them is likely to be considered as an extra and will be ignored. On the other hand, in mobile networks, the moment when it goes wrong is the moment when a problem occurs. So it is necessary to monitor all of these performance indicators. The important role of domain experts here is to determine which parameters and which performance indicators should be monitored. So when developing AI and ML technology, AI and ML experts and domain knowledge experts should work closely together to develop meaningful and efficient technology. It is very natural and easy to say, but in real life, there are many cases where cooperation is not actively sought in different knowledge fields. So please keep in mind, it is very important that the solid cooperation between AI, ML experts and domain experts work together as key to successful technology development. The following is the issue of securing data. Since the AI and ML technology is based on model training, it is important to secure high-quality data. However, it is not easy to secure data because the amount of data is so large, and some operators prohibit data to be used outside the country boundary for security reasons. Also, it is difficult to obtain the labeled data. And even though the data is obtained, it often has inaccurate label. In addition, in order for the training result to be universal, the data for training itself must have diversity. But parameters applied to actual commercial networks often have a very limited range. In fact, the same default values are applied to most of the base stations, and different values are applied only to a few base stations. In this figure, you can observe that a certain configuration parameters are used frequently, but the others, the frequency is very low. So, one possible solution to this problem is to reproduce commercial network data with a simulator. Currently, we are working with Samsung for AI-based energy saving and simulator-based, that is, the digital twin-based one is used for that. But to maximize the usage and effectiveness of digital twin, it is necessary to reproduce more performance indicators in the simulator. This also requires huge computing power, but since the computing power of commercial CPUs or GPUs is increasing rapidly, this issue can be solved as time goes on. And so it is expected that a digital twin plays a key role in the 6G era. Another possible solution is to secure open data sets for mobile network. Of course, operators do not want to open their commercial data, but once the data is opened, more vendors will create innovative AI technologies using that data, which can also benefit operators as well. So I think it's time to start a discussion actively between operators and vendors about that, including how to abstract data so that the security-related issues can be hidden. And also, we should discuss about which key performance indicators should be considered and how much period considered and how many number of cells should be considered. And finally, let me talk about the system structure. Even if we have everything we have talked about so far, it will not work if the system structure is not suitable for operating AI. Nowadays, more and more operators request to support the ORAN architecture because the interfaces between network components are open and interoperable in ORAN architecture. Operators can buy different network components from different vendors, and operators can reduce cost through the competition. In the ORAN architecture, AI and ML use cases operate in the form of apps, like apps in our smartphones, in the centralized server. And it is necessary to secure sufficient interface capacity and to support the real-time data exchange between the centralized server and the digital unit of the base station. If the system is designed in consideration of these matters from the beginning, the scope of AI and ML technology that can be supported will be increased, and even scheduler functions can be supported as an app. In addition, the system should support fast recovery to the previous parameter setting in case that unexpected performance degradation occurs when applying AI and ML technology. Since stable operation is one of the top priorities for the mobile network, operators will be reluctant to apply AI technology if the performance degrades significantly during certain moments, even if the performance can be improved for the majority of the time. So it is very important to design a system to support fast recovery, and in terms of AI ML algorithm design, it is important to consider how to integrate this recovery operation in the algorithm from the beginning. Let me conclude today's presentation. I have talked about AI use cases and 3 things to consider in applying this AI ML technology to mobile networks. That is, utilize domain knowledge as much as possible, development of sophisticated digital twin, and make AI ML friendly system architecture so that unleash the full potential of AI and ML technology. Thank you for your attention.
Yep. Thank you very much, Seung-ju, for the nice presentation. I think you well summarized the challenges to unleash the full potential of AI, ML in wireless communication systems. So in the interest of time, I think we can take only one question. So one question from the board is in 2G through 5G, we see still call drop rate is one of the problems that need to improve for network performance. Can AI/ML improve call drop rate in mobile network? That's the question.
Thank you for your question. As you said, the call drop is one of the main factors that annoy the mobile users. No one wants to experience a certain call drop, and there are many reasons for a call drop. It may occur during handover or due to hardware failure. Surely, AI and ML can help improve the call drop rate. In my presentation, I introduced AI-based anomaly detection and AI-based root cause analysis. Using anomaly detection, you can detect the cells in which a certain kind of performance shows abnormal behavior. So you can find the cell with a high call drop rate by this anomaly detection function. Once you detected anomaly cell, then you can check what is the main reason for this high call drop rate by root cause analysis function. Reasons can be the handle failure or hardware failure or parameter change. Anyway, in this way, the AI and ML can contribute to improving the network performance.
Okay, good. Thanks again. We'll see you again soon in the panel discussion. Okay, thank you.
Okay, thank you.
Okay, then next speaker is Professor Sim Byung-hyul from Seoul National University. He's going to provide a presentation on deep learning-aided mobile detection and the beamforming for mmWave and terahertz communications. So Professor Sim, so it's all yours.
Hello everyone, my name is Byung-hyul Sim from Seoul National University. It's my great honor and pleasure to have a chance to present in Samsung 6G forum. And today I'm going to talk about the deep learning aided mobile detection and beamforming for mmWave and terahertz communications. So before talking about the main topic, I'll briefly go over today's wireless communication systems and mmWave communication and beam management in 5G and R. And then I'll discuss the computer vision aided beam management for 6G wireless communication. And then finally touch down the open issues and future research directions. As we all know, wireless communication has changed our life dramatically. So these days, in our office, in our home, in our when you're moving from the one place to the other, we all use the cellular phones, and then you can basically do everything using the cell phone, like voice call, SNS, banking, shopping, gaming, ticketing, to name just a few. And then if you briefly talk about the mobile wireless trend, then in old days, our wireless communication was just a voice-centric communication. But after that, we moved to text-centric, and these days we are using contents-dominating communications. So when you talk about contents, it can be YouTube, Instagram, TikTok, Netflix, some games, streaming games, and so many different kind of contents actually we are using. And especially content generation is much easier, so that we are seeing that each individual people are using their own channels, using a program like a YouTube. And then in the future down the road, we'll have a more emerging application like AR, VR, XR, and metaverse, and glass smart factory, to name just a few. And then the moral of the story is that in this application, record data rate is way higher than the data rate of the conventional services. Actually, to improve the data rate was one of the main issues, main challenges in wireless communication industry. To support the emerging applications, we should have more improved data rate. So that if you take a look at the figure below, then actually the data rate, maximum data rate, increase in a exponential scales. Y-axis, by the way, logarithmic scale, so that in each generations, we have new application, and in order to support that, our systems, wireless systems should support way higher data rate than the previous generations. The impact, how to improve the data rate, basically we have three directions. The first direction is to improve the spectral efficiency. Basic idea is for each unit bandwidth, we are sending more bits of data. So that spectral efficiency improvement technique includes the high order modulation, powerful error correcting code, spectral efficiency maximization like OFDM system, and resource allocation scheduling, and many more. This kind of technique actually has been successful to some extent, and then it was the main topic of wireless communication for the last 2 to 3 decades. Another direction is the cell densification. If you take a look at the hexagonal area in the left-hand side, and if you somehow divide these guys into the several pieces, like in the right-hand side, 7 pieces, then under the some assumption that there's no inter-cell interference, we can recycle, we can reuse the frequency band of the whole area using the left-hand side, so that we can increase the data rate in proportion to the number of divided cells. And then in these days, ultra-dense network is also one of the hot research issues for the 6G communications. And then finally, more important and then direct way of improving the data rate is to increase the bandwidth. So that if we have a more bandwidth, then definitely we can have a data rate proportional to the bandwidth. And then many real-world problems actually can be solved by increasing the bandwidth. And then impact in 5G to support the emerging applications. We introduced the higher bandwidth. The frequency range 1 is 3.5 gigahertz band, but FR2, frequency range 2, we started to use the 28 gigahertz band, which we call a millimeter wave band. It offers actually colossal bandwidth, but there are some practical problem coming from the physical characteristics. In order to do millimeter wave communication, first of all, we have high path loss, and the millimeter wave communication is sensitive to the rain attenuation and atmospheric attenuations, and they also have a strong directivity. And then the path is sparse in the angle and delay domain, so that usually we mainly have meaningful energies on the array path. And then in case non-array path, we have only a few. So to deal with this kind of problem, in particular path loss is increasing quadratically with the carrier frequencies. From the basic free flow, we see that the received power is quadratically decreasing with the frequency, so that if you compare the 3.5 gigahertz and then 28 gigahertz, then basically millimeter wave in 28 gigahertz decays 64 times more than the FR1 in 3.5 gigahertz band. So that we need somehow an operation called beamforming to compensate the path loss. Basic idea of beamforming is to direct the transmit power to the mobile devices. To do so, we need somehow control the phase and amplitude. For example, for a given azimuth angle theta and elevation angle psi, the directional beamforming vector is constructed by the canonical product of the two steering vectors. Then we need to somehow identify the azimuth angle and elevation angle. And how do we do that? In 5GNR, we introduced the special block called the synchronization signal block to support the beam domain processing. So if we briefly talk about the 5GNR beam management, basically it consists of two steps. To find out the code word aligned to the direction of mobile, we use the beam sweeping and beam refinement stages. In beam sweeping, the basic idea is to transmit multiple beams carrying SSB to different directions. So if you take a look at the figure below, we have 8 different directions, and in each direction, we are sending the SSB. And then mobile measures the RSSI, receive signal power, and then transmit feedback the index of the strongest beam, transmit beams. And after that, in the beam refinement stage, to narrow down the beam directions, base station transmit beams carrying the CSI-RS, some reference signal, to the range identified the first step in the beam sweeping stage. So this two-stage handshaking process, base station can identify the direction of the mobile and then send the transmit beam to the direction of a mobile. That's the way things are going on in 5G now. But if you take a look at some drawbacks, then first of all, there's a mismatch between the predefined beam direction and the real directions, because we are using the finite number of codebook elements. In particular, in 5G, we use DFT-based codebook, so that fundamentally we cannot avoid the quantization errors. And in case of if you use 64 DFT with some linear array structures, then each code, each beam direction covers around the 6 degrees. So there's fundamentally the error around the 3 degrees in the worst case. And then even with the slow movement of mobile, beam direction can be misaligned. In this case, beamforming gain is reduced significantly. And then in case of beam failure, whole process should be started over so that it will be certainly big overhead for the systems. On top of that, power consumption and connection latency caused by the complicated beam management is also an issue. For example, when you try to support the ultra reliable and low latency communications, beam refinement stage, in each beam refinement stage, reference signal transmission period is 10 milliseconds, so that it basically do not meet the URLC requirement. So all those kind of real-world problems, deployment of the mmWave communication is a bit slow in North America, Asian countries, and European countries. And then to make things worse, situation will not be getting any better in the teraband communication because the directivity is much stronger and then path loss will be much higher. So that actually there might be some extension and modification like a larger code book or larger transmission power or more base station, more complicated handshaking, or we are just focusing on fixed wireless. It can be some modification, but none of this seems to be the easy and simple way. So that based on my consulting on many companies and then based on my research experience, I learned a lesson that entities are not to be multiplied beyond necessity. We call Occam's razors. So moral behind this story is that if things are too complicated and yet inefficient, then that might be not the right answers. So when you have a problem or phenomenon, then simple description is likely to be the right one. So from this dictum, what can be learned from that? Maybe things are too complicated and that is not the right answer, then we might consider the new directions. So that's why it's time that we need to consider the computer visions. Computer vision is a very powerful tool to interpret and understand the visual scenes. And in particular, recent advances in deep learning significantly improve the quality of the computer vision tasks. So in many computer vision tasks, actually, like object detection, semantic segmentation, and image classification, computer vision surface outperforms the human level performance by a large margin. And then it is very effective tools. So basic setup of the computer vision is that we use the sensing device like RGB camera, LiDAR, infrared laser. So there are so many sensing devices. And then using the sense data, we do deep learning processings. As a deep learning model, we have a bunch of actually bewildering variety of the DL model like CNN, LSTM, Vision Transformer, and so on. And then Beijing deep neural net architecture-wise, also we have so many options. So we use the deep learning-based computer vision model for the sense data, and then we do computer vision tasks like object detection, scene classification, gesture recognition, and so much more. So we apply this idea into our beamforming control. So basic setup of the computer vision aided beamforming is that we generate sharp beam by the help of the computer vision. So what is the main step? First of all, we extract the mobile object. In our actually simulation and in our test, we set up the person holding a cell phone as a mobile object. But it can be different things like a small base station, drone, relay, IRS, Wi-Fi access point, so many more can be a mobile object. And once we identify a mobile object, then we extract angles. Angle can be azimuth and elevation angle, and also distance. Extract from the depth information. So in first step, we need to do object detections. Goal of object detection is to detect object of interesting classes. Again, we set the person holding a cell phone as our target object. And then in the object detection, we use bounding box to identify the class of object, and also location, and then also how competence it is, competence scores. So in step 2, once our target object is identified, we do localizations. For the centroid of the bounding box in the rectangular box in the figure below, we do find out the location in a form of the 3D spherical coordinate. And then we first identify the object, and then we narrow down, we find out the 3D localization. Then the next step is the base station generate the very narrow and accurate directional beams toward the direction of a mobile. Among many, there are many different kind of options, implementation options, but I'll just show you one simple implementation options. In this scenario, first of all, we borrow some step of 5G beamforming like beam sweeping. So in the first step, we perform the coarse identification of mobile using the beam sweeping. So in beam sweeping, as I mentioned, we do log coarse identification of the mobile object directions. And after that, for the physical area designated by the coarsely identified regions, base station captures the image using the camera attached to it. And then BS identify the mobile target mobile object and its location using the object detections. That is all done by the processor attached to the base station. And then in step 4, we just generate a very narrow directional beams such that main lobe of beam radiation pattern is directed toward the mobile, so that without any quantization, we directly sending a bomb toward the direction of the target mobile devices. To test our idea, computer vision-based beamforming, we generated a special data set called the vision object for beam measurement. So basically what it did is our group of students in our group actually took a picture in very diverse places like a classroom, libraries, the basement, and so on. And then we generate 135 pairs of RGB and depth images. Using that, we could do object detection and then the localizations. And then as an object detectors, because time limitation, and then in order to test our idea simply, we used the off-the-shelf algorithm called the efficient depth. And then we did some beam measurement simulation setup. So with the 64 transmit and 4 receiver mmWave MIMO systems, and then we used the indoor path loss model. And then we also compared the 5G NR beam measurement schemes with DFT-based beam codebook. And then this is basically the object detection and localization performance. If you look at the table in the middle, then you see that in most of cases, except for the very few corner cases, the object detectors can detect the mobile devices very accurately. And if you take a look at localization errors, then localization error of the computer vision-based beamforming is way accurate than the today's 5G beamforming. And then based on this result, we also evaluated the data rate. And then basically, if you take a look at the figure in the bottom, then the base station is located in the reference point in 00. And then you can assume that the mobile device is located any place. Then clearly in the right-hand side in 5G beamforming, in case of the angle is not fitting with the transmit angles, transmit beam direction, then there is sharp drop in the data rate, whereas the proposed computer vision-based schemes does not suffer such kind of behaviors. And in general, the data rate performance is much higher than the 5G codebook-based beamforming. But we have many research directions down the road, so I'll briefly go over some of them. First of all, computer vision-based beamforming is free from the discretization errors. That's a good news, but it depends on the resolution of the sensing devices. One good news, I believe, is that considering the rapid development of the CMOS sensor technologies, down the road, we will have a better pixel resolution, better sensing devices. And another direction is we can use the multimodal sensors like camera plus LiDAR, camera plus lasers. Those kind of multimodal devices will be also very effective. And the object detect perspective, I said we used the off-the-shelf algorithm. But if you take a look, then we should have so many training, validation, and test the data. So it is quite a big challenge, but we'll consider in the futures. Basically, by designing the object detector specialized for the computer vision-based beamforming, the quality will be much better than the off-the-shelf algorithms. Mainly because the task is requires only a few classes like a cell phone, relay, or small base station, and so on. So that this is very interesting future directions. The inter-device communication, near field is far more dominant than far field because relay distance is higher than the mmWave scenarios. So in these cases, we have need to not only know the direction, but also we should consider the distance as well. So that to consider the distance, sensing devices performance is very important. Those kind of aspect is also very helpful for our proposed approaches. Then latency perspective, since the location information is inferred from the captured image, we don't really need handshaking. And then the one thing is that if we somehow use a dedicated AI processor, designed with a small nanoscale CMOS technology, then certainly we can reduce the deep neural network processing. So those kind of things, we also get a help from the technology advancement in the futures. And the energy consumption perspective, we don't really need to send RF power and transmission powers. Instead, we are just using sensing devices and deep neural network. So complicated tracking and repeated beam measurement process is unnecessary. That is also good news for the computer vision-based beamforming techniques. In conclusion, in 6G, sensing and computer vision will be a major part of wireless communication. And then this is, in my opinion, very important directions. But there are so many open issues and challenges, and I wish it would be there are many interesting problems. And if you're interested in, you can take a look at the papers that I submitted below. With this, I conclude my presentation. Thank you very much for your attention.
Okay, thank you very much, Professor Shim, for the very nice and interesting presentation. I love the idea of computer vision-based beam management. So in the interest of time, we can take one question. Can you give us another example where a sort of the sensing can help to improve the performance of wireless communication systems?
Okay. These days, the first observation is these days we are seeing the great phenomenal improvement in the sensing devices, resolution and quality in camera CMOS devices, LiDAR, and so many things. And in fact, we are observing from the autonomous driving in Tesla or electric vehicles. And then actually, indirectly, we are seeing that those kind of sensing devices now quite reliable, and then we can accurately use it in estimating distance and angle and so on. So that, in my opinion, so far all the control mechanism in wireless communication is based on anyway handshaking and radio frequency transmission. In all the control channels, what we did is we send a signal and then mobile device receive it and measure it and send it back in a feedback mechanism. But those kind of things, if you think carefully about it, then we can replace with the sensing devices. And the good thing about sensing devices, for example, in camera, we can just use the camera and then we don't really need to get any feedback from the mobile devices. The camera captures the imaging and then using the very powerful AI technology, they can for example, find out the interference source, what is the best path, what is best scheduling, what is best resource assignment, so on. So that I think down the road in 6G, it's time that we need to aggressively consider the sensing device as a part of the communication system. And then if you have some more imagination, maybe you can think like this in a vehicle to communication system, for example. I'm in a hurry. I need to go to the city or in 10 minutes. And then there's a big traffic. Then I just do pricing and negotiations. I just do the very quick messages sending to the nearby vehicles. And then if they have some time room, they get money and they just change their lane to the first lane to, let's say, second lane, and I go straight. And then I just, satisfy my mission, my quality of service, and the vehicle nearby me also satisfy their, satisfaction, and then we can do happy solution using the sensing devices. So I think the usage of sensing device in the future 6G communication will be much more wide and much more diverse, I believe.
Okay, yeah, thank you very much, Professor Shim. I think it's very exciting to have such potential a lot. So it's time to move on. So we will see you soon again in the panel discussion. Thank you.
Sure, thank you.
Again. Now, last speaker of the afternoon session is Professor Xu Jin from Southeast University. So he is going to give a talk on deep learning-based CSI feedback in massive MIMO systems. So Professor Jin, the floor is yours.
Hi, I'm Shi Jin from Southeast University in China. It is my great honor to attend the first Samsung 6G forum. In this talk, I will give an overview of the deep learning-based CSI feedback. In this talk, I think I will firstly introduce the background. The 6G communications should include the enhanced QoS techniques in 5G and some new technologies, such as AI, race, and enhanced massive MIMO. In massive MIMO, the knowledge of the accuracy channel state information at the base station is essential to optimize the performance gains of massive MIMO. In FDD MIMO systems, the downlink CSI is estimated at the UE and the feedback to the base station through uplink, thereby occupying a larger overhead. Conventional CSI feedback methods are based on the codebook and comprehensively sensing. This approach has some problems, such as sparsity assumptions of channel, high complexity, and low accuracy. In the past 10 years, deep learning, DL, has achieved a great success in many areas. Inspired by its success, DL has been introduced in wireless communications. Our work, DL-based CSI feedback, has been a popular topic in 6G research. For example, DL-based CSI feedback enhancement has been selected as the first used case in 3GPP R18 study items. That is the first release of 5G Advanced. Next, let me show some of our recent work on DL-based CSI feedback works. First, I will introduce the first work that introduced the DL to CSI feedback. That is SysNet. In computer vision, an autoencoder can effectively compress the natural image. Thereby, we propose the basic architecture adopted in DL-based feedback, borrowing the idea of the autoencoder used in image compressions. The SysNet frameworks regards the downlink CSI as a spatial type of image. This approach can learn transformations from CSI to codeword and its inverse transformation. In these architectures, the CSI compressions is realized by reducing the neural number of the fully connected layer. At the decoder, the CSI is first recovered by a fully connected layer, and then refined by a refinement block. This table shows the feedback performance. We can see CSI SysNet clearly outperforms the other algorithms. Novel network architecture design can further improve the CSI feedback performance, such as the SysNet Plus. It adopts a large convolutional kernels and then adjust networks to improve the performance of residual structure. These figures and the table shows the performance and the parameter numbers of SysNet Plus. We can see our proposed SysNet Plus outperformance SysNet for indoor and outdoor scenario. The expert knowledge, that is the correlation, can be exploited to improve the feedback performance. For example, we can consider the multi-domain correlations, such as the time correlation, partial bidirectional channel correlations, and the correlation among nearby user CSI. The first correlation is a time correlation. In a time-varying scenario, the used location is not fixed. However, the user's moving distance with a short time is small. Therefore, the environment around the users does not fully change. At this time, the CSI at adjacent slot exhibits a high time correlations. Considering this kind of correlation, the CSI of the time-varying scenarios can be regarded as the sequence data. The next correlation is the partial bidirectional channel correlations. The single propagation environment is the same for the downlink and uplink. Therefore, the bidirectional channels hold partial correlations. The accuracy of the reconstructed downlink CSI becomes better if the uplink CSI is exploited. The next correlation is the correlation among the nearby users CSI. Based on practical measurement of the of our studies, the channel's correlation is very high for all close by users. Therefore, the CSI correlations among nearby users can be utilized to improve the feedback accuracy and reduce the feedback overhead. In the practical systems, the CSI is feedback in the form of the bit streams. If the encoder's output, such as 32-bit floating point code word, is directly feedback, the overhead is very huge. Therefore, the code word needs to be discretized before feedback. Based on the relevant studies, the values of the most code word elements are almost near zero. Therefore, a non-uniform quantization named the Moore law quantized is introduced to the CSI code words quantizations to meet the above requirements. Once receiving the quantized code word, the base station first refines the code word by an offset neural network. The table shows the NMSE performance of the proposed quantization method for different scenarios. In order to optimize the CSI comparisons jointly with the quantizations, we can set the quantization gradients of the quantization operations to 1. The above works assume that the user directly feeds back perfect downlink CSI to the base station. However, the CSI is estimated from downlink pilot signals. Here, we propose the downlink-based joint channel estimation and feedback framework. As shown in these figures, the framework of CEF-net combines the communication knowledge with the neural networks. The cost downlink CSI is first estimated by some simple algorithms, such as a least square estimation. The framework pilot comprehension and feedback neural network, PFNet, regards the channel estimation and feedbacks as one modules and directly compares the received pilot signals with a neural network based on encoder. This table shows the NMSE performance of the two proposed networks. We can see this CEF-net and the PF-net can both recover the channel well from the noisy pilot, although there is a difference in reconstruction performance and the complexity between them. Next, we will introduce some practical considerations. Some practical communication systems need to adjust the number of the feedback bits according to the different scenarios. In practical systems, the CR needs to be determined automatically. A classification modules can be added to the feedback to select the suitable CR in accordance with the CSI. Then, lightweight multiple rate frameworks can be adopted to compress the CSI. The feedback performance improvement is at the expense of the neural network complexity. To reduce the complexity of DL-based feedback, some compression methods are being adopted. For example, we have the following 4 solutions. The first one is the neural network weighted pruning, and the neural network weighted quantizations and binarizations. The third one is the efficient neural network architecture design. And the last one is the knowledge distinguish. The above works are conducted on simulations. When deploying DL-based feedback to practical systems, data collections and online trainings should be considered. For data collection, we need to consider that the user network performance depends on the number of the CSI samples used during neural network training. The straightforward data collections approach requires the users to store many CSI samples and then occupies the uplink transmission resource. For online learning, online trainings, we can use the transfer learning, meta learning, and free rate learning, online learning, and the gossiping learnings, and so on. For the standardization, we can automatic based feedback frameworks need to completely change the existing CSI feedback schemes. We propose the AI-based CSI enhancement strategy, which directly refines the received channel code words at the base station by neural networks. Okay, next I will introduce the future research directions of DL-based CSI feedback. To accelerate the deployment of the DL-based CSI feedback in future communication systems, such as the 6G, many challenges must be considered. Here, we list some of them. The first one is the CSI data set for realistic systems. More existing works use the data set that adopted the cost 2,100 channel models. The channel distributions simulated by software cannot exactly describe the realistic systems. Moreover, how to collect the CSI in practical systems is a difficult task once the neural networks is deployment. And the second one is the trade-off between the performance and the complexities. Users with the different computing powers are equipped with different neural networks adapted to them. Consider the dynamic available computation powers. The feedbacks neural networks need to be executable for at a different to permit a performance complexity trade-off during inference. And the third one is the generalizations. The envelopment of a cell will change over times. Therefore, how to generate a neural networks with higher generations is one of the major challenges in DL-based CSI feedback. So, for example, we can consider design the data set to cover the all channel distributions. And we also prefer the online training. Okay, I think that we need to consider more directions, such as the effect on the standardizations. The effect of the DL-based CSI feedback on the existing standards needed to be evaluated. For example, can we use this one in 5G systems? And the high-speed scenarios is also an interesting one. Mobility of the users becomes higher in the futures. The channel agents is a phenomenon and leads to a large drop in system performance. And we need to consider the challenges for in these scenarios. And we can also consider other emerging technicals. And many new technicals, such as the RACE and extra large scale massive MIMO, which can also, because are introduced to communications and are also regarded as the potential key technologies in 6G. So the CSI feedback combined with these new technicals need to be exploited. So from the above the introductions, I think we can see the different directions in CSI feedback. I think it is now a new a good topic for the 6G research in the future. Thank you.
Okay, thank you, Professor Jin, for the very nice presentation. So it seems that AI ML-based CSI feedback is one of the most promising use cases when it comes to applicability of AI ML to wireless communication systems, especially in the massive MIMO systems. So let me take a few questions from the board. The first question I have is, you mentioned the high-speed scenarios as a future research direction of AI/ML-based CSI feedback. So do you have an idea how we can tackle this problem?
Okay, thank you so much for your, this is a good questions. I think high-speed scenarios, we also, I think in our life, we, for example, in a high-speed railway, and there are other cases. So in these scenarios, we think the decoder of the base station must not only be able to reconstruct the channel state information accurately, but also predict the future CSI, not the current CSI, to reduce the influence of the channel aging. And the deep learning-based feedback method should be designed by considering the properties of the high-speed scenarios. For example, the user in these scenarios usually move on a fixed path, and because it is a high speed, so you cannot move your directions arbitrarily. So usually on a fixed path, so such as in rails. Because in these cases, I think the environment around the fixed path is usually long-term stable. So we can also use the AI or ML to predict the CSI, and so maybe it is solutions for the for these scenarios. Okay.
Okay. Yeah, it should be another interesting research topic.
Yeah.
Okay, then another question is also on the future research directions in your package. So you mentioned a performance complexity trade-off during the inference, considering the dynamic available computational power. Then the question is, how can you assess dynamically available computational power? Do you have an idea?
Okay, thank you. I think for this performance and complexity trade-off, for example, we can, for certain users, the available computation powers varies dynamically. Therefore, the feedback of the neural networks need to be executables at the different ones, such as the neural numbers in a fully connected layer to permit performance complexities trade-off during the inference. I think specific hardware such as GPU or TPU need to be designed and used for the baseband processing in 6G. Therefore, the available computation powers for baseband processing can be accessed in advance. However, this power cannot be fixed for all times. Therefore, I think we should define some scenarios in advance. Then, available computation power in each scenario is different, and then UE should need to select the suitable neural networks according to the different scenarios. So it means we should, for the different scenarios, we should use the different computation power, and then depends on the conditions which we choose the different solutions. That's it. That's my ideas for this case.
Okay. Yes,
Okay.
sounds interesting. Okay, thank you very much again, Professor Jin. We will see you again in the panel discussion. Okay?
Okay. Thank you so much.
Thank you. Now we are going to have a 10-minute break. After the break, we are going to have the panel discussion on the network AI. Please stay tuned. Okay, see you soon again. Thank you. Okay, I'm back. Is everybody enjoying presentations and discussion on state-of-the-art technologies today? You must be. So now it's time for panel session on network AI. So let me introduce Seung Choi, who is going to coordinate the panel discussion today. Seung, please go ahead.
Okay, Eddie. Thanks very much for your introduction. So, okay. Yeah, so I'm Seung Choi, the head of Advanced Communications Research Center at Samsung Research. I'm very honored to moderate today's panel discussion on network AI towards 6G. So before starting our discussion, let me briefly introduce our distinguished panelists. In fact, they gave a talk earlier today and kindly agreed to serve as a panelist as well. So first of all, Professor Tarik Taleb from Oulu University, Finland. Tarik, good morning to you. Can you say hi to the audience?
Hi. 안녕하세요.
Yeah, good to see you. Thank you. So the next is Master Seungju Mang from Networks Business Unit of Samsung Electronics. Seungju, please say hi.
Hello, nice to meet you.
Okay, nice to meet you. I look forward to a great discussion today. And the third is Professor Byung-hyo Shim from Seoul National University, Korea. Byung-hyo, please say hi to the audience.
Hi, thank you for having me.
Okay, great, thank you. Well, actually, your bookshelf with all the books look great, actually.
Thank you.
Thank you. Finally, Professor Jin from Southeast University, China. Hi, please say hello to the audience.
Hi, nice to meet you.
Okay, nice to meet you. Great, so okay then, now I think it seems like we are all set to start our discussion. So before starting interactive discussion with the panelists, I would like to give you some general overview to facilitate the discussion. So we all know that AI ML has been utilized in many different areas, while some of them are affecting our daily lives today. In fact, this technology continues to develop, and some keywords in the AI ML tech trends include hyperscale AI, reinforcement learning, and explainable AI. In fact, I will try to touch explainable AI as part of our panel discussion later too. Apparently, more and more industries are trying to employ AI ML technology to enhance the performance while reducing the human efforts and costs. Such industries include healthcare, retail, automotive, advertising, and manufacturing. Given that Samsung has businesses in many different areas, we are also trying to apply AI ML technology in our businesses as well. Apparently, wireless communication is not an exception. Given that wireless mobile network has become too complicated to manually manage and operate, AI ML has been applied to this area too, especially to reduce CapEx and OpEx. As shown in the slide, AI ML is being utilized to predict the cell coverage and performance. Especially performance prediction can be utilized for network planning. And also, it can be utilized to monitor the network once the network is deployed, and also particularly, anomaly detection and root cause analysis are examples which can utilize AI ML technology today. And also, during the runtime of the network, AI ML can be utilized to optimize the network performance. Some particular examples could include load balancing and energy saving, as Seungju presented today. In fact, 3GPP, which is the standardization organization for mobile communication, started developing standards for AI ML usage. The very initial effort started with 5G standardization in Release 15, especially to develop a special network function called NWDAF, or Network Data Analytics Function for AI/ML function in the 5G core network. As you might know, 3GPP just started working on 5G Advanced, which is the next version of 5G, or kind of bridge standard between 5G and 6G, beginning Release 18 very recently. Particularly, 3GPP started looking at AI/ML applicability in the RAN or base station side as well. Also, AI/ML support for media, service, and model transfer is being studied as well. Well, actually, this slide shows the landscape of 3GPP's AI/ML standardization. Basically, 3GPP will standardize the use cases and architecture supporting AI/ML services. Also, data formats for AI/ML model data, metadata, and intermediate data, as well as supporting protocols, will be standardized. On the other hand, as part of 5G advanced standardization, 3GPP assumes the current 5G architecture and potentially minimal architectural change. Moreover, AI/ML algorithms are out of 3GPP scope, but reference algorithms could be discussed within the standardization group. In this figure, I would like you to pay attention to some of them in here. We heard earlier today that Professors Byung-Hyo Shim and Shi Jin talked about beam management and channel state feedback, respectively. 3GPP is looking at such topics as a study item as well. Master Seung-Ju Mang talked about network energy saving as part of his talk, and it is also being considered within 3GPP today. Finally, the evolution of AI/ML supporting network functions will probably enable the service of services, which Professor Tarik Taleb talked about in his keynote speech. So now, what's the next towards 6G? We target comprehensive, end-to-end, and native AI for intelligent 6G. As I presented earlier, today, AI/ML is being utilized for network management and optimization in a limited manner in the current network. However, in 6G, AI/ML will be used in all the layers, even physical layer, and all the nodes across user equipment, radio access network or base station, and core, and even application supporting cloud. Now, I believe we are ready to start our exciting discussion. In fact, I collected possible questions and discussion points based on the questions which the participants posted at the forum website earlier. The discussion topics are categorized into 4 groups, namely native AI in 6G, and cost aspects, and third, interoperability and standardization, and finally, trustworthy AI. Now let's talk about each topic in the following. So the first is native AI in 6G. We are claiming that 6G should be AI native, while earlier generations were not. Note that mobile communication technology has been traditionally developed based on solid math-based communications theory. Given that many people are questioning about the utility of AI/ML technology, particular questions in this topic can include the following. So I'll read through the questions which I would like to address in this discussion. So the first question is, how will AI/ML influence the system design of 6G? The next could be, what will be the role of AI/ML in 6G wireless systems? The third is, what are the intermediate steps to be taken in the next few years, especially 5G Advanced in release 18 and 19, that are essential for realizing native AI in 6G? And finally, given that AI/ML is being introduced in 5G Advanced, in order to comfortably introduce AI native 6G, what should be 6G like? So for this topic, I would like to hear the opinions from our colleagues, first from academia. So Byung-hyo, can you start first? What do you think about these questions?
So first of all, I just want to say that the AI technology is way different from our conventional approach called the Shannon theorem or Shannon principle, in the sense that all the AI is basically learned using the big data sets. It's data-driven, meaning that unless we have enough data, we cannot have a meaningful inference on the problem that we want to solve. So that the network architecture that we have developed for the last 2 to 3 decades, and then the AI principle is in fact way different. So that in the long-term perspective in 6G, we need to somehow consider from the scratch all the fundamental change in our network architecture and cellular system, such that those kind of aspects. First of all, we should have a training, we should collect data, we should train the network, train the functions, and then we, using the AI, we do inference. Of course, that cannot be the everything for the network, but main part of our future network should be designed in a way to control and adapt the new AI technologies, such that our 6G paradigm should be started, I believe, not incremental. It should be started from the scratch.
Okay, sounds good. I think you talked about data collection and network architecture and so on. Apparently, as I kind of mentioned, as part of 5G Advanced, some form of that kind of change is happening already. Of course, whether that, how far we can go with 5G Advanced and what should be done as part of 6G, standardization, I think it remains to be seen.
I think we are now in release 18 in 3GPP and 5G.
Right.
We are also looking at some part of the functionality. We are trying to use the AI technology. I know that. And then I think because this is, I think, effectively first step toward using the AI technology, so that definitely in the standardization process, again, standardization is way different from the academia. We can do research, some assumption, you can write a paper, but standardization should be more strict, should look at more comprehensive way, and then it should work even in the corner cases. So that, I believe that we can get a good lesson, especially the industry and standard body will get a good lesson and insight and some lessons from the release 17 and 18 processes, I believe. That can be starting point of the new revolutionary change in the 6G, I believe.
Yeah, so especially in this panel, we have 3 professors, right? So, and also, Byung-hyo, you mentioned, the role of industry and academia. And well, actually, you guys, in academia have, I think, freedom, to consider whatever you want, and also, without much worrying about the reality. I think, being now I have apparently long academic background. I was a professor for 17 years, until 3 years ago. I think I enjoyed that kind of freedom before. Now I don't have much that freedom anymore. But I think, in one sense, we need to consider the reality and practical constraints. But at the same time, I think professors, you guys should continue to kind of do research without too much worry about that. I think I do agree with that. Based on that kind of approach, you can imagine a lot of things. Something which might look impossible now, but we are talking about 6G and 10 years down the road, right? And I think you have to look at all different possibilities for sure. Yeah, it's a good point. And yeah, good. So what do you think, Shi? You also kind of talked about physical layer, channel state information transfer. And do you think what do you think should happen towards 6G?
Okay, I think for 5G advanced, the AI ML may not make much modifications to the system designs. It is mainly realized by replacing some single blocks or multiple blocks of the communication systems. I mean, for the physical layers with AI models. For example, we use some designs for the channel estimation by using the DNN and or CNN, and therefore it does not require any new signaling or procedures, as they only impact the implementation algorithms. However, in 6G, I think we should consider replacing the parts of the L interface with the AI models. For example, we just talk about the CSI feedback, and currently we just use the AI at the base station to enhancement the CSI feedback, CSI reconstructions. But for in 6G, I think maybe we should change the signaling over the air, and maybe it will help to utilize the AI. So in this case, I think new forms of the signaling and procedures should be considered to enable end-to-end the training. But this is not considered in 5G. And I also think different from the 5G advanced, I think in 6G, AI ML is more likely to substitutions in algorithms. It will play a critical role in the development of 6G across the design, deployment, and operation phases. Now I'll give some examples. For example, in waveform design, different forms of a single classic waveform choose, such as OFDM in 5G. But AI could enable learning the waveforms for different frequencies. That is not only make more efficient use of the spectrum, but also adaptable to the practical limitations of the transceiver hardware and the channels. So also for transceiver design, I think fully learned transceivers have the benefit that they are no longer need to undergo the very costly and time-consuming the traditional process of algorithm design and hardware implementations. I think maybe it's my ideas for some of the physical layer designs in 6G.
Okay, Shi, actually, I think you have many good points. You said that 5G Advanced considered to replace some of the algorithms in the traditional transceiver with AI ML model. I earlier mentioned that 3GPP is looking at CSI feedback and beam management. And also in the physical layer, they are looking at positioning and sensing as another study item too. So, as you said, these are kind of trying, approach to replace the existing algorithms with AI ML approach. It's a good point. And actually, towards 6G, I think we have to look at more possibilities, given that we are trying to make AI ML as a core part of 6G, especially even in physical layers. So I think you have a really good point. And also you mentioned waveform design, based on AI ML too. Yeah, actually, I don't know if you watched the video demo which was played during the lunchtime. As part of today's demo, we revealed or shared our recent progress with AI ML-based development. Especially one of them was called AI NC, where NC stands for nonlinearity compensator. So basically, traditionally, communication system have been assuming linear system, right? Channel linearity in the channel, linearity and in waveform and coding and so on. But apparently, if you take a look at the power amplifier, power amplifier has a lot of nonlinearity properties. And in order to avoid nonlinearity, we have been using power amplifier in the linearity region by backing off transmit power. But what we did was, by making transmitter transmit, boost up the power so that the transmitter transmit distorted signal, but such distorted signal can be compensated and at the receiver by utilizing AI ML technology. So I think it's a good example for utilizing AI ML to handle problems, in the nonlinearity region too. So I think we have to consider all different possibilities, especially by breaking, without considering the traditional assumptions of linearity, as I said. So that's a good point. Another thing is you mentioned end-to-end performance, right? Towards that, I would like to invite Tarik and Seung to talk about system architecture aspect. Especially Seung mentioned AI ML friendly system architecture in his talk, and also apparently Tarik talked about network system for service and services. And also, towards AI ML research of 6G, we have been talking about end-to-end AI ML, comprehensive AI ML, and we also talk about network compute convergence. And also, we also talk about split ML. So, a single ML model can be splitted so that inferencing can be done in different entities across the network. So that is, some of the ML function can run inside UE, while some of the rest can run inside base station or MEC or cloud and so on. So we are talking about split ML and so on. So yeah, so towards that, Tarik, do you have some specific ideas, regarding end-to-end AI ML things and also system aspect and so on?
Yeah. Well, again, really thank you for having me in this very excellent, actually, forum, which is organized by the first time by Samsung. It's really a pleasure to be here. As I presented in my talk, this vision of services, among the services or among key enabling services, actually AI, and I was referring to that as ubiquitous intelligence, and I explained that as think of it as a huge library of AI models which could be committed by different people, and then you choose the one which is most suitable for the service that you are targeting. And since actually this event is organized by Samsung, in my humble opinion, the biggest success of smartphones is not the phones themselves or the design of the phones, but actually the platform that these smartphones brought, the platform which is running in the back, where developers could commit their applications, put them, let's say, on Google Play Store or on alike. And then, it's up to the market to decide which application to become popular or not. Now, and because of this platform, we've been seeing lots of interesting and innovative services really coming to the market, services that we didn't see 10 years ago or even 15 years ago. Now, think if we adopt the same, let's say the same model for AI. So basically, let's say that Samsung, for example, will build a platform which will enable developers, AI and ML developers, to commit their models after training them, put them on this platform, and then it's up to the end users. End users could be operators, could be service provider, could be anybody who's interested or is in need of using AI. Imagine this platform is there, and then, as I said, AI developers committing their models, and then people, they are using these models, which are, let's say, tested, validated, against different metrics of privacy, security, and so on and so forth. And then the people, they are using them as per the need of the service that they are actually launching or they are actually targeting. And I think if we do it in this way, then the AI itself becomes just a service. And this is exactly how we can achieve, the topic which you have mentioned in the beginning, which is the nativeness of AI. So basically, 6G will be just a platform that can actually call on these AI models, use them, and these AI models, as I said, they will be coming from completely different entity. So that's, since you were saying that actually academics can dream and can think of things which are actually beyond, so that's exactly what really I'm hoping it can happen, let's say, in 10 years from now.
Okay, sounds good. So Tarik, do you have some idea about what kind of applications and services will benefit from the kind of application of AI ML in the future?
I think, in my humble opinion, there is no limit. Today's talks, they were talking about, for example, the radio access network, how it can benefit from AI. I think in your introduction, you mentioned that the core was the focus of AI application in the beginning. And I think this comes, the roots go back to, when we were talking about self-organized networking with all of these self-stars and so on. But then, there are lots of services that are using nowadays AI. Just think of me, I want to develop an application that needs certain customization according to the location of the, instead of developing that AI model and I don't have the expertise to do it, then I just borrow the AI model, which could be already developed by somebody else, targeting the location that I'm actually interested in launching my service. So there is no limit. And this is exactly what I was mentioning earlier. Once we develop this platform and we provide it, then there is no limit to what we can do with it. It's only probably, one's imagination that can be limited to that.
Okay, so actually, especially when we, by the way, we released our white paper, 6G white paper 2 years ago. Back then, as potential services enabled by 6G, we mentioned, truly immersive XR, extended reality, and also digital replica. And actually, we have been looking at this kind of services more and more, and apparently, this will require interaction between applications and communication support. And also, we just talked about sensing and so on too. Apparently, in order to support truly immersive XR, we might need to utilize AI ML for many sensing purposes too. For example, sensing of human body gestures and interaction and so on. And also for digital replica, in order to replicate real objects in the physical world, we need to sense a lot of things. And for the sensing and positioning, I think, again, we are trying to utilize AI ML technology to have better sensing and positioning capabilities. So, yeah, actually, again, coming back to end-to-end, beginning from the application part to down to physical layer, operation. I think we need to think about all the details, to make all this AI ML operation in a comprehensive manner. So,
yeah. And one thing else which I probably would like to highlight, I mentioned that in the talk. Sometimes we could make an AI model which is perfect, for the radio access network, but probably it will take a decision which is not optimal, let's say, for the core or for the service itself, the application which is being provisioned. And that's why there is need to synchronize between this AI, let's say, these closed loops, which are actually dedicated for each segment, And sometimes you may come up with a decision which is suboptimal for one segment, suboptimal for the other, but when you look at it end to end, then it becomes optimal. And that needs lots of training, and it needs also the understanding of the different segments which are actually involved into the end-to-end communication. This is a very interesting research topic, by the way, for those that are interested in working on AI and how you can make AI, let's say, useful, for communication.
Okay, sounds good. So, Seungju, do you have any specific opinion about this topic? As I said, you mentioned this AI/ML friendly network system and architecture too, right?
Yes, right. And I'm from the industry side. I think I'm more realistic than the professors. And I think, as I mentioned in my presentation, it is very important to design the system architecture such that it can support the AI/ML operation without any limitation. In case of 4G or 5G, because the system is designed without considering the AI or ML operation, and now we want to add some AI functions on top of our existing system, then we found that sometimes it is not easy to modify the software system to support the real-time interaction between the different network entities. In some case, the AI/ML function will cover the scheduling functions. For example, in massive MIMO case, the AI/ML function can categorize the users for single-user MIMO operation and the users for multi-user operation, and also AI/ML function can choose the user sets in slot basis is 1 millisecond or 0.5 millisecond basis, and to support that, the scheduling result from the AI/ML function should be delivered to the layer 2 back layer and layer 1 in real time. But if the AI/ML function is on the, for example, central server, then if the architecture design is considered from the beginning to support that operation, it is not easy to support that in real time. So in that sense, the system designed for AI/ML friendly is really important. And the another thing is that to consider the recovery mechanism, fallback mechanism, because the maintaining the system performance, the stable, is very important. And even with the rule-based algorithm, if we change some parameters such as some mobility parameter to control the load of different bands, but since there are so many interactions between users and the different performance factors, we cannot expect the performance change after applying the new parameter. So it is important to monitor the performance after changing the parameter, and as soon as we detect some degradation occurs, then we should fall back the parameter set to the previous one to recover the performance. By using that, the operator also can apply the kind of the adaptive operation, closed operation in their commercial network. And AI ML algorithm design. When we design the AI ML algorithm, we should consider how to incorporate that this kind of fallback mechanism in AI and ML function operation.
Yes, Seungju, thank you very much. I think you mentioned two very important things. The second one is, can we really, trust AI? I think it's related with our fourth topic. We'll talk about trustworthiness of AI. But you said that the system should be able to support the fallback mechanism, so that just in case AI does not work, we should go back to traditional approach or kind of bottom line approach or whatever. So I think it's a really important thing. And the first thing you mentioned, the system should be AI friendly so that AI function will work properly. When I heard about what you said initially, when we think about network core, especially 5G network core is service-based architecture, right? In there, we can introduce whatever network functions we want, and NWDAF, which I mentioned already, is being kind of defined and probably will be deployed in 5G or 5G advanced network in the future. I think along the same line, for 6G, we can do similar approach for network core side. But I think the problem is on the RAN side, because the RAN side is not service-based, is employing service-based architecture, and also it's not that easy to kind of break down network functions inside RAN side. I think what you said makes a lot of sense, especially in order to support very timely operation of the network. Probably we'll need to think more about it too. So yeah, thank you. So I think what all you said, I think are very relevant. I think towards 6G, AI native, 6G, I think we have to consider all of this, very carefully. So now, having said that, let's take a look at the second topic. So the second topic is about cost. So apparently cost involving data collection and model training and model inferencing should be carefully considered to judge the ROI, return on investment, of AI/ML. And in detail, while AI/ML heavily depends on data collection is not an easy job given the amount of data transfer, and data storage. Are there ways to reduce the incurring cost? I think that's the first question. And secondly, AI/ML model development is often limited due to the difficulty of securing enough quality data, or enough amount of quality data, I would say. What should be the solution to handle this problem towards AI native 6G? And finally, some AI/ML algorithms should run in a real-time fashion, but such operations might not be feasible due to the hardware limitation, hardware kind of capability limitation or computation limitation. Will this limit the achievability of AI native 6G? So Seungju, I'd like to ask you again. So cost is always one of the most important factors for real products and services. I also remember that you talked about difficulty of securing data for AI/ML training earlier in your talk. Accordingly, I would like to hear your opinion first. Can you share your idea about this issue?
Thank you. I think there can be the opposite way to reduce the cost. One is to reduce the amount of data to be required for training, and another way is to generate data itself. We can reduce the amount of data by using the technologies such as transfer learning or meta learning. For example, if we can create a create a common model for different morphologies like dense urban, suburban, or rural, then it will be possible to tune the model according to each morphology by retraining the model with small amount of data for that morphology. And for the generating the network data, one possible way is to use the digital twin. It is true that the data is anyway required in the process of tuning the digital twin to replicate the real network situation. But once it is tuned, the data required for AI model training can be generated through the digital twin. And also, we can obtain the virtual data by assuming a certain operation, a specific operation, such as turning off the certain frequency band in energy saving function. In general, it is difficult to test such an operation in commercial network because that kind of operation will cause the user experience performance to be degraded. But using digital twin, we can test any operation as we want, and we can also get enough data for that operation. Another way is to secure open data set for mobile network. As I said in my presentation, operators may not want to make their commercial network data as an open data set because the competitors may know about the advantages and disadvantages of their network operation. But once data is opened, the benefit they can obtain will be much higher than the drawbacks, because the lots of vendors, not only the major vendors, but also the small vendor startups can create innovative and disruptive AI technologies using that opposite data. So the method to make network data an open data set should be discussed in the standard body, including ways how to abstract data such that the sensitive information can be properly protected. And for hardware limitation, regarding the hardware limitation, I don't think that the hardware limitation will be a constraint on achieving AI native 6G, considering the speed of the software algorithm development and speed of hardware, the processor, the development. For example, when LTE was first commercialized in 2011, Galaxy S2 was the first smartphone to support the LTE, and the peak data rate at that time was 100 megabit per second. And the Galaxy S20 is the first smartphone to support 5G, and its peak data rate is 2 gigabit per second. It's 20 times difference. And even for base station side, Samsung already commercialized the virtualized RAN in Verizon and Vodafone. And in virtualized RAN, the complex layer 1 operation is implemented as a software on Intel CPU due to the powerful computational capability of CPU. And recently, technologies such as on-device AI have been developed, and in this, the on-device AI, AI algorithms are performed on smartphones instead of going through the centralized server. And for this purpose, the neural processing unit technology is also actively developed, which is optimized for performing AI operation. So I think hardware limitation can eventually be overcome by the technology development.
Okay, Seung-ju, thank you very much. I think you talked a lot about all of them, and I really appreciate it. Well, actually, regarding open data, collection, I really like the idea. Probably for that purpose, we need to persuade, our operators, right? And as you know, as a kind of company, we do have some data, from the operators, but especially, given that we have 3 professors here, for academia, it's almost impossible to get kind of, quality data, or real data, from the real network. So I think, to enable quality research in academia, I think we also, as a whole, need to work together to secure some open data, which can be used for future research. So I think that's very important. Let's think about how to achieve that all together. So I like all the professors to kind of claim that, to the operators too, so that they will be kind of willing to share their data with all of you, for your research. So
let me share one of my episodes when I did beamforming-based research. Actually, I wanted to design the computer vision-based algorithm such that it only detects wireless devices like a person holding the cell phone or a small base station or something. But unfortunately, I just used off-the-shelf deep learning algorithm. The main reason is because of data set collection. Usually, when you try to use the when you try to design a new deep learning model, then we should at least like 1 million data set or 200,000 so on. And then when I try to take an image of those kind of data set, my group of students was shocked and they said that it will take a couple of months.
Right.
And obviously it will delay things, and then because my job is more like a proof of concept thing, so that I decide, after some consideration, I decide to use the off-the-shelf, just the published work with the known data set. In that case, I can just use the data set as well as the learned parameters. So that, I mean, we can borrow those kind of idea, AI field idea to our wireless industry. In the future, obviously, when you try to design the new deep learning model, then certainly data collection issue might be one of the biggest hurdle in the problem. So that I think we can somehow collaborate all the mobile operators, network companies, and academia. If we work together and then make some common data set, then certainly our hassle and all the pain will be relieved, I believe.
Okay, sounds good. So Tarik, did you raise your hand? Do you want to say something about this?
No, I just confirmed that actually there is need for such kind of data. And to be honest, we do collaboration with vendors. And I recall there was one time that a vendor had actually very interesting data from operators in Europe as well as in Africa. And they want to compare how the network works, in a developed country and a developing country. We want to have the data, but then even if those that we were actually collaborating with, they wanted to share the data, but there were lots of legal complications. In the end, they couldn't. And the solution was that they actually hired my student as their employee. So then, he became the employee of that company, and then he could get access to the data and so on. But I mean, really one solution, which in my humble opinion, the companies like Samsung and the like can help a lot, academics, so they can do good research work. Since you have actually, access to this kind of data, it would be really interesting if companies like Samsung, reflect those data in a simulator, or let's say, can create some kind of small digital twin of the networks and then make those, via well-defined interfaces, accessible to academics. So then academics can just try their models and see whether the models, is accurate or not. Having access to data, if it is possible, for example, in Korea, it will be very difficult in Europe, for example, because of this GDPR rules and so on and so forth. So it really depends from a region to another one. And you can agree that there are lots of concerns with privacy and so on and so forth with that.
Yeah,
but absolutely, it is for the data, yeah.
Right, you're right. Actually, data collection and sharing, I think there are a lot of regulatory issues too. And Seungju mentioned just privacy, but I think that one can be probably handled by anonymizing the data and so on. But yeah, I think this is a really good homework. We need to work on all together. So let's see how it goes. So I'm sorry?
Yeah, I said even if you anonymize data, there are actually ways of knowing who is the data owner.
I see.
There are lots of research work on finding out, for example, from the mobility pattern of the person, that this person is moving from this location to that location every morning. Then you can say this person is living here and working there. So, yeah.
I see. Yeah, it's really tough question and tough problem to solve. Yeah, so let's try to solve all this all together. And you mentioned performance and complexity issue as part of your presentation, right? So can you share your thoughts about this more, regarding the cost and so on?
Okay, thank you. I think since most of the cost of the data collection comes from the myriad data in real systems. Because we focus on the physical layer design, we also need to set up demo systems, and then maybe it is a massive MIMO systems. We should cost some monies to set up these systems. But we collect data. We also cost a lot of time for the different scenarios. So I think in this case, I think establish a reasonable simulation platforms to generate the simulation data close to the distributions of real measurement data can reduce this cost. For example, we in 5G or 6G we use some just like the cost 2,100 models and other. For example, we also use the some of the SCM models. But for the AI design, actually we can mix the data and some simulations platforms. Then it generates the data. Moreover, I think the data enhancement technologies and the data generation models in AI can also be applied to generate a large amount of training data. And some learning method in AI, for example, incremental learning, do not require access to the historical data during trainings. I think it will, which further reduce the cost of the data storage. And on the other hand, I think it is also very important to improve the equipment performance or the channel state to reduce the bad effects of the imperfect measurement, such as the hardware imperfections, signal interference, and random noise. Data processing, just like some noise filter, can also be used to address these problems. And a series technologies in AI has been proposed to handle the problem of the surfacing data. Just like I think the VAE and GAN and so on, which efficiently expands the data set. Regarding the hardware limitations, I think the limitation storage or computations capabilities in most network equipment calls for the well-designed AI models with the high performance and low model complexities. I think the self-adjustment and higher generation models are also required to interact with the dynamic environment in real times. and which will enhance its predictabilities. Up to now, a large amount of AI enlightened wireless system design has been proposed to address the implementation problem of real systems with these hardware limitations. I think these challenges will promote the integrations of AI and wireless communications more in the future. Okay, I think this is my idea.
Okay, sounds good. I think you mentioned simulation. I think it's along the same line as what Seungju mentioned, in kind of regarding, digital twinning, and also, data augmentation and so on. And also regarding the hardware thing, so far, not just communication, but also for many application and services, we have been relying on very, compute kind of heavy servers in the cloud for AI modeling and inferencing and so on. But we are trying to make lightweight models so that these models can be run and in the device, in the smartphones, for example. So on-device AI is another very hot keyword. So assuming according because device and hardware development is kind of progressing very fast. I assume that what we worry today should not be a big problem eventually. So yeah, that's what I hope. I think in the interest of time, I think we have to move to the next topic. Actually, we have 2 more topics, but we don't have much time. So yeah, let's talk about the third topic. So it's about interoperability and standardization. Earlier, I explained what is happening with the 3GPP for 5G Advanced. Apparently, 6G technology should be standardized, but what about AI/ML? So which aspects of AI/ML in 6G should be standardized and what should be left open for proprietary implementations? One of the hurdles that could delay the introduction of AI/ML is multi-vendor interoperability issue. How can we guarantee performance of AI/ML-based designs from different vendors? And finally, details of AI/ML network designs are treated as assets of each company. Will this limit the type of AI/ML network that can be utilized in the communication network? For example, how can we utilize autoencoder type network between base station and mobile station without sharing details? This is about, again, I think industry-oriented question. So Seungju, can you take the lead about this discussion?
Okay. In my opinion, it may be difficult to standardize the AI/ML model itself. Even now, each vendor has developed its own scheduling algorithm for resource allocation, and which is one of the key assets of the vendors to make their system more competitive. So I think that the type of AI/ML use cases and input and output for each use case and signaling message format for reporting AI/ML capability, and also some interface format for data exchange can be candidates for standardization. And regarding the performance, even now in 3GPP, there's a commitment to Ram 4 that makes the standard for minimum performance requirement. So, and it defines the test items and measurement procedure for each item and minimum performance requirement for each item. So like this, in case of AI/ML, we should also make the minimum performance requirement to maintain the performance between different vendors to be similar, to satisfy the certain threshold. So even for now, each vendor should make their system or terminal to meet the minimum performance requirement standard to sell their product. And to this end, it is necessary to make the test scenario very carefully so that the performance in various environments and also the exceptional cases can be covered and also can be verified.
Okay, sounds good. Does any other panelist would like to add on this? Yeah, Tarik, yeah. Could you please be brief?
Yeah.
You know, we don't have much time, so.
All right, I'll try to be very brief. Well, the first thing that probably we would need is as we were saying earlier, maybe a digital twin or simulator against which, these AI models can be benchmarked, number one. Number two, I think we can get inspired from the design of the previous generation systems like 4G or 5G. For example, you know that in 4G or 5G you have equipment coming from different vendors. Let's say that you have a PDN gateway coming from Ericsson that needs to talk to a serving gateway which is coming from Nokia, but then they need to communicate among themselves via well-defined identifiers or numbers so they can set up the quality of service. And here I'm referring to QCI or 5QI, as identifiers which are actually well defined in standards. If I say QCI number 5, it means this much in terms of delay, it means this much in packet loss, and so on and so forth. So probably we have to define also KPIs, for AI models, accuracy, trustworthiness, and so on and so forth. And then when I say that this AI model is of this identifier, I don't know, AI class identifier of 5, then immediately I understand that this is going to give me this amount of accuracy, this amount of trustworthiness, this amount of privacy, perseverance, and so on and so forth. And I think in this way, if I have an AI coming from Samsung, with this kind of identifier, I will understand exactly what performance I'm expecting. So these are just some steps that probably we could standardize, the AI models, which will be coming from different vendors, and they need to communicate among themselves, somehow in coherence. Sorry, I was long, but that was in brief.
Okay, thank you. Yeah, does anybody would like to add about the possibility of revealing the AI model, given that a lot of companies treat AI model as their asset? I think it's a really tough problem. Byung-Yo, could you please be brief about this? Yes, please.
Yeah. In order to make the standardization of AI technology, you should make sure that it should affect both transmitter and receivers. In case you are just using the channel AI-based channel estimation, you don't need to worry about. If you really want to do some fancy scheduling in the base station side, that does not really affect the standardization. In order to standardize things, we should somehow think about the control signal, such that the base station side should send some signal to the mobile side, such that the mobile side decode it and then change their configuration. Or it should be an encoder-decoder pair such that without that, decoding cannot be fundamentally possible. So having said that, when you really want to standardize AI technology, what you should do is we should have some sort of agreement among companies. If some companies just argue that it is their priority, and then is their patented things and they cannot reveal it, then it cannot certainly be standardized. So that we need somehow some sort of discussion and agreement process in the standard body to really make things work in the standardization down the road.
Yeah, it's a good point, but I think the tough kind of situation is I thought that ideally, given that the AI model which base station would like to use and base station like UE or terminal to use at a particular site should be dependent on the location, right? So one possibility is whenever terminal or UE enters a specific area, it downloads the model from the base station and utilize the model at their location. But if base station vendors doesn't like to share the model with the UEs, then I think it's problematic. So I think it's a tough problem. I think people are discussing this, inside the standard body too. So let's see how it goes. And if you have really nice idea, please let us know. I think it's a kind of good chance to incorporate your idea into the standard. So yeah, I think in the interest of time, we have to wrap up. But I would like to briefly touch the last item very briefly. So it is about trustworthiness. Trustworthiness of AI model is often questioned since their behaviors are mostly unexplainable, and attacks to AI ML models are also reported. And I'm particularly talking about adversarial machine learning and so on. So I think I know there is a kind of generally big issue in all the AI models and AI application. So I don't think it's particularly a problem for wireless and mobile communication. But I think Seung mentioned fallback kind of mechanism. So I think we should make AI ML model behavior and kind of because we have anomaly detection approach already by monitoring the network performance based on AI ML model. Once some abnormal behavior is detected, probably we should have enforced the fallback mechanism there. So I think not just relying on a single model, we can rely on multiple model operations so they can kind of monitor each other and so on. So I think there could be multiple ways. And another thing is, as part of 6G security, we talk about zero trust architecture, where network entities do not believe or trust each other. So whenever they do some communication or transaction, they should authenticate each other in advance. Then I think probably we can make network even more secure, and AI ML model which rely on data collection and so on could be kind of more reliably operate. So I'm sorry. I think in the interest of time, I think we'd better stop here. I really want to hear your opinion, but I think we'd better stop here. And probably this last topic, we should be able to discuss it further in the next panel in another event, or potentially next year in Samsung 6G Forum. So I think we have to wrap up. So I will try to wrap up in our panel. So I'd like to tell you that, as you have probably seen and also agree, we have lots of unsolved questions and challenges, right, to realize AI native 6G, right? While addressing all these questions, especially three of you guys, coming from academia, might be able to produce many PhDs, right? So I believe that it was an exciting panel discussion to predict the role of AI ML in 6G and understand the challenges which needs to be tackled as part of our preparation for 6G. So I hope that we, across industries and academia, continue to work hard to tackle these challenges. So I'd like to thank all the distinguished panelists who shared inspiring ideas with us today. So thank you very much.
Thank you.
Thank you. I hope to see you in person in a near future. So thank you.
Thank you for the excellent moderation.
Thank you. Oh, so I think it's time to wrap up a day-long Samsung 6G Forum. We were very privileged to have 8 distinguished speakers who are world-renowned leaders in the mobile communication field from both academia and industry. We also had 2 exciting panel discussions about 6G air interface and network AI. As you know, we are working on 6G technology to bring the next hyper-connected experience for all, to every corner of life in the following decade. It will be a long and sweaty journey. This cannot be achieved by Samsung alone and will require the collaboration across industries, academia, and governments alike. We at Samsung intend to play a leading role in both innovation and collaboration. As part of such efforts, we hosted today's first Samsung 6G Forum. I believe today's forum was a very exciting and inspiring event towards 6G. I'd like to thank all the speakers and participants. I look forward to meeting you all offline, hopefully next year. So thank you very much. Thank you. Bye-bye.